Hello everyone, welcome to this video presentation about Introduction to Safety Instrumented System (SIS). The first topic will be on the industrial disasters. This video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly subscribe to the channel. Industrial disasters. We will go through an overview. What is industrial disaster? Oil and gas production facilities, chemical and petrochemical industries, and power plants operate with petroleum, gas, several chemicals which are prone to hazard. Industrial accidents are some of the most unfortunate as they often result in personal injuries, damages to the equipments. Accidents in the plant can also put employees out of work or out of a job depending on their nature of injuries. Industrial accidents are commonly the subject of workers' compensation claims and cases. So here we are seeing two photographs. One is the refinery which is under normal operation. The plant is running with a steady state and production is going on. And second picture, what we are seeing is an industrial accident, wherein there was a fire on the refinery. Here we can see fire engulfing from the plant and different units of the plant, and we are seeing some fire extinguishers being used to extinguish the fire. Also we are seeing one more tank which is under fire. According to safety experts, there are three basic causes or factors that contribute to accidents in organizations. They are chances of occurrence, unsafe conditions, and unsafe acts on the part of employees. Actually, accidents do not happen by itself. There could be some error, some mistake which could have been done by one employee knowingly or unknowingly. To avoid industrial accidents, it is important to understand the different common types of industrial accidents and then apply necessary cautions. Okay, we will go over the elaboration of the accidents. Some accidents are minor and cause injury to the workers. They don't get big damages to their body. It is only causing minor injuries to the workers. So these are the few examples. One is lifting. Many employees are prone to sprain, strain, or tear a muscle by virtue of lifting an object that is too heavy for them to lift on their own. The workers or employees, they need to do lifting only up to their capability. If the weight exceeds their capability, there results in a small accident. Or fatigue. Failing to take a break is another common cause of accidents. People working in the outside environment, harsh environments, either hot sun or harsh weather, wind or dust, they have to be very cautious and take intermittent breaks in the shade, under the shade, and then get back to the work. Otherwise they may get into fatigue. Dehydration. This is a loss of water in the body. People and workers in the plant, in the outside environment, they have to take regular water and to keep them hydrated always. Poor lighting. Inadequate lighting leads to accident. The work area and the offices should have adequate lighting. The lighting is poor, there are chances of getting into accident. Handling hazardous materials like oily greases, toxic chemicals handling. People who are working in the plant in the industrial area, they need to wear gloves, hand gloves, and safety boots always, especially whenever they are handling hazardous materials. Otherwise, some chemicals are very toxic in nature and then damage their hands. They touch it mistakenly. Acts of workplace violence. There could be some minor misunderstanding between some employees and they may get into quarrel, which has to be avoided. Trips and falls. So slipping due to any barricade, scaffolding, and falling from heights. there could be some scaffolding or some barricade in an area where work is involved. So the workers need to take proper care. Stress, physical stress that the employees undergo, it is either due to their duties or due to their personal circumstances. They have to be careful. In all the above cases, the workers in that particular job or task gets minor injuries to them. Okay, we'll further go into the detail. Some accidents are major and cause injury or death to the workers and equipment damage. Accidents in an industrial site or production facility which are very severe in nature are categorized as major accidents. Types of such accidents are chemical spill or leak, explosion, radiation leak, building collapse, gas leak, mass poisoning, and industrial fire, etc. The accidents happening under this category are known as major accidents, which cause severe damage to the plant as well as the personnel. In the early 80s and 90s, there were number of such chemical industry disasters happen around the globe. So I've just listed out a few over here for our understanding. One is in Halifax explosion in Canada. It happened in the year 1917. The nature of hazard is explosive chemicals damage, and it resulted in 2000 people's death. And Bhopal in India, it happened in the year 1984. It's a methyl isocyanide gas leak which resulted in 3500 people's death. And next one is Chernobyl in Ukraine. The accident happened in the year 1986. It's a nuclear power plant explosion due to wrong operation, wherein hundreds of people died. And next one is in Sandoz, Switzerland. It happened in the year 1986. There was a chemical spill resulting in hundreds of people's death. And another BASF plant in Germany. It happened in the year 1921. It's a ammonium sulfate and nitrate spill happened, which resulted in 600 people's death. And another one is in Phillips, Texas, in the US. It happened in the year 1989. It's a polyethylene reactor fire, which results in hundreds of people death. It's not only causing the death of the people, but the area surrounding to the plant gets severe damage, because during these such accidents, several chemicals gets into fire and gases leaks, and they spread around the surrounding environment of the plant, which causes inhalation issues and several other issues to the people in the environment. So it has to be taken care to avoid such accidents. Glimpse of industrial disasters. Major industrial disasters calls the attention of the plant management, giving an alert to take more precautions in future, and they're getting published in the magazines as well. So we are just seeing two examples over here. One is in Bhopal, India, gas tragedy, which happened in the year 1984. It's a methyl isocyanate gas leak. See, it has been published in the magazine. And another one is in Phillips, Texas, in the US, which happened in the year 1989. It was a polyethylene reactor fire that resulted in an explosion. We are seeing the explosion and then gas engulfing around the plant area. So which has happened in the year 1989. This also caused a lot of damage to the people surrounding that plant area. How do you know and how do we go for a solution for these disasters? And solutions to major industrial disasters. If not all, most of the accidents are preventable. By careful design of the plant, safety systems can be improved. In the early 80s and 90s, safety systems were not well planned and plants were not equipped to handle such major accidents. Control systems were not robust. Therefore, it was one of the direct cause of those accidents. Better designed and more dependable control systems could have prevented or significantly reduced the severity of accident. Hence, Safety Instrumented System (SIS) was evolved. Now we went through the industrial disasters, about the classification of minor injuries, major accidents, and we came to know about the different type of accident that involved in the plant. It's one of the system is plants are getting installed with the safety instrumented system. So we'll be discussing in detail about this one in the forthcoming topics. Thank you. Hello everyone. I am going to present a topic on Introduction to Safety Instrumented System on behalf of instrumentationtools.com and automationcommunity.com. Kindly subscribe to the channel. So our topic for this discussion is going to be safety. Safety is going to be explained. Safety in detail. What is safety? Safety is the method to have accident-free work culture. Few safety slogans to remember. Safety is number one priority in the operating plants. Everyone to go home safely as their families are waiting. Accidents hurt, safety doesn't. Every accident is a notice that something is wrong with the men, methods or materials. Investigate, then act. Safety is the ultimate goal of each plant owner, operations and maintenance head to ensure all employees complete their work and return home safe. So whenever in the industrial environment where lot of hydrocarbons, gas and oil is being used along with toxic chemicals is being used, there are chances of getting some accidents inside the plant facilities. So it is the sole responsibility of the operation heads to operate the plant safely and ensure that all employees are safe and get back to home. Okay, why do we need safety? Safety is required for people to work with peace of mind and contribute their entire skills, ability for the growth of the plant and organization. Plant, operating facility, administrative offices are unsafe, then there is a high probability of accidents to occur, which not only cause injury or death of employees and also results in equipment damage, production loss. If the hazard is worst, it may spread to the community around the plant and create various environment and health issues to the people, plants, etc. Plants that handle hydrocarbons, toxic chemicals, oil and gas are prone to severe hazards unless they are properly maintained. Why we are talking about the safety again and again? Because the plants which are handling with the hydrocarbons and toxic chemicals, oil and gas in the production facilities and several manufacturing units, there is a high chance of risk that hazard can happen due to any small mistake, any small attentions not being given properly for the safety. Hence, it is the individual responsibility to work safe as well as prevent any unsafe activity in their vicinity. The workers and employees who are working in the plant, they have to be very careful, watch around the plant, and whenever they make movement in the plant, they have to watch around places to ensure that all conditions are kept in safe operating condition. Otherwise, the fire extinguisher is not kept in place in the office and there is some small electric fire happening, there is a chance of getting big damage to the office, injuring so many people and causing several damage. Likewise in the plant, there are oil ponds around and people should not go and do the smoking over there, because in the plants in general there is a specific designated area to smoke If they fail to do this and then go with the cigar to the plant, there is a high chance of getting a fire happening in the plant. Okay, what is safety system? In the earlier presentation topic, we looked into several industrial accidents that happen across the globe in different facilities. Safety system is a prevention layer, acts in such a way to control if any hazard happen in the plant, when the plant control systems could not prevent the hazard happening. A plant control system is normally used to operate the plant in an automated, steady state manner or with the small step changes wherever the production is required. But if there are some hazardous conditions happening, there is a tank overflowing happening or a pump failed to start and causing accumulation of toxic liquids, so there are chances of getting fire or any other accident. So the plant control system cannot stop this one because it automatically keeps on giving command for the plant to operate. So there should be an additional system, additional protection layer, which is known as safety instrumented system, so which has to take in control and do the preventive action to control the hazards. Better designed control systems can prevent and significantly reduce the severity of accident. Hence, safety instrumented systems was evolved. This will be discussed in detail in the forthcoming topics. So we are going to discussion on this safety instrumented system, about its implementation, and there are several requirements, and how to do the engineering, how to do the installation, commissioning, everything. Okay, safety instrumented system, we have industrial standards. Development of international and national standards which require safety instrumented system when hazardous conditions exist. Formal adoption of these instruments by some governments, it's when warranted by process conditions and requirements, it is the right thing to do to protect the people, plant and environment. International agencies such as IEC, ISA set and defines the requirement of safety instrumented system. IEC stands for International Electrotechnical Commission. You will see the logo something like this here. And ISA stands for International Society of Automation. This is the logo for ISA. And ANSI stands for American National Standards Institute. So this is the logo for ANSI. Okay, safety instrumented system. There are different standards within IEC, ISA and ANSI. For the plant safety instrumented system, below standards are being used. One is IEC 61508. This is a standard detail, standard number. This is for the functional safety of electrical, electronic, programmable electronic safety related systems, also known as E/E/PE or E/E/PES. This is being used for the manufacturers. Basically, the manufacturers who are producing the electronic equipment, sensors, final control elements and several logic solvers have to follow this standard. And another one is IEC 61511. This is a safety instrumented system for the process industry sector. Actually, this the one which is governing the requirement of safety instrumented system in the plant, about the installation of the sensor, logic solver and final control elements, about various testing requirements, about commissioning methodology, system validation. Like that, many process requirements have to be fulfilled based on this standard, and this is used for end users. Similarly, ANSI as well as ISA 84 is an instrumented system to achieve functional safety in the process industries. This is also used for the end users. So we will be discussing in detail about the safety instrumented system in the forthcoming topics. Thank you. Hello everyone, I am going to make the presentation on Introduction to Safety Instrumented System. This presentation is being taken on behalf of InstrumentationTools.com and AutomationCommunity.com. Kindly subscribe to the channel. What is Safety Instrumented System? A safety instrumented system detects abnormal process condition and brings it back to a safe condition without human intervention. In the process plants, normally a DCS, distributed control system, is working and doing the plant automatic operations. Whenever any hazardous conditions arise and DCS control system cannot able to contain, then the SIS system comes into action. The predefined action that SIS must take without human intervention when an out of control process demand is placed upon is called a safety instrumentation function. SIS system is comprised of sensors, logic solvers and final control elements. All these things put together is acting upon any particular hazard. So the complete process is known as safety instrumented function. I will go over the synopsis of the SIS system. SIS stands for Safety Instrumented System. Typically, SIS is a separate SIL certified control system. SIL stands for Safety Integrity Level. We will be discussing this in the forthcoming presentations. SIS sensors, logic solver and final control element, which is valves, are to be certified by approved international safety agencies as per international standards. In the earlier presentations, we saw the international standards by IEC, ISA and C, like that agencies. They formulate the standards which is being certified by another set of agencies known as safety agencies, based on which only the manufacturers has to produce the products and then install in the safety instrumented system. Okay, SIS reputed manufacturers include Modicon, Tricon. They are produced by a company known as Schneider Electric Company, Siemens Safety PLC, HEMA, Honeywell Functional Safety Controller, Delta V Safety System, etc. These are the different manufacturers who are making such safety instrumented system. This is for our basic understanding. Safety instrument system action, we'll just understand it basic simple way like what we do in our day-to-day life. Here in this picture, the car is being driven in a highway. The green zone is a normal drive area wherein the car has to be driven. So in an analogy to the process industry, we are giving it as an area of influence of the BPCS, basic process control system. So the car has to be driven in a highway within the green zone. Similarly, in the process industry, the BPCS keep the process into the green area. Whenever there is any hazard happening, though there is a chance of BPCS which cannot control the hazard, so the safety instrumented system needs to come in action. So this yellow zone, whatever you are saying, is the SIS area. So similarly in the process plant, the safety instrumented system takes a control and prevent the hazards. So just as an analogy, we are seeing from the road highway example, the safety instrumented system keeps a chemical process from going into an unsafe zone. Okay, we'll go over the safety instrumented system details, process related P and ID. Yes, safety instrumented system is a combination of sensors, logic solvers and final control elements. Sensor, logic solver and final control element. Sensors, actually what they do, they measures the flow, pressure, temperature, etc. This is sensing from the process and measures the pressure, flow and temperature and various other parameters. SIS sensors detect an out of limit abnormal process conditions. If you see in this particular vessel, there is a temperature transmitter which is detecting whenever the temperature is going high than the desired limit. Okay, logic solver performs logical functions. Controller does necessary logic action. Actually, this is a logic solver which is known as PLC, programmable logic controller. The logics are built in over here, and it is acting based on the some high temperature or high flow or high pressure, whatever it is, and taking an action to give a command to this particular valve to close it. Final elements: on off valve to shut off the flow in the process. This is the one. See, the steam is coming inside into this reboiler vessel. Shut off valve, which is known as a EBV, also emergency block valve. And in this particular P&ID, this is the final element. So whenever the temperature exits over here in this distillation column, this is detected by this sensor, and then the logic solver is having an internal logic built in, so which is sending an output command, because whenever the temperature exceeds, it should not further admit the steam. If it is happening continuously, steam temperature inside the column will go high and there are chances of explosion. So to avoid and safeguard that this distillation column, this EBV takes into action and shuts the steam. So the final elements brings the process to a safe condition by closing the relevant sys valve or EBV without any human intervention. Whatever we are seeing over this here, all this being taken care automatically without any human intervention. Okay, we'll just go over an overview. How does it look? Sensors. This is a logic solver. This is the final element. Sensors are what? The transmitters, what we saw earlier, which measure the pressure, flow, temperature. In some cases, it is measuring the current, power from switchgear. All these is known as sensors. And logic solver, programmable logic controller, wherein the programs are built. They are having different kind of programs like ladder logic, function block diagram, etc. So which is being programmed into this logic solver, the microprocessor based unit, and it works based on the built-in logic, and then gives a command to the final control elements, which is valves. Here in our case, this is shown as a butterfly valve. So normally, why it is shown in double? Because some process requirements may need two valves to operate for one particular logic. Similarly, the sensors are triple. They are known as triple, 2 out of 3. Because we saw one temperature transmitter in the previous small P&ID. Similarly, there will be 2 more. So that particular thing will be having 2 out of 3 voting. So whenever 2 temperature elements goes high, based on which logic solver will work and then give a final command to the final element. Logic solver, this is normally supplied by reputed companies like Modicon, Siemens, Triconix, Honeywell, Emerson, etc. They are the popular manufacturers, and we are just going over a independent protection layer view. This will be discussed in detail in the forthcoming presentations. Just for an outline view, I am just briefing it over here. It's a process, the normal process, and BPCS, which is basic process control system, which is the next layer, and critical alarms, operator supervision, and manual intervention. This is which is in green. This is the next level. Whenever the temperature limit goes high, there is an alarm coming, and then the operator will take an action. At the next level only, we are having the sys system, which is taking a preventive action to prevent the hazards. And further, if the sys system also cannot contain the hazard, then we have physical protection layers like relief devices, pressure relief valve, pressure safety valve, etc. And further, we have the physical protection devices like dikes, and further we have the plant emergency response and community emergency response. All these things we will be going to study in detail, but for our basic understanding, I have just explained it over here. Thank you. Hello everyone, I am going to make a presentation on Introduction to SIS Safety Instrumentation System, and this topic is on Basic Process Control System BPCS. This presentation is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly subscribe to the channel. What is Basic Process Control System? A BPCS is an automated control system to monitor and control the process. Under steady state operation, production, all the controls works in automatic mode. Few controllers may be designed to work in cascade. Cascade means one controller works and giving an output to the next controller to act. There may be some requirement. In the process plants, there are several thousands of transmitters which sense pressure, temperature, flow, etc. and several hundreds of valves that operate in the process. So all these things has to be operated automatically to have a trouble-free operation, for which the BPCS is being used. Here we are seeing a brief overview of it. There are several sensors and valves, and these are all known as controllers. The BPCS what we are talking of, and it is connected to the HMI network, which is known as human machine interface, from which the operators will operate and control the plant. BPCS takes input from the sensors to provide an output to control valve based on approved design control strategy. Based on the process requirement, the BPCS acts and gives a command. So what are the components involved in the basic process control system? We are going to see about the input-output devices. BPCS receives input from sensors, performs internal processing and calculations in the DCS controller, and then sends output to control valve. Sensors measures the process parameters such as flow, pressure, differential pressure, temperature, etc. Or you can measure current, power, etc. from an electrical switchgear also. Control valve. What for it is being used? It's used to regulate the flow, pressure, temperature, etc. Controller. This is the core topic what we are taking of. It is performing in the signal processing, comparison, mathematical calculations, time delays, etc. as per the logical requirement. For each particular process, there is a requirement which is being developed by the process engineers, chemical engineers during the design of the project, and they formulate a control narrative based on which the logic controllers are working and giving a required command to the valves, control valves, to control the pressure, flow, temperature, etc. The whatever required process parameters according to the process conditions. Okay, here we are seeing a simple P&ID view. How does it look like? For example, this is a HCl tank, for example, and the liquid is being pumped into here, and it is being taken away at the bottom, and it is being sent to a different vessel. Here we are having the level measurement using a level transmitter LT100. This is the technique, and there is a control valve LV100, so which is being used to control according to the level which is being built inside the liquid tank, and then sent to the next process. Maybe a tank, it may be a vessel, or maybe going to some boiler, whatever it is. Okay, and here we are seeing a LC control block itself. It is known as LC100. In pictorially it is represented as a controller. Actually, basically it looks like over here, wherein the controller will be having a power supply unit, a central processing unit having control microprocessor based controllers, and an input model, output model, etc. DCS and BPCS we are talking alternatively, but both represent the same. Basic process control system, cascade control, which I mentioned in the previous slide. Cascade control involves use of two controllers with the output of the first controller providing a set point for the second controller. The feedback loop for the one controller nestling inside the other. Here just we are seeing a control room look. How does it look like? Basic process control system, HMI. HMI stands for the human machine interface. Basic process control system has an integrated HMI for controlling the plant from a remote location. HMI monitors are provided in the control room. We are seeing a large screen monitors, LCD monitors, and wherein the operators are sitting and operating the plant. These are all part of the DCS itself. Large screen LCD monitors, keyboard, trackball are part of the HMI. Additionally, annunciation windows may be there for alerting operators with an alarm. There could be alarm annunciation windows wherein any particular level of the tank is going high, or temperature getting into a boiler going high, pressure going inside a boiler is going high. Those things will be indicated by an alarm. This is in addition to the monitors which is available over here. HMIs are located in an non-hazardous location for safety of the operating personnel. If you look at the process plants like oil and gas plants, refineries and other petrochemical plants, all the process area is containing lot of hydrocarbons, flammable liquids and high toxic chemicals, etc., which are hazardous in nature. And the operation plant which cannot be in that area, which is a hazardous area. So they are located a bit away from this process area and connected by fiber optic cabling and all. So this is for the safety of the operations personnel. DCS controllers are connected by to HMI by fiber optic and Ethernet communication cables. The controllers will be sitting in a small room besides the HMI area, and a cable will be there from the field to the controller, and then from the controller to the HMI stations. So this is a pictorial view of the DCS system, BPCS system, wherein we have the transmitters as sensors, and a DCS or could be a PLC as a controller, and final control elements are different kind of valves. So we have gone through a basic overview of the BPCS control system. Hello everyone, I am going to make a presentation on Introduction to Safety Instrumented System, and this topic is on layers of protection. This video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly subscribe to the channel. Layers of protection. What is layers of protection? Layers of protection refers to multiple prevention and mitigation levels used as protection layers in the plant control hierarchy. Each protection layers shall act independently without impacting the other protection layers. Protection layers prevent or mitigates the hazardous scenario, and hence they are named as independent protection layers. So we are just seeing an onion ring over here. This is for the easy understanding of the multiple layers of protection in the plant. So this is a normal plant which is operating, and basic process control and process alarms are available in the next layer, first layer. So this is the BPCS, which is normally doing the plant controls. And at the next level, which is a green shaded area, this is the next level. Critical alarms, operator supervision is required, and manual intervention is required in this level. And next one is the automatic action, SIS or ESD. ESD stands for emergency shutdown system. And physical protection layers. Next one is the relief devices. Mechanical protection devices are installed in plant, which is a pressure relief valve, pressure safety valve, and a rupture disc. Like that, mechanical safety devices are installed. And next level is another physical protection layer, which is known as dikes. Inside the plant area, there are some dikes available. And further, the hazard exits, it is calling for the plant emergency response. And in further, we have the community emergency response. As the picture looks like an onion, it is termed as onion layer. So we'll go in detail about the different protection layers. First one is known as basic process control system, alternately known as distributed control system. In every plant, this system is in operation and doing the day-to-day operations of the plant. It is being controlled automatically for running the process. Be it a refinery, be it a oil production facility, be it a petrochemical plant, be it a chemical plant, a nuclear power plant, thermal power plant, and all other major industries which is involving multiple processes are being controlled using the DCS. Secondly, alarms are configured in the system for operator to take an action. Level in a tank goes high, or temperature exceeds, or the pressure inside the vessel goes high. There are sensors that senses and gives an indication to the control room operator to take an action. Next comes the safety instrumented system, which is going to be our main core topic and the presentations, which acts based on emergency requirements. Under normal operating conditions, SIS is silent. It doesn't take any action, it is just silent. If process hazard is not contained by SIS also, then pressure relief system such as PSV, PRV or rupture disc operates to relieve the system pressure. There is a pressure exits in a tank, SIS giving a command to close the emergency block valve. Even then, the pressure which is contained in the vessel is not getting contained, and there are safety valves installed above the tank top, designed to relieve when the pressure when it exceeds a certain limit. Next one is in the next level of protection layer, tank bunds are built to contain any flammable materials discharged from the storage tank, etc. Actually, in the process plant, if you see, there are a lot of tanks which are located in an isolation area, which is a bit far away from the process plant area, and they are constructed inside a dike. So whenever there is a hazard happening and these protection layers fails, like BPCS fails, SIS layer fails, and mechanical protection system also fails, there is a chance of chemical or oil getting spilled outside the tank, and they have to be contained within that area, so that there are dikes are built inside the plant. So this level is referred to that. And also some area fire hydrant systems are installed in case of any fire happening to protect and quench the fire immediately. And next level of protection is plant emergency system are in place, where emergency response teams, mostly from the health and safety environment team, to control hazards if any. Members in this team are trained to take a preventive action in case of any hazard, fire hazard or any other hazard happening in the plant. It's like a fire service, and they are trained for that plant requirement. And further, the hazard is quite high and exceeding further, and there comes the community emergency response, which will be needed in case of any gas leak, fire having risk to spread around the nearby community. Notifications will be provided by the government appointed authority to evacuate the area by means of media, public address system, etc. As you know, the hazard is going high and high, and it's not able to be contained. There will be a requirement by the plant management and by the local government to make an announcement for the community to evacuate that area. So all these are having independent sensor control system and other thing. In case of mechanical devices, they are having independent pressure relief devices. So all are acting independently without intervention of the other layers, so that it is called independent protection layer. The brief sample of a LOPA workbook, which is known as layers of protection analysis. We will be discussing this topic separately in a forthcoming presentation. This is how it looks like. Here the scenario of a different hazard will be listed over here. Like in this example, it's a reactor vessel failure due to polyol decomposition reaction, and there are different layers acting for the protection of the hazard. So which is listed over here. And here only we can see what can happen, what kind of hazard can happen, and what can it cause, it will result in what, and how bad this will be, like that. And there is a LOPA target factor, like that, what we will discuss in future. It will be arrived at. This is a numerical presentation of the severity. And here in this small process pre and ID, we are seeing a different layers of protection. Particular vessel is having a temperature element and being controlled by a temperature control valve. And in this process, the cooling water is going through a heat exchanger and getting out. And we have one more block valve which is supplying to the tank. So here the failure of this control valve is the initiating event. And BPCS control action is high temperature opens the emergency cooling water jacket. This is a normal action. So this is one independent layer. High pressure alarm is acting using this pressure sensor. The alarm will be acting. That's why it's an independent layer. And assist function A, high pressure blocks the feed to the reactor. And there is high pressure, it blocks the steam to this reactor. That's why it's in the SIS layer, safety instrumented system layer. And further, the tank, this is failed and the tank pressure is exceeding, and we have relief valves installed over here, which is a mechanical protection device, which is known as PSV, also pressure safety valve also. So if we see there are multiple colors, they are all acting independently. That's why it is known as independent protection layers. In our future presentations, we are going to discuss in detail about the safety instrumented system. Thank you for watching. Hello everyone. I am going to make a presentation on Introduction to Safety Instrumented System, SIS, and this topic will be on the significance of SIS system over BPCS. This video presentation is taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly subscribe to the channel. We will go over the detailed view of BPCS, Basic Process Control System. What are the functions of the BPCS? Basic process control system are either active or dynamic. This always making changes in the plant process and then doing the required control. BPCS have analog, digital inputs and outputs, performs mathematical calculations and have feedback loops, maintain or change the process conditions. Based on the requirement, it helps to adjust the pressure control valve to maintain a pressure, or temperature control valve to maintain the temperature inside a vessel, or adjust the flow and all. So it is always varying and then taking action to control the process to the desired level. Basic process control system control helps to obtain best performance from the process, and at times used to increase the performance to the maximum process condition limits that can safely be achieved. Hence, most failures in these systems are inherently self-revealing. What happens? Suppose the one reactor is designed for producing 50 tons per hour. Normally, under the normal operation conditions, it will be operating at 40 tons per hour capacity or 45 tons per hour capacity as a safe operation. But at times, due to the consumer requirement, due to the high demand of the product, that particular reactor may be required to make a high production. So instead of 50, there will be a requirement to change it to 55. Actually, the calculations will be done to ensure that even at 55 tons per hour, it will operate safely without any harm to the equipment itself. So then it will be increased depending on the plant requirement and management requirement, etc. So for those conditions, there will be requirement to change the control logics and then required to improve the output rating. So for all such conditions, the BPCS control inside the program, the logics will be changed, and then it will help to increase the maximum process limits as an end required. This is not always. BPCS are designed in such a way to flexibly allow frequent changes. Process example set points, PID settings like the control from manual to auto, etc. require constant change as per process requirements. If it's a raw material change or output grade change, these are all conditional based on the requirement. There may be changes requirement and it will be required to be changed. So that's why as we see, the BPCS is active and dynamic, so it will be easy for the operation to change the requirement, change the set points, etc. Part of the system may also be placed in bypass and other process may be controlled manually. There are multiple units in the process plant. For example, one particular control valve is having an issue and it may be required to operate it in bypass. I will keep the valves isolated and make the system in the controller in the bypass mode and then operate. So that's why it helps. A BPCS controls are operating at all times. They are not expected to have diagnostic routines searching for faults. As the control system is always in action, as it is dynamic, it is very difficult to make a robust diagnostics inside the controller. This is what it explained in the last bullet point. What are the functions of safety instrumented system? Safety systems are, on the other hand, are dormant or passive. Sys elements are silent while the plant is running. During emergency, it is called into action. Under normal state operation of the plant, the BPCS is taking control and it is doing the required changes and operating the plant on the required process limits. Whenever the process limits exceeds due to some reason, that time the BPCS control is unable to contain the pressure going high or temperature going high or the volume in the tank is going exceeding the limit. In those conditions, the next level of protection, which is a safety instrumented system, comes in action and then does the required action. That's why in the normal condition it is dormant. So we are just doing an example over here. Example would be a pressure relief valve. Normally the valve is closed. It only opens when the pressure reaches the set value. This is another layer of protection, just briefly explained over here. And many failures in system may not be self-revealing. If the relief valve is plugged, there is no immediate indication. It's a mechanical device, so we will not be able to know. The PLC could be hung up in an endless loop. Without a watchdog timer, the system would not be able to recognize the problem. There is a need for extensive diagnostics in dormant passive safety systems. Even though the controllers will be continuously processing and there is no action, like process input is not varying to give an output command, like a control system, it's not dynamically acting and giving an output, always running and doesn't comes into action when the plant is in the steady state. That's why it is known as dormant system. Safety systems need to be kept to a fixed set of rules and access for changes are pre-restricted, and they must be highly reliable and be able to respond instantly when a hazardous situation develops. As this is a robot system and it is required to prevent any hazards, there are engineering stations available which is required to do the configurations and then any changes if required. Plants, there are different level of category people are available. Like one is the lowest level, the technicians will be available, instrument technicians or electrical technicians, mechanical technicians, etc. In our example, we need to think about the instrumentation people. So instrumentation technician will be available. Next, there will be instrumentation supervisors, and further we have the instrumentation engineers in the plant, and further next instrumentation group leader will be there, and further the department leader will be there. Normally the instrumentation engineers were responsible for the particular plant area doing the required changes on the safety instrumented system BPCS system and any other PLCs and all, except exclusively on the safety systems, that each changes requirement will be having a access limit. So based on which only the changes can be made. Like for having authority, who are having very good training on their system only can work on and then do the necessary changes. DCS or BPCS does not have that restriction. Anybody who are knowledgeable can go and do the work. We'll see the functional differences between the BPCS and SYS. BPCS receive input signals directly from the process through sensors and instruments and generate output signals to control the process and its associated systems to operate the plant in proper way. Safety instrumented system is composed of hardware and software components used to control critical process systems, that is refinery and chemical nuclear power plants. BPCS implements multiple functions including the management of process variables, alerting, monitoring, and the provisioning of an interface of monitoring and control through a HMI. SYS devices are system responsible for facility operating in safety. They have no control or emergency procedures in case of abnormalities belonging to the process, bringing to the anomalies, bringing the process to a safe state. It is all an automated action only. Whenever the hazardous scenario is happening and the BPCS is failing to control it, next level SYS sensors are taking into action and then gives a logic command to close the SYS valves. BPCS does have some inbuilt security functionality, as it is considered the first layer of prevention in the protection of the process. In SYS, processor, communication, input and output models are designed intelligently to overcome any external attacks. This is related to the cybersecurity attacks and much more robust items of cybersecurity, as SYS systems is certified by IEC, ISA cybersecurity system standards. In the recent past, one system had external cyber attack which had resulted in the unit shutdown. So if there is any external attack by some malware, there is possibility of system getting hacked or corrupted, which may call for the plant shutdown. So this is recent incident. That's what I explained over here. It's not that BPCS cannot have cyber attack, but even though there is something happening in worst case scenario, it will not hamper the plant operations. Only a part of the plant, part of the controls will be failing. Okay, we'll just go through the testing and certification requirements between BPCS and SYS. So these are the different criteria which is listed over here, and we'll see whether it is mandatory or not mandatory. Certification for safety applications, in case of SYS, it is a mandatory. BPCS, it is like optional, it is not a mandatory one. And redundancy, the controller redundancy. If you see the SYS system, mostly the controllers are triple modular. There are 2-3 controllers working parallelly, each are having the same program and they are working simultaneously. And BPCS in such case may have redundant controller, but also it is not a mandatory requirement. This is based on the process and process size and nature of process, etc. Proof testing requirements. For the safety instrumented system, proof testing requirement is to be met as per the IEC standards. It is mandatory. Whereas in BPCS system, it is not mandatory. It is again optional. Whenever only particular loop in the just having a BPCS control has to go for a testing, but again time limits may not be as strict as SYS. Extensive system diagnostics. This is what we talked earlier. The controllers have more robust intelligence, and then they have to go through a more rugged kind of diagnostics running inside the processors, input output models, communication models, etc. Whereas the BPCS system, it is not mandatory, even though many of the manufacturers and many of the systems installed across the plants have diagnostic facilities. It is not as extensive as SYS. access control requirements on the engineering stations. This is what I discussed in the previous slide. For each system, there are independent engineering stations available to make a program on the BPCS system, to make a program and changes on the C system, etc. And there are hierarchies there to control the access. It will be decided by the respective plant head and production owner. So this system have some higher level of hierarchy. Only people having much experience on the particular process plant and they are very thorough with the process and instrumentation, safety instrumented system knowledge only, they can do the changes in the program in the C system. Whereas in BPCS system, everybody have the right to do the changes. Field instrument redundancy based on the safety integrity level. Again, this is a calculated one based on the layers of protection analysis, etc. So for the SIS system, it is mandatory. For BPCS, it is not mandatory. BPCS, which is working as a safety layer, can work with an independent single instrument also. And this is a seat leakage requirement as per APA standards. This is for the valves, shutoff valves need to undergo a seat leakage test, and this is mandatory. There is a APA standard like IEC, ISC and all. APA is for American Petroleum Institute. This has constituted a standard. So based on which the valves which are in the SIS loop have to meet the requirements of the seat leakage as per the standards available, whereas it is mandatory for the SIS system, whereas it is not mandatory for the BPC system. So the SIS system is having overall much more ruggedness, much more testing and certification requirements compared to BPCS. Thank you for watching. Hello everyone, I am going to make a presentation on Introduction to Safety Instrumented System, and this topic will be on functional safety. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly subscribe to the channel. Functional safety, we will go over the brief of it. Functional safety means the safety function will be performed automatically as per the intended function in the event of any hazard happening. Functional safety enables the techniques to get rid out of unacceptable risk. This is achieved through the safety life cycle. In general, it is adapted from two main industrial standards, IEC 61508 and IEC 61511. These standards help address the safety life cycle and address different types of failure from faults. We already saw these two standards. IEC stands for International Electrotechnical Commission. There are two standards, 61508 and 61511, which governs the safety requirements. To improve the plant process safety, functional safety systems enable the orderly shutdown of processing units when abnormal situations occur that are beyond the capabilities of basic process control system or operators to correct or prevent a hazard. Under steady state scenario, the plants are operating in an automated way using the basic process control system, which is always doing some action to maintain the process in a steady state and giving production output. If there is any hazard happening and the basic process control system is unable to contain that hazard, then safety instrumented system comes into picture. Whole concept and study about the safety instrumented system are part of functional safety. Functional safety will go over the multiple layers. The goal of functional safety layers is to reduce the risk of accident or injury. The many layers of protection that a plant uses to safeguard the process, equipment, personnel and the community. Here the different layers are in different colors for our understanding. This is a process, normal process, which is operating in a steady mode. Plants are designed to operate in this steady mode. And here we have the process control, which is loop control and measurement, everything, which is done by the BPCS, basic process control system. So you are seeing it, this one in the green color. So a plant has to operate in the safe zone, green zone. And then further the limits are exceeding. For example, we will just understand this using a small P&ID over here. There is a chemical tank which is having a hydrogen chloride facility. For example, required chemical is being sent into the tank using the isolation valve, emergency block valve, flow control valve, and then it is being admitted into the tank. And in the tank, the pressure is being measured, the temperature is being measured, the volume of the tank is being measured, and based on the volume, if the level is going down, this control valve is operating using a flow indicating controller and then admitting additional chemical into the tank. Here we are having level switches for high level indication and another level switch for the high indication, based on which the emergency block valve will shut. Tank level keeps on increasing and it is not able to be controlled by the control valve function, and in this case level high, LS adjust means level switch high. So when it reaches to this limit, then sensor will sense and give a signal to close this emergency block valve. This is the operation sequence, and when this valve also fails, emergency block valve also fails due to some reason or some components inside the block valve is not functioning, say solenoid valve, so it may not function properly, and then the chemical keeps on adding into the tank, which will result in increasing in the tank level and getting the pressure inside the tank getting high. So in this case there is PRV, known as pressure relief valve. This operates and then vent the pressure into the atmosphere. And in further case, if the pressure relief valve also does not function and there is any choking or any plugging inside the pressure relief valve and it is not able to relieve the pressure out of the tank, so then there are chances of spillover happening above the tank top surface, and then it will get into the dikes. This is a dike. Generally the hazardous chemicals and all other hydrocarbon related materials are stored in a dike in the process area plant, and this is one kind of protection layer. And further, if it is exceeding, suppose the chemical is keep on adding into the tank and then gets out due to all failures, it gets out and getting filled in that dike area, so there are high chances of getting any further hazard, maybe a fire, so which require a plant emergency response. So we'll go, we are just going through this one through the layers description. Then the normal operation, process is designed to operate in normal mode, and process control, which is BPCS, is controlling and keeping the process within the green zone. And if the BPCS limits or controllable limits are exceeding, it gives into an alarm, which is level switch high in this case, and this alarm requires an operator intervention to make a field visit and then close relevant valve to minimize the level increasing. And further, if it is exceeding and it reaches to the level switch high, and this is a trip limit wherein safety instrumented system acts and then the emergency block valve used to shut off the chemical into the tank. And further, if the valve fails, and in such cases the active protection, in this case some incident has happened, so the failure of the emergency block valve happened and then the chemical admission into the tank is not able to be contained, so now it's resulting into an incident. In this incident, and during this condition, which is an orange zone, and the PRV is taking into action and it is trying to lift the pressure from the vessel, and still the pressure cannot be relieved using the PRV due to its failure, and it is calling for a passive protection, which is a bund and dikes. So whenever there is a chemical spillover and it has to be collected in the dikes and drained out to the proper drainage system using a proper process. So this is a loss of containment, and if this is still not contained because operator misses the action, and then the emergency block valve does not act, pressure relief valve does not act, and then the chemical keeps on adding into the tank, so it keeps on adding and it is overflowing from the dike also. In this case, it is calling for a plant emergency response. In the plants, there are health, safety and environment team is there, wherein the process safety personnel are sitting, and there are some trained people who will take an action during any kind of such emergencies. So that's why it's put in the black color, and they will take action to contain any further hazard spreading out. Further, if it spreads out and there is a chance of any gas leak, any fire happening in the plant, then it calls for any community response. So community response will be called off by the plant director, and people around the area will be required to be moved to a safe zone. If you see this protection layer graph, each of these acting independently with the independent sensors or control valve and set-off valves like this, or mechanical relief devices like this. So all these first 4 layers are known as prevention layers. So within this, the normal plant has to control and then limit the hazard not to exceed. If it is not able to be contained within this zone, then it's called a mitigation layer. Now, so in this case, that's why we are saying here an incident has happened. Now there is no choice or no question. Now the emergency has to act and then mitigate the hazard from spreading further. So these are all the different layers in the functional safety. Okay. So, and how functional safety is achieved? There are many steps involved in it, and we are just going through this 7-8 brief steps. So identify a system with the design of the plant using a P&ID and process manual, and identify the requirements of any safety, design requirements, safety requirements, operational excellence, etc. The next step, A1, and the next step, the hazards has to be identified using the HACCP study, and there are some safety analysis, operation safety reports has to be prepared based on the ISO and other things, and even based on the IEC requirement standards. And you're using this one, the risk assessment has to be performed by the team, and there will be a process safety personnel, process operation personnel who are having a thorough knowledge of the process and what kind of risk can happen in the plant, and they have to be having good knowledge of the process, so that only they can identify if there are any chances of any hazard can happen, any risk can happen. In this step, the LOPA, LOPA for layer of protection analysis, failure mode effect analysis, FMEA, fault tree analysis, and combined fault tree and another matrix is there. This analysis, all these things are being done in the risk assessment stage. So, and then required functional safety layers, the protection layers, what we saw in the previous slide, the different layers has to be designed and allocated. And further, next as a next step, the designs engineered SIS. Wherever the safety instrumented system is required, the number of sensors and the number of final elements and the different seal level has to be identified using engineering study, and then the SIS has to be designed. And there are different tools, Simulink, MATLAB, LabVIEW, like that, different tools are there which is required to be used during this step. And then this is a step of again engineering study, and then the plant is being installed, and after installation the safety instrumented system need to be verified for its proper operability. So all these are known as safety management systems, and as we discussed in earlier slide also, IEC 61511, IEC 61508, these are the different international standards giving the licensing requirement. So functional safety, where it has to focus, the functional safety focus is on ensuring safety critical functions and functional threats in the system, subsystem and software are analyzed and verified for correct behavior per safety requirements. Program software is doing the calculations and giving the output command for the final limits in case of any sensor signal goes high or low. So in this case, the logic solvers are working and giving a output command. So all this system, subsystem and software has to be analyzed in this functional safety. Functional safety focus includes any functional failure conditions, faults, inappropriate mitigation in the design. As we saw in the previous step-wise design, and this is part of the requirement of the sys engineering. And functional safety's complete scope is to treat the function of a component or subsystem as part of the function of the entire automatic protection function of any system. There are many subsystems within a major system, so everything has to be automated. The automatic protection function should be ensured as a part of functional safety. Functional safety standards and functional safety methods should focus on electrical, electronic, programmable electronic systems as well as non-electrical, electronic, programmable systems, which are the safety relief valves, PRV, PSV. There are rupture discs to relieve the pressure also, and dikes, everything. These are all non-EPS because they are not electronic, they are mechanical protection devices. So functional safety, who are the participants to do the functional safety analysis? Process hazard analysis and safety instrumented function allocation strategy studies gives clear idea for functional safety engineers as to put many protection layer clarifications into action. This is the one what we discussed in the couple of slides before about the different layers, how to allocate the number of sensors and number of the type of logic solver and the type of final elements and all as far as sys is concerned, and many different layers like mechanical protection devices, etc. So who will be the part of it? The functional safety experts, process licensors, operational personnel, process design engineers, plant safety experts, assigned safety instrumented system coaches of the facility will take part in the functional safety analysis. These are the people who are participating and deciding the different types of requirements. They will be part of the plant engineering design team. We will go over the functional safety standards. So functional safety standards activities follows the international standards, which is IEC and CISA standards. IEC is 61508 is one standard, 61511 is another standard, and CISA 84 is another standard. IEC stands for International Electrotechnical Commission and C stands for American National Standards Institution. ISA stands for Instrument Society of Automation. IEC 61508 is giving the details about the functional safety of electrical, electronic, programmable electronic safety related systems. So the standard is giving the requirements for all this. IEC 61511, this is specific for the process industry. This is giving the standard requirements for the implementation, commissioning, validation and verification of the safety instrumented systems. ISA 84, it is application of safety instrumented system for process industries. These two standards are for the process industries, and IEC 61508 is for the manufacturers who make the products for the safety instrumented system. It may be sensors, may be a logic solver, it may be a final control element. All the components within these three, so sensor, logic solver and final control elements, has to be certified and has to follow the IEC standards. What is the role of functional safety standards? IEC standards focus on eliminating the risk and maintain the plants in safe state. Here just we are seeing a small pictorial representation wherein functional safety, which ensures the safety through electrical, electronic, programmable electronic technology, and its main intention is to maintain a plant in a safe state, and if there is any source of danger is happening, and in this case it is going from the normal operating mode to a hazardous situation, so functional safety standards take into action. Functional safety standards has a set of rules which has to be adapted by the industries during the engineering and design stage, and it has to be implemented properly and as well as maintained throughout the life of the plant to achieve the safety of the plant and people and equipment. So the requirement, whenever any hazard is happening, it has to get into the safe zone to get out of the hazard, for which the functional safety standards helps to develop the standards. Another thing, it is having a safety function requirements, safety integrity requirements, so many things. So we will be discussing different topics in the future presentations. Thank you everyone. Hello everyone, I am going to make a presentation on Introduction to Safety Instrumented Systems (SIS), and this topic will be on SIS terminologies. This video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly subscribe to the channel. SIS terminologies. The objectives, why do we need to understand? Provide different terminologies in safety instrumented system design, implementation, commissioning and maintenance. Users, who will be the users of these terminologies? Safety instrumented system coach, who are responsible for the SIS design. Instrumentation automation engineers, who are involved in SIS design, maintenance, operation personnel, maintenance teams like instrument maintenance specialist, technicians, valve maintenance specialist and technician. In this presentation, we will be seeing lot of abbreviations only. There is no other graphical or pictorial presentations, because this topic is whole mentioned for the terminologies only. Okay, below the different terminologies which we have to use in our practice of safety instrumented system. LOPA. LOPA stands for Layer of Protection Analysis. We will be discussing in a separate presentation about LOPA. HAZOP stands for Hazard and Operability Studies. And BPCS. BPCS stands for Basic Process Control System, which people may be aware. Also, it is known as DCS, Distributed Control System. Actually, since we are talking about the topic on SIS, the credits which are taken in the BPCS column in the LOPA workbook are considered as BPCS loops. We will be going through the LOPA in future presentation, so you can understand about it. OPR. OPR stands for Operator Response to Alarm. Those credits that are credited in OPR column in LOPA workbook are considered as OPR tags. And Safety Instrumented System, SIS. This we are talking in frequent, so we will be easily understanding this terminology. SIF. SIF stands for Safety Instrumented Function. The whole function which SIS is performing is known as Safety Instrumented Function. PFD. PFD stands for Probability of Failure on Demand. That is the probability of that a system will fail to perform a specified function upon demand. This is known as PFD. And TI. TI stands for Proof Test Interval. In the SIS process and during life cycle and other study, we will be understanding about the proof test requirement, and TI stands for the proof test interval. SRS, this is known as Safety Requirement Specification. This is a design requirement specification which has to be filled. It is an Excel sheet based template. The SIS design, implementation and commissioning is documented in SRS template. This is part of the designs, SIS design requirement. Whoever will be working on it has to understand and fill up the safety requirement specification before going into the process implementation. Proof test. Proof test is a periodic test performed to detect dangerous failures which are not detected by automatic diagnostic tests, to demonstrate that the equipment operates according to the design basis and is maintained in as good as new condition. A proof test is being performed for the safety instrumented system sensors, logic solvers and final elements to ensure that they operate whenever there is a demand, whenever there is any hazard happening and it is occurring to act, that has to, the sensor elements has to act. And verification is a confirmation by examination of objective evidence that the requirements have been filled. Tests performed on the SIS instrumentation to ensure that they perform as designed. This is known as verification. So when we study about the SIS design, we'll be using these terminologies. Validation. The act of proving a safety instrumented system acts as expected upon initial installation or after functional modification by performing a physical test of the complete system end to end. Validation means we have to test the particular scenario, particular operation sequence of the safety instrumented function. So it is being done by initiating the sensor to reach the limit, maximum limit, to sense the level high, pressure high, temperature high, whatever it is, and then operate the logic. The logic is being performed automatically, and then the respective final element is taking action to close. Okay, the complete testing is known as validation, and this is performed only once when the system is implemented or the safety instrument system is modified. Okay, logic function. It is a function that performs the transformations between input information provided by one or more input functions, that is provided by multiple sensors, and output information used by one or more output functions. So similarly, there may be two valves which is required to close based on some logic. So all these mathematical functions based on the process requirement, based on the safety instrumented study, is being implemented using the logic function. And MTTR, it is a mean time to restore. Actually, if there is an instrument failure, this is the expected time of the instrument to restore from a fault. If there is an instrument failure during the operation or maintenance, so it has to be restored and put back within a certain time. So this is known as mean time to restore, mean time to restore. SIL. SIL stands for safety integrity level. This is ranging from SIL 1 to SIL 4. So higher the SIL, lower the expected PFD average. PFD is probability of failure on demand average. Lower the average frequency of dangerous failure causing an hazardous event. If there is a higher SIL level like SIL 3, SIL 4 and all, it is the highest safety. And diagnostic coverage. This stands for measures. Diagnostic coverage is the one which measures the effectiveness of the diagnostics implemented in a SIS sensors. SIS sensors has an inbuilt electronic functionality testing which is giving the diagnostic coverage. SC, this is systematic capability. SC, systematic capability, is achieved when the equipment used to implement any safety function is designed using procedures intended to prevent systematic design errors. So this avoids the systematic capability is a parameter used in the SIS design. It is helping to prevent any design errors. So we understood about the few terminologies which will be frequently used in the safety instrumented system design. So brief explanation about the different terminologies used in the SIS have been detailed. The SIS users, operation and maintenance personnel need to get acquainted with the terminologies and use in safety instrumented system for better understanding and working on the safety instrumented system. Though this complete presentation is referring only to the terminologies, I would emphasize the users to read this, view the video multiple times and understand the terminologies for the better understanding of the safety instrumented system. This will be used frequently in the forthcoming presentations. Thank you. Hello everyone, I am going to make a presentation on Introduction to Safety Instrumented System, SIS. This topic will be on definition of LOPA, Layer of Protection Analysis. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly subscribe to the channel. LOPA concept. LOPA is a process of evaluating the effectiveness of independent protection layers in reducing the likelihood or severity of an undesirable event. LOPA is used to evaluate high consequence scenarios, determining if the combination of probability of occurrence and severity of consequences meets company's risk tolerance. Each company will be having a risk tolerance upon which hazards has to be worked out, and then the LOPA has to be studied and the desirable factors, independent layers of protection has to be built into the facility. LOPA is most commonly used effective semi-quantitative technique. By such quantification of risk, we arrive at required LOPA target factor. We will see this in the below slides. LOPA definition. LOPA document defines what are the high risk scenarios in the plant. What are the protection layers considered in each scenario to bring down the risk of an acceptable risk to an acceptable level? When the plants are built, especially the plants handling the hydrocarbons, oil and gas, heavy chemicals, and various chemicals, toxic chemicals, they are prone to hazards. As the plants grow older, the chances of hazard is getting increased. So the LOPA study, and there will be one more study known as hazardous operability. These will be required to be done to build the required protection layers. LOPA takes into account more factors than most qualitative technique. Hence, this is widely preferred by many plants and organizations. LOPA is a good document for training and awareness about the process hazards of each plant. Risk is quantified by impact of people, business target factor, based on value of loss, and chemical specific target factor, chemical specific safety target factor. These are the three parameters which is used to identify and quantify the risk. And when we are studying about the LOPA, we need to understand one more acronym known as ALERP. ALERP stands for as low as reasonably practicable. The LOPA technique can be put into place by companies who are striving to achieve a specific target factor or to lower risk as low as reasonably practicable. The triangle here represents the decreasing risk and the diminishing proportional benefit as risk is reduced. The ALERP principle can be used to define two sets of risk tolerance criteria, a minimum requirement and a target value. The companies cannot go on spending millions of dollars to build the safety requirements and build many layers to get out of the hazards. Hazard is inevitable, but the company need to make a balance between the process with respect to the minimum requirements safety requirements, and they need to achieve a target value to make it into a tolerable level. Between the two sets of criteria, the range of risk is tolerable. ALERP guide has been produced to explain the concept of reasonably practicable in a simple way by HSE Health Safety Environment Committee by the United Kingdom. If you see in this triangle, the risk is increasing. As I told earlier, when the plants are getting older, the chances of risk is getting high because of the maintainability, because of the spare parts availability, and for the plant with 20-25 years old, the identical spares which are used from the beginning of the plant may not be available. For example, the plants built in 1970s, 80s, those instrument and spares which were used in those days may not be available, and it is not practically possible to upgrade the complete plant by spending millions of dollars. So the companies will be very conservative to invest the required quantity of money to achieve the safety in an economic way. This we all know. The companies normally used to make the study and then arrive at as low as reasonably practicable cost. So here we are seeing in this triangle the risk is keep on increasing as the plant goes to older. So when we want to achieve the tolerable zone, which is the green zone over here, this is the ideal levels of risk. Risks are negligible or so small that they can be managed by routine procedures and no additional risk treatment measures are needed. This is the most preferred zone and hence it is known as tolerable. And next one is as low as reasonably practicable, a level of risk that is tolerable and cannot be reduced further without expenditure of cost disproportionate to the benefit gain or where the solution is impractical to implement. So this is an ideal zone. Actually, the risk can be reduced with spending the money as per the requirement. Intolerable levels of risk. Adverse risks are intolerable. Whatever the benefit and risk mitigation measures are essential at any cost if activity is to continue. Some cases the risk is very high because, for example, we are using the fuel gas, fuel oil, toxic chemicals in a plant. So just to overcome the risk, we cannot make parallel lines of gas to a facility. So building a pipeline of very huge size will incur very high cost. In case of any emergency or any requirement to shut down one line and use the other line, it is practically not possible, and it will be incurring very heavy cost. If you see on the other part of the triangle, see when we are from the intolerable level to most tolerable level, if you are going to reach, we are going to spend money. The cost is gets on increasing when you are going to do this exercise and build the plans to achieve the practically tolerable limit. So companies need to strike a balance between the intolerable zone and the tolerable zone, which is known as low as reasonably practicable. So this is a part of study of the LOPA technique, and people need to understand about this one. Okay, how this LOPA workbook looks like. This is the real workbook from LOPA. Here, the protection gap will be listed over here, and the target factor should be listed over here. And this is the scenario definition. Here it is giving the scenario number, and the next part, next column, it's a description of undesired consequence. So this tells what can happen. See, for example, in this slide example, It's a reactor vessel failure due to polyol decomposition reaction. This is one of the scenario which is causing the risk. Okay, how do we mitigate this risk and arrive at the safe factor? So we have to arrive at a LOPA target factor of 6. This is the desirable limit which we will discuss in the forthcoming presentations. And initiating event factor, so which initiates this kind of risk actually, very little catalyst present due to acid leaking into a reactor and neutralizing catalyst. This is a kind of a risk, how it can happen, how this hazard can happen. So, and enabling factor, this is sometimes it is compounded with some other factor which enables that risk. And probability of exposure, I think how long the people will be exposed to that facility and all will be listed over here. And this is the scenarios, and in the right side of the columns there will be different layers like BPCS control layer, operation layer, and sys mitigation layer, and then further mechanical devices, pressure relief valves, etc. How it is going to act, each item, each protection layer is going to act and mitigate the hazard from happening. So finally we will have to arrive at the target factor. When there is a gap between the target and the protection, required protection gap, there will be a requirement of building some additional instrumentation, some additional mechanical protection. So these things need to be understood. So we have to go through the detailed study of both layer protection analysis and the mathematical modeling to arrive at that required protection. So layers of protection, we'll have just quick bite with this slide. LOPA can be quickly and easily understood with the Swiss cheese model per pillow diagram. If you see on the other, similar to the earlier slide, there has to be many independent layers of protection. So as the plant grows older and older, there are chances of hazards getting increased day by day, and irrespective of that longer duration of the plant, when the plant facility is being built, even the new facility is being built, the as-of study has to be undertaken after the process P and ID is frozen. The as-of study has to be during the process P and ID study, as-of has to be taken up, and LOPA has to be worked out to identify the type of safety instrumented system that has to be installed for the facility, and type of the protections need to be included in the design, so which will give us a clear picture of different layers required to prevent in case of any hazard is happening for the particular facility. There may be multiple scenarios available, and each scenario can contribute to different kind of preventive methods to prevent the hazard happening. So we need to understand all those things which require a detailed training and understanding. So now we went through a basic concept of LOPA to understand the basic requirement, and then this can be used in our further presentations. Thank you. Hello everyone, I am going to make a presentation on Introduction to Safety Instrumented System, SIS. This topic will be on Safety Instrumented Function. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly subscribe to the channel. What is safety instrumented function? Safety instrumented function explains what safety instrumented system does. SIF basic function include below categories: how an out of limit or abnormal process condition will be detected, how the process will be brought to a safe condition without any human intervention. These two categories explains the SIF's requirement. As per IEC 61511, this is the international standard, SIF is designed to achieve the required SIL which is determined with the other protection layers participating to the reduction of same risk. You would have seen in the earlier presentation videos that there are multiple protection layers. Each one is called independent protection layer. So they have to act concurrently. Actually, they have to act one over the other. So the SIF is designed to achieve the SIL determined with the other protection layers. That's what is mentioned. First level is a BPCS control layer. Next level is the operation alarm response by the operators. Next one is a safety instrumented function layer. Further, we have the protection layers like pressure safety valve, pressure relief valves, etc. SIF is designed to achieve the required SIL which is determined with the other protection layers. Safety instrumented function allocation. Safety instrumented function allocation means of detecting the required risk reduction for the chosen or allocated safety function on the P&ID. In the P&ID it will be marked, so the safety function has to be allocated accordingly. Health safety environment risk management team should obtain and review tolerable risk criteria applicable to the facility from the end user. This shall also include spurious trip rate data and risk ranking methodology. This also includes safety integrity level allocation methodology. These are all the further technical terms which will be used while calculating the safety integrity level and calculating the SIS requirement. Spurious trip rate is by the instrument and valves manufacturers data. So they have to analyze these things for making the required SIF allocation. We are talking SIF again and again, so better we'll understand it through a P&ID. SIF defines what the SIS system must do to control a specific abnormal process condition. SIF is defining what the SIS must do to control a specific abnormal process condition. It can be understood with a description. We are just explaining it over a small P&ID. This is a distillation column. A feed is coming into the distillation column. It is having one reboiler. Reboiler stream is being admitted to do the required stream heating, and then from this reboiler the outlet is going to the next process, and further we have some coolant available for the condenser, and there are reflectorums available, and the reflux is also being sent into the distillation column, and the collected distillate is taken out and going to the next process. Okay, in the distillation column we have some measurement instruments. Here we have one temperature transmitter which is shown in black. So this is in the measurement loop, which is in the BPCS control system. So this temperature loop is being controlling the control valve to operate and admit the stream, required stream. Whenever there is overpressure in the column or temperature is exceeding high, the temperature transmitters, other two temperature transmitters, these are shown in the red color, so which is part of the safety instrumented system, safety instrumented function, and these two temperature transmitters are sensing the temperature inside the vessel, and this is signals are going into the logic solver, safety instrumented system logic solver, and from the logic solver the output is going to the valve. This is EBV, emergency block valve. So here the SIS stops the stream feed to the reboiler. This will be in action whenever the temperature inside the column exceeds the preset limits. Okay. In this distillation column example shown, when the temperature in the column reaches a specified point as measured by TT10096 and 10097. These two are the temperature elements, TT10096 and 10097. So, and this is measured, and then steam to the reboiler will be closed by ABV 12390. Automated block valve, or it is emergency block valve, ABV or ABV. Okay. Each SIF is numbered according to the business rules. Here we are seeing SIF 1111. So, this particular safety instrumented function is numbered with this number SIF 11111. So, all the relevant sensors and the final control elements, they are having the same SIF number. On the P&ID, SIS components are typically identified by a hexagonal symbol that will give the SIF number in the symbol. See, here seeing this SIF number we are seeing in the hexagonal picture. So, this is identification for the safety instrumented function. These temperature elements are belonging to the safety instrumented system, and then it is having a SIF number. And similarly, this emergency block valve is also belonging to the safety instrumented system, and this is the relevant SIF number, because in the process plant there are several thousands of sensors, valves and other measurement elements. So, each has to be identified separately for a quick understanding, and for the instrument maintenance people and the operation people to get an immediate knowledge how this particular instrument is behaving and where it is connected. Supposing if this instrument is not working, they have to see the relevant alarm announcement window in the DCS screens, and then there could be some error reported over here. If it is reported, so the same has to be informed to the maintenance technician, or if it is not reported, just simply it is not showing any reading, they have to call the particular technician, maintenance technician and maintenance engineer of the plant to say that this particular element, like TT10096 is not working. Like that they have to report, for which the numbering sequence is given in an unique way. In the field, SIS equipment associated with a given SIF will typically be identified with a supplemental hexagonal tag that gives SIF number. In the field where actually the temperature element and temperature transmitters are located, that will be in the plant area. There also it will be identified with an hexagonal tag showing SIF number, so that the tag number of the instrument plus SIF number of the particular system will be easily identified for the ease of the operation and maintenance team. This is very important for the proper identification. Otherwise, there could be a chance of an error. Instead of attending to the T10096, people may go and attend another one. This is TT10046, which is also identical and it is in the same location. So, if the tagging philosophy is not properly maintained, there could be a chance of an error by attending to a wrong instrument. So, the tagging philosophy and the SIF identification need to be made actually in the field also for making an error-free maintenance. SIF identification. The SIF safety instrumented function identification. For identifying a SIF, easiest way is to provide a unique SIF identifier in the LOPA workbook or LOPA database tool for each function. So, while developing the LOPA, each scenario will be numbered uniquely, which is giving the SIF number. This makes sorting very easy, and a unique SIF identifier will eventually be needed for SIF documentation. A common SIF identification scheme is to make the first three numbers the same as the P&ID number of the SIS sensors, and the last two numbers be a unique SIF number on that P&ID page. Each P&ID will be having a different sequence of numbers. The identification is given for the SIF number, safety instrumented function. The first three numbers after the SIF is related to the P&ID number where this particular instrument sensor is being installed. And the last two numbers, they are an unique identifier. For example, in this particular PNID, there could be some 8 or 9 sensors, or there may be still more. So this numbering gives an sequential reference for the operations and maintenance team to identify and attend to the respective instrument in case of any fault or in case of any maintenance required. This is a typical identification which may vary each plant and EPC. Each plant owner and the engineering procurement construction company may be having a different tagging methodology. So accordingly, they will provide. This is a typical one. More or less, the EPCs and different engineering companies will follow the standard, but there could be some difference based on the geographical location of the plant, based on the end users requirement, etc. Normally, the PNID page will be referred in the SIF along with an additional unique identifier. These are all the basic requirements and needs of the safety instrumented function, how it will be used. We understood what is SIF and how it is being used in the process plant and how to number it and what is that kind of tag to be used in the field for the identification of the maintenance people and the operation people to make any routine maintenance or to attend to any faults. This has to be followed thoroughly to avoid any mistakes. Okay, thank you. Hello everyone, I am going to make a presentation on Safety Instrumented System SIS loop. This topic will be on components of safety loop. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. What are safety loop components? Safety Instrumented System has basically three main components to perform safety functions. Sensor. This is to measure the process parameters such as pressure, temperature, flow, differential pressure, etc. Preferably having SIL, Safety Integrity Level certification. It is preferred to have such certification for these sensors. Logic solver. This is an intelligent controller, usually a programmable logic controller, which is having very high processing speed and scan time. As we all know, the SIS logic solvers has to act very fast depending on any hazard happening inside the plant. So the processing speed and the scan rate for those processors shall be very high. So the logic solver has to be selected accordingly. Final control element. This is an automated on-off valve having SIL certification with the solenoid valve, limit switch, instrument air regulator and pneumatic booster release. These are the subcomponents. Solenoid valves, limit switch, instrument air regulator and pneumatic booster release are the subcomponents of an automated on-off valve. So when the valve is built with all such accessories or subcomponents, it has to get certified by the relevant certifying agencies like ICSIDA, TUV, etc. and other international agencies for the qualification of safety integrity level according to the requirement of the process. Alternate safety loop components. Safety instrumented system has further components, electrical and analytical instrumentation. Earlier what we saw is all are process related, sensors and final elements. There are other components as well. So sensors, they are current transducers, power transducer, analytical instruments such as oxygen, CO2 measurement and gas chromatograph. This will be used in the refineries, petrochemicals and other chemical industries. Logic solvers. Sometimes field mount PLC having more ruggedness and high temperature rating with high speed scan time can be used as safety PLC. Normally the safety PLC BPCS controllers, everything will be located in an air-conditioned area, either in the process zone and connected through a fiber optic cabling. Within the process zone, it will be in a shelter which is having a gas detection system and other thing to detect any gases appearing inside the shelter. Normally, this is a case, or in some cases, DCS and safety instrumented system controllers may be located in the control room, which is far away from the process area, and they are in a safe zone. But there are field mount PLCs available these days which can withstand high temperature, and they can be deployed in the field directly, but only a small cooling system using an instrument air through a vortex cooler. This is like a small cooler arrangement can be made to keep the temperature within certain limit. Otherwise, they are prone to work with higher temperature than the conventional PLCs, which are to be housed in the air conditioned zone and safety zone. Final control elements. For an electrical interface, there is an interposing relay to give trip command to motor starter. Motor starter is nothing but it's a electrical device. It's a controlling the switchgear for the pumps, turbine, fan, etc. In this case, electrical relays also need to undergo the proof test requirements. In the earlier slide, we saw it is an on-off valve having multiple components, but there are interposing relays which is mostly sitting in the switchgear control room in a separate electronic cabinet that will be taking the input from the sys logic solver and giving a command to trip the switchgear, which is for the pumps, turbines, fans, etc. So now we are seeing it process loop. These are the typical safety loop components. There is one reactor which is having a pressure transmitter, temperature transmitter. In this slide, we are seeing both BPCS and sys, because to make an explanation and understanding, it is given separately. There are two temperature elements. It is connected to the input-output modules of the BPCS controller, and the output from here, it is going to the control valve. So, other than that, there are two pressure transmitters and one temperature transmitter which is connected to the input-output modules of the safety instrumented system. The complete this unit, which is having a power supply, CPU stands for central processing unit, IO unit, which is input-output unit or input-output module. Here, for example, this is an input module because all the sensors are being connected over here, and this is an output module which is giving a connection signal wiring to the final element on-off valves. And these two are known as the sys final elements, which is the on-off automated on-off valve, and these three are the sys sensors. So this is a safety instrumented system PLC having a power supply, CPU, input-output modules, etc. And we are seeing different picture showing typically a valve, a sensor, everything. So here we are seeing in this process there is a gas flow or liquid flow is going through this process line, and there are two valves by one manufacturer known as Emerson. The valves are the actuators or Betis actuators. They are having the components like in the previous slide. This is air filter regulator, this is solenoid valve, this is a booster relay, and there are actuators which is doing the action for the on-off valve. And the valves are by one manufacturer known as Virgo valves. Similarly, there are two valves are there because sys final elements normally there will be two valves for the safety depending on the SIL category, safety integrity level category. And we have one more component known as DVC controllers as well, which is the digital valve controllers. So this is the final element, sys final element, and there are three sensors for measuring the pressure of the process. These transmitters sense the pressure and then gives a signal to the logic solver over here. And this is again another manufacturer known as Rosemont pressure transmitters. Since there are three transmitters, they are acting in a 2 out of 3 voting logic, and then they are connected to the controller, which is a delta V sys logic solver. All these components are by one manufacturer known as Emerson. The sys controller PLC is having a communication link to the BPCS HMI monitors and all, wherein the operations can see the actions being taken by the sys controllers. Okay, earlier we saw there are electrical interfaces as well in the safety loop. Here we are seeing electrical relays which is giving a input to the PLC. Actually here we have barriers, isolators, converters, relays. These are different electrical components. Normally it is through barriers we are getting the signals for the current and power measurement. And this is our PLC, which is having the hardware for processing the signals and then giving an output command to the field devices, which is a relay. This here we are seeing the example of an electrical interface. So here we are seeing one electrical relay, and through the relay from here it will be going to a switch gear which is operating the motor, fan or pump, etc. So this is a typical electrical interface. We are having barriers and isolators to get a signals like current, power, transistor signals, and then giving an output command through an electrical relay to the switch gear. We are again and again talking about the sensors, final elements and logic solvers. There are logic solvers also. There are having different designs. One is a redundant configuration which is having two PLCs or two central processing units running always in parallel. They are doing the processing function and they are always in parallel. In a healthy environment, in a normal environment, both processors will be acting, these two processors, and in case of failure of any running processor, there will be an automatic switchover to the secondary processor, and this is known as redundant configuration. And here we are seeing one panel having multiple terminal blocks and electrical components and main power supply MCBs, which is circuit breakers, and there are some relays mounted over here and some barriers mounted over here, and this is all giving to the signal, and input output terminals are also located over here. And here inside, which is shown in yellow color and shown by that arrow, is a PLC. It's a redundant PLC configuration. And the another one is a triple modular redundant. Here we are seeing, see, these are all known as modules. So first one is a power supply module, the second, third, fourth are the processor modules. Here we are seeing 1, 2, 3 identical modules. They are known as the central processing unit with the 3 redundant, because there 3 are operating parallelly. There is a watchdog timer between the 3. So whenever any one fails, the other 2 will be functioning. Supposing the second PLC also fails for unknown reasons, it can work with the single PLC also. But under normal running conditions of the plant, all the 3 processors are running parallelly. So this is known as triple modular redundant. This is given by some vendors, and there are input modules, output modules and communication modules, etc. for the functioning of the processor and giving command to the other systems like a BPCS system and sometimes other third-party systems. So these are the sys logic solvers, and we went through the different components: sensors, logic solvers and final elements. These are the components involved in a safety loop. Thank you very much. Hello everyone, I am going to make a presentation on safety instrumented system loop. This topic will be on basics of safety instrumented system, sensors. This video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. What are sys sensors? Sys sensors used to detect process parameters such as pressure, temperature, flow, and electrical signals such as power, current, and analyzer signals from chromatograph, oxygen, and CO2 analysis. CIS sensors in a safety instrumented system measure process variable conditions in order to recognize a potential hazard. Usually, these are the same process variables that are used for control measured by different sensors. In the process piping or an equipment, there are multiple sensors. One set of sensors being used for the control application only to control the process, and whereas the CIS sensors will be in the same location, same application, but they are being measured by a different set of sensors. Most important consideration when selecting CIS sensors for safety application is that they accurately and reliably measure the process variable. This is the most critical one. Whenever the CIS sensors are being used in the process, selection of the sensors should be in such a way that they measure process parameter very accurately and as well as reliably, because the repeatability of the measurement is another criteria. Need to ensure that those sensors are being quite rugged and having a long life for the accurate measurement of the process. That's why in the safety instrumented system there are some proof testing requirements. Any process vetted materials must be compatible with the chemicals of the process. In chemical and petrochemical industries, there are several chemicals being used which are having more toxicity, and some chemicals being capable of corroding the sensor part. So the sensor part, the body of the sensor material has to be selected accordingly, and to ensure that any chemical being used in the process should not hamper the measurement. Some case stainless steel sensors or stainless steel body is being used as a sensor. Instead, we will go with the tantalum or other materials which are having very high temperature withstanding capacity or proven for chemical applications. Typical safety instrumented system sensor usage. This data is being collected from 2020 by an agency in the United Kingdom, which is for the health safety environment system of the United Kingdom. So this is the overall population of safety instrumented sensor being used in the process industries. Here we can see a pie chart showing the portion of distribution as well as the chart. Pressure transmitters are the most highest quantity being used, which is having a population of 38%. Temperature sensors around 19, level sensors around 15%, flow sensors around 14, gas detection sensors like analyzer signals and gas chromatograph signals, those kind of sensors around 6%. Flame detection system sensors are around 8%. Here the electrical signals are missing, but usually they used to be very negligible, about 1% population. This is a generic data across the industry for the safety instrumented system application. Here we are seeing one logic table, truth table for the typical 2 out of 3 safety instrument sensor voting. We are again and again seeing about the type of voting and other thing. Whenever the process requirement is very high accuracy requirement based on the process and the size of the equipment being protected, size of the vessel being protected, like an reboiler equipment, like a distillation column, or like high pressure piping, which is being protected against the hazard by safety instrumented systems. There will be 3 transmitters to measure the pressure. If it is a vessel, it could be a level, or it could be a temperature. Like that, different kind of measurements, whatever we saw earlier. There will be 3 different sensors on the same process line to ensure that 2 out of the 3 sensors going to high level or high pressure, high temperature. This is to ensure that there is no tripping or safety action being taken whenever a particular instrument going false, just to ensure that instrument reliability is quite high and for the safe operation of the plants. So this is a small truth table. People who are done the electronics subject or instrumented subject, they should be quite aware of this logic gates. This is an AND gate and this is an OR gate. In this case, whenever it is a 2 out of 3 voting, two sensors X, Y, Z are considered to be 3 different sensors and B is the output. And whenever two sensors, like here this case Y and Z going high, the output will be 1. This is a simple logic truth table. Safety is being handled and protected. The equipment is protected suitably in a safe way according to the process requirement. Some cases it could be 2 out of 2. Some cases it could be 1 out of 1 and all. These are all votings are all depending upon the process requirement, which will be decided by the process safety experts and the safety design experts, etc. during the design of the process. Sensor diagnostics. This is another important requirement to ensure that a safety instrumented system sensors are being working quite reliably and accurately. Some sensors designed for safety instrumented system applications typically have built-in automatic diagnostics. That attribute is one of the main advantage of sensors designed per IEC standard. IEC standards mandates having self-diagnostics kind of sensors in the safety instrumented system application are quite important and critical for the process requirement. Smart meter verification overview. This is actually provided by one manufacturer known as Emerson. They are providing an additional electronic board in the same sensor to ensure that the diagnostics and meter is being functioning perfectly. This is being used for some flow measurements and inline flow measurements like ultrasonic flow measurement type of transmitters having this facility. Smart meter verification, which is known as SME, enables to check flow meter's health without taking the flow meter out of process. Normally, the safety instrumented system sensors are always functioning, like in the earlier slide what we saw is 2 out of 3 sensors voting. Maybe in this case only one sensor can be kept out by doing a necessary bypass in the system logic. Whenever the instrument is an inline instrument, it is not possible to remove the transmitter and take it to the workshop to do the calibration and testing. So for those kind of instruments, Emerson is one manufacturer is providing a smart meter verification kit. Smart meter verification helps to detect the tube buildup and the potential instrument damage. Actually, this is about the flow meters, as I was telling. Sometimes there are process chemicals or process liquids or gas being used may form a deposit inside the tube. So this SME will help to detect if there are any buildup. SME performs a traceable calibration verification with a patented tube integrity diagnostic to ensure mechanical stiffness of the flow tubes. These are all basically for the mass flow meters. So the SME can perform a internal calibration to ensure that the tubes are not choked or something. Okay. Usage of SME provides early detection of instrument damage before it creates a safety risk or accuracy shift. As I told, reliability of the instrument should be very high whenever it is used from the safety instrumented system application. This SME helps to make an early detection because it is doing self-diagnostics always. This traceable calibration verification as well as verification of all electrical components is included as a standard feature. Actually, this is a statement from the manufacturer Emerson. Internal calibration verification. This is doing verification of the flow tubes as well as the electronics which is available in the sensor. Whenever customers are buying the sensors with the smart meter verification, they ensure that the integrity of these components are being checked. The SIS sensors are always quite reliable and used for the safety and protection of the plants, but always there are chances that some may fail. So there are some concerns about the safety instrumented system sensors as well. So what are the concerns? We will just go over quickly. It is advisable to select safety instrumented system sensors with SIL certification. SIL certification is being given by some agencies. We saw in an earlier presentation. They are known as TUV, EXIDA, ISO, etc. So it is preferable to go with the SIL certification whenever it is used in the safety instrumented system application. But however, do not select instruments only because they are SIL certified. Actual site performance is the most crucial based on prior use considerations. The SIL certifications not to be proven one because the certificate is being provided by the agency and the application is quite different. One plant in one part of the world is having a very cold condition and ambient is very cold and the atmosphere is very clean. Instruments can work perfectly without any issue. Whereas the same instrument being used in the other part of the world where the humidity conditions are quite high, temperature conditions are quite high, it may not prove to be working successfully. There could be some issues. 90%, 95% could be fine, but there are some chances that the same instrument which is used in one part of the globe cannot be very good in the other part of the world. There could be, not 100%. There could be. So wherever the even though we have the certification, it is good to check that particular type of instrument has been used in the particular plant in this zone or in this area and has been working without any troubles. So this is known as prior use. It could be for the same plant, it could be for a different plant which is having a similar kind of process. For level and flow, where many different types of measurement technology exists, and hence the site conditions like weather, ambient conditions pose a critical challenge. Like especially for the level applications, there could be some capillary tubes bringing the level measurement, and there could be some fill fluid. So it may get hardened with the cold weather. Some part of the globe, we know the weather is quite chill, it is going sub-zero temperature, and whereas in the other part of the world the temperature is going 50 plus 60 degree and all. So internal chemical components may get either choked or it get solidified too much. So and this one, and as well as the weather conditions, ambient conditions, some part of the globe the ambient is always quite clean and the atmosphere is quite clean, and even the pollution control is being done very thoroughly so that no pollution happens and does not damage the human surrounding. Whereas in the other part, the atmosphere itself may not be very clean, which may also pose a threat for the good measurement of the level or flow. So for the right technology, some manufacturers has done a complete IEC 61508 assessment. This is an international standard. So some manufacturers are doing this assessment as per this standard. Then that product might have a considerable advantage. This has to be analyzed thoroughly before selecting the SIS instrumentation. As I told, one particular type of instrument and measurement which is being used in one of the plant in, for example, in America, cannot be exactly having the same kind of repeatability whenever it is being used in the other part of the like Asian continents, wherever the temperatures are very high. So this is also a critical concern that sometimes sensors may not behave as good as behaves in a different plant. So these are all some challenges to be taken care while selecting the safety instrumented system sensors. So these are all the few concerns. This will be corrected or this will be understood very well over the continuous usage and applications, and by experts in that particular region who are having quite knowledge on the type of sensors, type of application being used, etc., to have a good selection of the safety instrument system sensors for use in the right application. Okay, thank you. Hello everyone, I am going to make a presentation on safety instrumented system loop, SIS loop. This topic will be on basics of SIS logic solvers, safety instrumented system logic solvers. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. What are sys logic solver? Sys logic solvers are built with very high speed microprocessors and perform the required logical functions. Usually the processing speed lies in milliseconds. Sys logic solver is typically made up of redundant double or triple processors, power supplies and human interfaces. Here we are seeing one picture having a redundant PLC configuration. Here we are seeing two processors having the same functionality and working in parallel. This is a redundant configuration. We have two redundant communication modules as well and redundant interface modules which is going to the other system and power supply modules, etc. Okay, what are sys logic solver? Sys logic solver will process many safety instrumented functions concurrently. So sys logic solver is capable of doing multiple logical functions concurrently because they will be running in sequence. That whole processing scan sequence is around few milliseconds only. Okay, sys logic solver will have continuous monitoring the healthiness of processor, also known as watchdog. In case of any running processor fails to perform, secondary logic solver takes over the control and error is reported back to the control room via an annunciation system alarm, etc. As we saw in the earlier slide also, the configuration was a redundant configuration wherein two processors having the same application program are working parallelly. And in this case, in this diagram, we are seeing three triple model redundant, which means three processors are there. You are seeing the picture over here having three processors and two power supply modules. It is having the communication modules to the external interface and input output modules, etc. So in this case, we are having three processors working parallelly. In case of failure of any one particular processor, the second processor takes over and continue to perform the same function as required. So as there are three processors doing the simultaneous functions, this is known as triple modular redundant. This particular technology is being manufactured and supplied to the plants by some manufacturers. Okay, we will further go over the sys logic solver certification requirements. International Electrotechnical Commission (IEC) provides all the requirements necessary to design, implement and operate safety system logic solver in a safety relevant application according to the certification. There are international agencies who govern the requirements of the logic solvers and provide the necessary design and implementation standards. The logic solvers, the manufacturers has to comply to it and then produce the products accordingly. The certifying authority assesses each logic solver intended for use in sys applications. The hardware, software and safety manual of the logic solver is analyzed for the purpose of application to be used. Each manufacturer has to provide the complete documentation about the hardware and the software being developed and safety manual of that particular logic solver for the standard agencies to review and give an approval. New logic solvers purchased for sys applications in any plant are to be certified according to the IEC 61508 standard. IEC stands for International Electrotechnical Commission. 61508 is a standard number which is for the manufacturers. So any logic solvers purchased has to be certified by the IEC requirement. They have to abide by the IEC requirements. Safety manual must be prepared for all certified sys logic solver. The safety manual describes any limitation applicable for operation and maintenance. It also addresses diagnostics, testing, programming languages, and the skill level for which the device is capable. A safety manual contains several details about its application requirement, program requirements, the redundancy, applicability, everything. It will be a detailed document giving all the details and the internal testing calculations for that hardware. It is not that any manufacturers of any PLC can supply a system or PLC saying that it can be used for the sys applications, because sys application is for protecting the plant from any hazards. So the particular systems, the PLCs used in the sys application, they need to be certified by the International Electrotechnical Commission and the relevant agencies approved by them. They have to abide by the standards developed by International Electrotechnical Commission. So IEC 61508 wants a standard which is applicable for the manufacturers to abide by the requirements of the standard. Okay, Sys Logic Solver application program. Sys Logic Solver application program of the Sys shall be in accordance with the application program safety requirements. Like I described earlier, any program cannot be written, and the PLCs used in the sys applications, they need to go through the set of rules given by the IEC, and then prepare the required logics. So application programs should follow a standard methodological way. There are different types of application programs, different types of functions available, like function block diagram, ladder logic diagram, cause and effect matrix, like that. But whatever is applicable and approved by the International Electrotechnical Commission has to be obeyed. Sys Logic Solver application program to be designed in such a way that all parts of the application programs are executed on every application program scan. Process safety time requirements shall be considered in establishing application program scanning requirements. There shall be a process safety time for each of the functions to do the processing. So that has to be considered when establishing the program. Sys Logic Solver application program and data are to be designed in such a way that they can be modified as and when required. Any program revision has to be monitored, controlled for its version management, backup and restoration procedure. Application programs shall be built and developed in such a way that any modification requirements as per the process need can be accommodated with proper care, and it can be modified at any time by the certified people, and who are doing the program, they have to monitor the revision, because for example, it will be a revision level from 0 to 999 or something. So every revision has to undergo through the revision change, so that whenever any application program error happens, or the logic did not perform as per the process requirement or as per the intent, the developers or engineers who are working on it can go back and verify what has been modified and what is the mistake had happened. That that prevents the logical program execution to not happen like that. So it can be monitored, and in case of any error happen, that can be corrected. So the version management is very important, as well as the backup of the programs is also a critical one, because whenever there is any PC crash or something is happening, then it is very difficult, and there is a power supply failure for the processor racks or something, there could be a chance of the program getting deleted totally, or there could be a chance of any crash on the processor itself. It's a rare possibility because all these systems have redundant power supply arrangement also, but in worst case scenario there could be a chance that the complete power supply may go off and there is a chance of the program getting removed totally. So in such cases the backup available on the engineering workstation PC has to be uploaded to the processor. And restoration procedure, that's what, in case of any total failure of the system, that PLC has to be brought back in line to ensure that the safety instrumented system application comes back for the safe operation of the plant. So this is a restoration procedure also has to be properly written. Sys logic solver communication, we are just seeing the communication. Design of any sys communication interface shall ensure that any failure of the communication interface shall not adversely affect the ability of the sys to achieve or maintain a safe state of the process. Because the sys systems, as we have seen in earlier slides and we have been seeing in multiple occurrences, that they are having one SIL certification. They are capable of doing certain level of this SIL requirement, safety integrity level requirement. So all the parts of the logic solver also need to be having the certification, and it has to have the capabilities which includes for the communication network as well. Communication interface to be robust to withstand any electromagnetic interference including power surges without causing a dangerous failure of the sys, because there are hundreds of cables running in a cable tray, and normally the network cables does not carry a heavy potential. The maximum voltage will be around 20-24 volts, whereas there will be some cables running quite closer or adjacent in adjacent tray having 11 kV, 33 kV, like that high voltage capacity. Though there is a physical segregation between these two cabling, there could be a chance that due to any cable fault on the power cable, EMI interference can happen, and which can hamper the communication to drop. This is similar to our mobile networks, whenever we are going inside any closed area or very far and the high altitude and all, sometimes we are not getting a proper signal. So it's something more or less similar to it. So when we go through the detailed study about the safety instrumented system as well as the basic process control system, so we will understand about the different communication interfaces available. Most popular communication protocols include OPC, TCP/IP and serial communications with the plant BCS and other systems. See, here we are having basic process control system, its modules, and it's another set of modules power supply, and here in this part of the big network diagram we are seeing some transmitters working in a wireless way. They are connected through a wireless gateway and communicating with each other and then communicated to the system. And the other part of the system is a safety instrumented system, wherein there will be redundant processor or triple model redundant processor having a interface with the field devices and also having interface with the other systems, the like DCS system and the human machine interface, etc. So there will be number of communication cables running between the sys system logic solvers and to the basic process control system. So there are different protocols which is described over here, like OPC, TCP/IP and serial communications. Who are having knowledge in the communication and networking can know better about it. So these different kind of communications are available with the sys logic solver with their communication interface modules. Sys logic solver diagnostics. Sys logic solvers shall be capable of performing diagnostics. Functionality of processors shall be monitored, and if there are any troubles in running processor, secondary processor to take over automatically. Some systems have redundancy direction module to do the changeover. There is one more module known as redundancy and direction module. Whenever any failure of particular running processor, it will automatically give a command to the secondary processor to take over. Sys logic solver, any errors will be reported immediately and logged as well. Supposing the running processor fails and it is not able to do the calculations and it's not able to do the communication with the other systems, then that particular processor will stop due to some fault, either internal fault or some power supply failure for that particular module or something. So then the secondary processor will automatically take over and continue to do the safety protections and process the logics as per the design. So in such cases, any error occurring has to be reported and it has to be logged so that the same can be retrieved when the plant is in normal conditions and sent to the manufacturer for them to do the analysis and then come out with the diagnostics. Application level diagnostics are to be implemented, such as external watchdogs, application data integrity checking and sensor validation to meet the required safety integrity level. Actually, the application level, there are to be diagnostics which has to be implemented and monitored. Like watchdogs means it's a kind of program which is confirming that both the processes are in a healthy state. Whenever there is any fault, any processing sequence issues or errors, watchdog will report and then do the changeover. So healthiness of the processes is very critical for the safe operation of the plant. Thank you. Hello everyone, I am going to make a presentation on safety instrumentation system loop, sys loop. This topic is on basics of sys final control elements. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. What are sys final control elements? Sys final control elements are the protecting device that saves the plant from potential hazards, if any. In the process industries, the most common final element is a remote actuated valve. This assembly usually consists of a pneumatic control assembly, an actuator and an on-off valve. The control assembly may be as simple as a three-way solenoid, a small partial valve stroke box, or complex electro-pneumatic assembly with solenoids, pneumatic booster relays and quick exhaust valves. Here in the picture we are seeing a typical picture of a on-off valve. This is a valve part and it is assembled with an actuator, it's a spring return actuator, and it is getting we are having other pneumatic components fitted into the valve assembly. All this complete setup is known as on-off valve, automated on-off valve, which is used in the safety instrumentation system application. Similar type of valves are used in the BPCS applications as well, but the safety related testing requirements, proof test requirements and all will not be as stringent as sys. Okay, we have the air supply coming into a filter regulator which observes any moisture in the air, and it is going through a three-way solenoid valve, which is one either passing the instrument air to the actuator body. The air gets into the actuator body, it works against the spring pressure to push it down and thereby opening the valve. And whenever any emergency situation arises, any hazard arises, that time the solenoid valve port will move in such a way that the air will be vented out. instead of it will be vented out through the vent port instead of getting into the this thing. So the air in this chamber will get out through this vent, and thereby the spring will act with its force to close the valve. This is a typical on-off-valve assembly and its components. In some cases, there may be many components like volume booster, and in some cases some air receiver tank. Capacity of the actuator is huge. There could be some volume booster and receiver, air receiver. Otherwise, these are all the general components. Additionally, we have, these are all pneumatic related components. Additionally, we will have the limit switch for the valves and a positioner in some cases. Like this, other components will be there. Okay, basics of this final control elements. On-off valves. There are many different types of valves used in the safety instrumented system. Typical valve types include ball, butterfly. In butterfly, we have the double, triple offset butterfly valves. Here we are seeing two different pictures. One is a ball valve fitted with an actuator. It is connected to the process piping. It is having a multiple pneumatic assembly like solenoid valve, instrument air filter regulator, etc. Like we saw in the previous picture. It is mounted with an actuator, double acting actuator, which enables to open and close the valve. And in the bottom part, we have the butterfly valve shown with an actuator. It's a disc, a butterfly disc, which will move against the pneumatic force. There are many different type of actuators. They are defined by their power source and range of motion. Actuators typically use electric, hydraulic or pneumatic power sources. There could be electrically operated actuator, there could be hydraulic as well as pneumatic power sources. But across the process industry, in many applications, we could see only pneumatic actuators, which is more reliable and quick acting. All of these different designs have different performance characteristics, different failure rates and different failure modes. These are the internal characteristics of each components, based on which the safety manual, what we discussed in earlier topic, in the safety manual, the failure rates and the failure modes of each components will be listed by the respective manufacturer. There are other devices also in the SIS final control elements. And other types of safety instrumented system devices include simple devices like relays, motor controllers as a final element. In machine control applications, the final element may be a motor controller. In rare cases, other devices have been used as final elements in safety instrumented functions, such as annunciation devices like horns, flashing lights or sirens in safety functions. Most of these will be in the fire protection systems. These will be simple like a relay which gets power from the digital output model for the safety instrumented system. This is about the typical safety instrumented system final control element usage. This is the data from the 2020 figures. Here we are seeing the percentage of different type of safety SIS final control elements being used across the industry, across the globe. This is around 92%. See, particular type of device which is a on-off valves, automated on-off valves. This is around 92% being used across the industries, and electrical relays usage is around 5%, and motor controllers is around 2%. Annunciation horn, bulb, siren, all less than 1%. So this is the typical data collected by the UKHSE department. Critical requirements of on-off valves used in the safety instrumented system. Safety instrumented system final control elements. Valves to be selected carefully, considering the valve type, materials, fluid challenges such as particulate, corrosion, erosion, cavitation, noise, etc. and ensure the valve is SIS capable as per the SIS design. We had talked about it in earlier slides also, when we talked about the safety instrumented system sensor, chemical process which is used in the process, characteristics may be erosion nature, which can impinges to the valve body. There is a possibility of erosion or cavitation, which may impact the performance of the safety instrumented system valves. Or some devices, some chemical components may have solid materials in it, which can also cause the performance to get affected. So that with the particular type of design, that particular process for the particular type of design has to be selected during the initial engineering phase. Valves used in seat leakage class 6 shall meet API 598 and ANSI FCI 70-2 requirements. This is a valve seat leakage requirement class, which is decided by the certifying bodies or international agencies, API and ANSI. So whenever the valve used in class 6, normally in many applications in the industries, chemical industries, oil and gas industries, the requirements may be very stringent. The valve has to have a very tight shut off. Whenever it is closed, it should not pass the gas or fluid which is entering into it. So this is known as tight shut off class, and it is class 6 requirement as per the API 598. We will understand it whenever we go into the detailed application requirements of valves. A partial stroke test device can be used to extend the time between foolproof tests. It can identify many failure modes, but it cannot identify everything that a full stroke proof test would capture. Partial stroke test device is an additional component in the pneumatic assembly, which is not installed in every valve. Based on the process requirement, some of the valves cannot be stroke checked because either it is a single valve in the particular piping and doesn't have a standby valve to support. So in such circumstances, or the system may not be possible to be isolated while the process is in running condition. In such cases, we may go in for partial stroke test device, which is an additional component that gets a signal from the control system, sys system, which can slightly move the valve. It will not move the valve completely. It will move less than 5 to 10% to ensure that the valve functionality is working good. Because as we all know, proof test requirements is very stringent for the safety instrumented system final control elements. In some cases, according to the process requirements, stroke testing may not be possible. In such cases, partial stroke test device shall help. Another one, which is a digital valve controller. Digital valve controller overview. Digital valve controllers can perform safety functions, capture demand stroke time, a great tool for partial valve stroke tests. Using these devices allows a partial valve stroke test to be scheduled as frequently as required. Hidden failures such as sticky movement and friction torque changes due to process buildup easy to identify. Digital valve controller is an additional device which can give a command to the partial stroke test device itself to move the valve partially. In addition, the ability to monitor solenoid valve health has greatly improved safety loop diagnostics and reliability. The digital valve controller can check the healthiness of the solenoid valve also. The solenoid valve is the critical component of an automated on-off valve that has to function properly. So, functionality also can be monitored using the digital valve controller. Both solenoid operated valve and digital valve controllers are powered separately. An advantage of this shift loop compared to the earlier stage is the redundant shutdown provided by the digital valve controller. Sys final elements, there may be some drawbacks using the sys final control elements. Nuisance or spurious trips which can result in an unplanned process or plant shutdown. There could be some unwanted trips which could have been avoided. This is due to failure of some components. This is a routine trouble with some maintenance being not done or the components getting aged and getting wear and tear, etc. Although a spurious trip is safe for the plant and personnel, the financial impact due to loss of production is substantial. The spurious trip, on one hand, it will improve the safety of the overall plant and it can protect the personal equipment and the environment surrounding, not to go for any hazard conditions. But on the other hand, whenever any spurious trip happens and the plant or part of the plant becomes shut down, that production is getting affected, thereby loss of production. That's a financial burden. Covered or hidden failures remain undetected and permit normal process conditions. This failure type is dangerous and contributes to the probability of system failing on demand. The testing shift loop is therefore crucial in uncovering the covered failures. This is one type of failures, so the proof testing can improve to avoid this one. If the valve and all related components are certified seal capable, that does not guarantee with the valve meeting the intent. Normally, whenever we go with the SIS design for selecting the valve, engineering contractor will try to select the valve with the seal capability. But having a seal capability for the valve does not guarantee that it will work as per the intent. Often there is a different supplier for each component because the valve, actuator or positioner plus an integrator. An integrator means the company which assembles the valve with the actuator. To put it all together, the integrator is the one who is doing the assembly of the valve with actuator with different pneumatic components like instrument, air regulator, solenoid valve, booster release, volume boosters, like that. So the integrator is the one is getting valve from one manufacturer, actuator from a different manufacturer, and the pneumatic components and the tubing from another manufacturers, and is making the assembly together and supplying to the end user. So these components have been procured from different suppliers and assembled at one facility, at an integrated facility. So there could be some chances that even though the valves having certification, so this there is a possibility of getting into an error, but it's not that every time it can happen, but the probability is high. So it is always better to go with one manufacturer who is doing the valve and actuator. Either they are manufacturing the actuator by themselves or getting it from a reputed manufacturer and assembling it, testing and selling to the end user. Integrator is one who is getting the materials from different manufacturers and assembling it together. They don't take the complete responsibility whenever any failure is happening. So these are all the few concerns. So whenever we do the engineering, whenever the SIS-related valves is being procured, proper care has to be taken. Thank you. I am going to make a presentation on safety system, and this topic will be on De-Energize to safe state. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. Basics of SIS De-Energize state. What is De-Energize state in safety instrumented system? In safety instrumented system, De-Energize to safe loop, known as fail-safe system. Alternately, this is known as De-Energize to trip. De-Energize to safe state means during plant normal condition, electrical current flows through the instrument loop. That is, when the plants are in normal operating condition and the valves, which is known as safety instrumented system valves, that are isolating a process or an equipment or a vessel, will be in open position using the solenoid valve. During any trip or shutdown happens due to hazardous conditions or manual shutdown, power to the loop will be disconnected and thereby loop gets de-energized. Example for de-energize to safe in safety instrumented system applications is the final control element on-off valve actuator wherein solenoid valve power will be removed and instrument air gets vented to the atmosphere. This is a generic example wherein for the safety instrumented system applications in industries, there are many on-off valves being used across the plant for different applications. A solenoid valve is the one which is controlling the air to open and close the valve. So this will be discussed in detail in the following slides. What is the function of the cis solenoid valve? A de-energized to trip example of a solenoid with a manual reset is shown on the following slide with a commonly used symbol for a 3x2 NC solenoid. NC stands for normally closed. The right side of diagram shows an alternative 3x2 solenoid symbol commonly used with spool type solenoids. This is one type of solenoid which is being used commonly across the industries. Solenoid valves are among the most common components in safety systems. They are commonly used to vent instrument air, so valve actuator moves the associated valve to a safe state. Most are relatively simple electromechanical devices with mature, proven designs that can provide reliable services in safety instrumented system or safety interlock systems. Advances in technology have also brought more smart devices that can provide solenoid functionality but with enhanced testing and communication capability. Of late, the modern devices have come with more inbuilt intelligent features which can detect the solenoid operations and healthiness and any other internal failures on the solenoid as well as in the actuator and the pneumatic components. So those are fitted with smart devices. So we are going to see the detailed example what is briefed in the earlier slide. This is a cis valve, safety instrumented system valve. It's an on-off valve. FC stands for fail close position. Whenever there is no air or no power, valve goes to the close position. So which is mentioned over here. And the valve is being operated through a cis logic solver. We had seen about the logic solvers in the previous presentations, earlier presentations. So this is one which is doing the action, that is which is giving the electrical power output to the solenoid valve to open and close based on the conditions, based on the process conditions, by detecting the respective vessels, pressure high or temperature high or flow high, like that. From the cis sensors, the logic solver is doing the mathematical computation inside and then sending an output through the relevant output models in the logic solver. So here in this case, the logic solver output is going to the solenoid valve, and this is a 3x2 solenoid valve which was mentioned in the earlier slide. So the main valve, which is this part, is known as an actuator. So this actuator is being driven using the instrument air. Line shows the instrument air being sent into the actuator through the solenoid valve. So under normal operating conditions, when the valve, when the solenoid power is energized during the plant normal condition, and the solenoid power is energized, the instrument air goes into the valve actuator body to keep it in open position. So whenever any process condition arises as hazard condition causing the trip or moving the system to the safe state, that time the solenoid valve gets de-energized and then the instrument air gets connected to the exhaust port. That means the pressure inside the actuator body gets vented into the atmosphere and actuator loses its power to hold the valve in open position, and by means of spring tension, the valve goes to the closed position. This is the general working principle of an pneumatically operated actuator valve. So, according to the process requirement, according to the process conditions, the sys logic solver will act and then cut the power to the solenoid valve, making it to move to the de-energized position. And these positions are known as the spool. Internally, the spools will be connected based on this representation. And at one position, the instrument air will directly go into the actuator body to keep it in open position. And whenever the power is disconnected, the spool moves internally to the exhaust port, thereby venting the entire instrument air from the actuator body to the atmosphere to make the valve to the closed position. So this is the general operating principle of a safety instrumented system on-off-valves. This is applicable for all on-off valves, but widely used in the safety instrumented system applications. So de-energize to safe state, what are the advantages? The reason for de-energize to safe mode to be implemented in SIS to ensure that systems are in safer and healthy state. In previous slide case, by closing the main valve when either one of the following condition occurs. So I told about this point earlier. Whenever there is an unintended instrument cable disconnection, either pressure switch or solenoid valve, there are pressure switches which is working as a sensor, and the solenoid valve is the final control element output. So in any one of this, if there is a cable disconnection, thereby it loses the signal going to the logic solver, and the output to the solenoid valve will get disconnected. That means the power may be removed in case of any cable disconnection in any one of this one. So in those conditions, to make the system the healthy state, the valve will move to the closed position. And electrical power wire cut. Similarly, there is any power connection going to the solenoid valve gets cut, the valve has to move to the safe position. And system module fault and doesn't supply power to the solenoid valve, to the field solenoid valve. If there is any power going to the solenoid valve gets disconnected due to the failure of the output module, it is an electronic module. During that time also, the valve has to go to the safe position, which is a failed closed position that we saw in an earlier example. Similarly, there is an instrument air failure due to compressor drip or any blocking in the instrument air line. In those conditions also, the valve has to move to the safe position to ensure that the plants are operating safely. These are the basic requirements for the de-energized to safe state. So if it is an energized, if it requires an energized condition, when there is any cable cut, the power cannot reach the solenoid valve to do the action to keep the valve open. So these are the basic advantages of the de-energized to safe state. Thank you. I am going to make a presentation on safety system. This topic will be on energized to safe state. This video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. Basics of safety instrumented system energized state. What is energized state? In safety instrumented system, energized to safe loop, which is alternately known as energized to trip. Energized to safe state means during plant normal condition, no electrical current flows through the instrument loop. For example, solenoid valve in SIS valve or de-latch valve. Under the plant normal operating condition, no current flows through the solenoid valve. In energized to safe loop, electrical current flows through the instrument loop, example solenoid valve, during plant trip condition. Loop will be energized during plant upset, trip or shutdown condition. Whenever there is a plant trip occurs due to any hazardous event happening, that time the power goes through the solenoid valve to make it open, to make the main valve open. Okay, energized to safe state for De-Energize valve, typical. Here we are seeing a typical example of a De-Energize valve which is used in the fire protection system. To clearly understand the working principle of energized to safe state, refer picture of a simple loop. The example is about a De-Energize valve used in fire protection system. It consists of a push button here and solenoid valve control a De-Energize valve. So here this is the main valve which is known as a De-Energize valve, and here the FO stands for fail open condition, and this is operated through the solenoid valve, and the De-Energize valve is the one used in the fire protection applications. So it receives water from a fire water ring header across the plant, and whenever these valves are situated at many plant locations, plant areas, near the pumps, near the vessels and all, wherever there is a possibility of any fire happening, to quench the fire, these valves will be operated. And this is what mentions, goes to the coverage area. The outlet of this valve goes to the coverage area. So the De-Energize valve is the one mainly being used for the fire protection across the industries, across the plants. Okay, here in this case, during plant normal condition, whenever there is no fire, the push button contact is at open position, so that no current flows within the loop. The push button is at open position, so no current passes through it and goes to the solenoid to make it open. Similarly, the solenoid valve of a De-Energize valve is not being energized by electrical power, because once the push button is pressed, only the current goes through the solenoid valve. So whenever, as long as the push button is at open position, no power is going to the solenoid valve of the main De-Energize valve. So this condition drives the De-Energize valve to close position, prevents the fire water from ring main passing through the De-Energize valve. So the valves are in closed position, thereby the fire water does not pass through the main De-Energize valve. If there is a fire in that area or zone, the operator receives an alarm through fire protection system and activate the push button and changes state to close position and enables electrical current flows through the loop. In the earlier slide, we saw the push button is in open position during the normal condition, but whenever there is a fire, the operator is pushing the push button. There could be some automated actions also through the fire protection system. So during that condition, the current flows through the push button and flows through the solenoid valve also. This current will signal the control system and execute the predetermined action, that is to open De-Energize valve by energizing the solenoid valve. Thereby, water flow through the De-Energize valve to extinguish the fire, which is available in the fire water header. The valve gets admitted through the De-Energize valve and goes to the respective area and zones. Thereby, it is helping to extinguish the fire in case of any. Note, this switching principle is also commonly applied for ESD push button for shutting down a plant. In the plants, due to any fire or any other emergency situations, there could be a requirement to operate a emergency shutdown push button for that area to get shut down, or that area to get isolated by shutting down the process. So those push buttons also have the normally open contact and used for a similar application, like whenever the push button is pressed, the current flows through it. Okay, what are the advantages of energized to safe state? To overcome mal-operation of final element, that is activation of a delay valve and the above example, due to instrument failure or unintended instrument cable disconnection. So this helps to this energized to safe state principle helps to overcome mal-operation of the final element. Unlike de-energized state to safe mode, energized to safe mode type of devices and systems does not have impact with only one failure on solenoid valve cable or system side fault. If there is a cable cut due to XYZ reasons, or any system side fault, that is the IO module, IO card is getting failed, in those conditions, as the power is not reaching to the solenoid valve during the normal operating conditions, it is not harmful. So in other case, whenever it is a de-energized state, the power is going to the solenoid valve. So whenever there is a cable cut or IO cord failure, it leads to the closing of the valve and leads to a closing of the main valve, which is not the case in this energized safe state. As long as the power is not flowing through the loop, failure of cord does not have impact. But whereas there shall be some system side fault indications which will require the operator and maintenance engineer's attention to go and attend to the fault and refix the issue or refix the failed module in case of any. So these are all the advantages for energized to safe state. Okay, thank you. I am going to make a presentation on safety system. This topic will be on redundancy. This video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. Basics of redundancy in safety instrumented system. What is redundancy in SIS? In safety instrumented system, redundancy refers to the duplication of protective systems. If the failure of any sensor is of concern, that is a nuisance strip or a fail to function failure, then redundant or multiple sensors may be used. Ideally, the possibility of two sensors failing at the same time should be very remote. The chances of two sensors used in the same applications may not fail at the same time. Redundancy is used primarily to improve reliability or availability. Either to improve the reliability or availability, the redundancy is being used. Again, this is being selected based on the cell calculations and all in the safety applications. The existence of one or more sensors means for performing a required function or for representing information. Representing information comes into picture in case of control loop. There may be multiple transmitters to do the measurement and provide information. Redundant sensor configurations. Redundant safety systems are commonly used in the process industry to respond to hazardous events. In redundant systems composed of identical units, common cause failures, CCF, also known as CCF, can significantly influence the system performance with regards to reliability and safety. However, their impact has been overlooked due to the inherent complexity of modeling common cause induced failures. So this is the redundant configuration of three sensors used in application. All the three sensors are identical, measure the same process parameter, and then the signal is being given to the logic solver. In the logic solver, there is some voting function is there, which is doing an averaging, or it selects the maximum, or it selects the minimum. Most probably, it does the mid of three value, does the required calculations, and gives an output according to the process conditions. Sys sensors redundancy. This is a study by the Emerson Systems, who are the largest manufacturers of the different types of sensors used in the safety instrumentation system application as well as in the process measurements. So Emerson System shows failure modes, effects, and diagnostics analysis from Exida. Exida is an agency who are doing the certification for the transmitters and final elements. So this is, they are getting an Exida certification for 3051S pressure transmitter. This is one series of transmitter being used in the safety instrumentation system application. Statistically, it has a dangerous undetected failure rate, which is known as lambda du, of approximately 0.01 per year. This means 1 in 100 devices in this application will experience a dangerous covert failure every year. 1 out of every 100 devices may have the possibility of going for a dangerous failure. Redundancy can reduce these risks if the failures are independent, that is, no common cause, and if the two transmitters are set as 1 out of 2, which means that the process keeps operating only if both the transmitters say conditions are safe. In 1 out of 2, the risk goes from 0.01 per year to 0.01 to the power of 2, or 0.0001, which is 1 in 10,000 devices that statistically may failure dangerously every year, because we have increased the number of sensors from 1 to 2, which is helping to increase the probability of failure. This increased risk reduction is by doubling of a spurious or unnecessary trip risk, since either transmitter can cause the spurious trip condition. Therefore, 1 out of 2 improves safety but reduces availability. Why we are telling reduces availability? In case of any one transmitter failure, the system cannot perform. So it requires both the transmitters to be in healthy state. Sys sensors redundancy, we'll discuss this with the 2 out of 2 or 2 out of 3 combinations. In a 2 out of 2 arrangement, keep operating if either transmitter says safe. 2 out of 2 means either one of this is in safe condition, system will continue to work. The risk of a dangerous failure doubles by adding the second transmitter, but availability improves. In this case, by adding the second transmitter, the risk of dangerous failure is getting doubled, whereas availability is improving because any one transmitter can support for the functionality of the plant. In a 2 out of 3 arrangement, safety and availability both improve, whereas 3 transmitters and the system is designed to operate in 2 out of 3 combination, both the safety and availability reliability is improving. Common contributors to risk may include, for pressure transmitters, the impulse line plugging. This is one of the common cause failure. Or in flow applications, orifice plate misalignment or damage. Whenever there is a damage in an orifice plate, it gives a wrong reading and wrong flow measurement. For temperature measurement, coating, electrical noise. There could be some coating due to the process, due to the chemicals used in the process, which may impact the temperature measurement, or electrical noise whenever the signal temperature signal is being transmitted, because mostly they are coming as a very low power signal, and whenever there is an electrical noise due to an adjacent power cable or any other interference, the temperature signals may affect. For level measurements, the process or fill fluid density changes. For the level measurement, the fill fluid, whenever it is used as with the capillary type of arrangement, the fill fluid density is a very critical parameter. Due to ambient conditions, it may vary and it may give a wrong measurement. Material compatibility and environment condition. This is common for all the type of transmitters, type of measurements, and extreme pressure and temperatures in the plant environment. This is also common. And installation or maintenance errors. These are the common contributors to risk, which may impact the measurement as well as the safety applications. So, how to improve SIS sensors redundancy? Analyze common cause effects before adding redundancy. So, as we discussed in the previous slide, plugging of the impulse line, if it is going to be a common line, it may impact both the transmitters. So, in this case, they need to go in for two independent impulse lines. So, like that, based on the applicability, based on the requirement and process conditions, design has to be improved. And recommended to use shorter, wider impulse lines. The impulse lines has to be required size in diameter. Otherwise, there could be chances of plugging inside the impulse line, and the process may not reach the sensor part to give you a proper indication, to give you a proper reading. Select stronger and reliable devices. The type of devices being used in the SIS applications has to be more rugged and reliable one to give you a proper measurement and apply the safety requirements. Use stronger materials. Materials used for the construction of the sensors, sensor body, everything has to be strong. Look for ways to inspect, test for common cause, like a common line, common impulse line plugging, and the single orifice plate being used for multiple sensors measurement. Those common cause creating devices has to be inspected for it, the healthiness. Apply diverse technologies, for example, using vortex or Coriolis to back up a DP flow meter, or radar to back up a DP level meter. This is vortex or Coriolis meters or the flow meters used as an inline instrument. This is being commonly used in safety applications as well. So, instead of going for a DP type of measurement for flow, we can go with the vortex or Coriolis type of measurement. One application in one process requirement measurement, we can go with one DP flow meter and second one as a Coriolis flow meter, or we can go with one DP flow meter and second one as a vortex flow meter, so that it has two different diverse technologies, so the failure of both cannot happen at the same time. These are the ways to improve the redundancy. And similarly, in the level applications, there are DP type of level measurement and another one is the radar type of measurement. We can go in for two different technologies to improve the safety and reliability. Use associated diagnostics like hot diagnostics. These diagnostics are automatic and put the transmitter in fail-safe mode if and when a failure is detected. This hot diagnostics can do the internal self-diagnostics of the sensor's healthiness, and they can put the transmitter in fail-safe mode in case of any internal fault arising on the sensor body or impulse line choking or some other reasons. So, these are all the multiple ways to improve the healthiness of the safety instrumented system whenever the sensors used in the redundancy applications. So, the type of instrument, type of measurement and the technology has to be used suitably to have the continuous availability of the safety instrumented system sensors and have the high reliability. Thank you. Hello everyone, I am going to make a presentation on safety system, and this topic will be on voting system. This video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. Okay, we'll understand about the basics of voting system in SIS. One of the key design parameters in safety instrumented system design is the architecture or voting arrangements of the various subsystems that comprise of a safety instrumented function. The architecture or voting arrangement is essentially the use of redundant pieces of equipment for the purpose of creating the ability to tolerate a failure of one component and still have the SIF perform its actions. Meaning, we wanted to have the SIF, safety instrumented function, performing at all times, as well as we wanted to keep some redundancy, some kind of availability in case of one instrument failure, one valve failure, the other one should take over. That is why during the design stage, it is decided and design engineered carefully to have a 1 out of 2 or 2 out of 3 like that different type of voting systems. This is applicable for all the 3 main components of the safety instrumented function, which is sensor, logic solver and final control elements. Okay. Selection of an appropriate voting arrangement will consider the failure modes of SIS equipment, the level of safety that must be achieved, and the rate of spurious failures and the associated consequences. It may be financial or potential damage to the equipment, etc. Whenever there is any trip going to happen, that may cause a financial damage to the property, as well as the sales may be down or equipment may get damaged. Eventually, everything will result into financial loss for the company. We are going to discuss about the different voting systems in SIS. In the process industry, SIS design, there are several common voting arrangements. For the purposes of this discussion, we will focus on the sensor subsystem. But the same discussion will also apply to the logic solver and final element subsystems. As you know, these are the different subsystems comprises of a complete safety instrumented system, and whenever it is performing a particular function, it is known as safety instrumented function. SIF architecture is decided by the failure tolerances of its components. It may be a sensor, it may be a final element, it may be a solenoid valve in the final element, it may be a sensor failure or any instrument card failure or electronic card failure in the PLC, everything. It may reach still higher level using redundancy. Whenever the redundancy is there, still will reach the higher level. The number of instruments will depend on the reliability of each component defined in its FMEDA. This is known as failure modes, effects and diagnostic analysis. These are the terminologies that we will understand when you go into the respective detailed training on the safety instrumented system. The 3 architecture are simplex voting or 1 out of 1, duplex or voting 1 out of 2 or 2 out of 2, triplex or voting 2 out of 3. These are the different common architecture which is used in the industry. Voting system in SIS. There are 2 parts to the voting arrangement description. We are telling about 1 out of 1, 1 out of 2, 2 out of 2 and all, we get confused. So we need to understand what is first number and what is the second number. A first number is a number of devices that must vote to cause a trip for the trip to occur. See, 1 out of 2 means it is one instrument has to failure out of 2 instruments. Okay. The second number is the total number of devices. Thus, in a 2 out of 2 voting arrangement, 2 devices must vote to trip out of a total of 2 devices for the shutdown action to be taken. There are 2 instruments available for the shutdown action. Both must go for the tripping. That is known as 2 out of 2 in this example. Okay, now we will go over the briefs of 1 out of 1, 1 out of 2 and all. Okay, simplex or voting 1 out of 1. The voting principle 1 out of 1 involves a single channel system and is normally designed for lower level of safety applications. Immediately results in the loss of safety function or process closure. See, in this example, we are seeing only one valve and one sensor. This is indicated as a sensor, switch or transmitter, which is connected to the PLC as an input into the input card of this PLC. And whenever there is a high level indication or high temperature or low flow or any process condition according to the design, it happens. It gives an input to the PLC and PLC processes the logic according to the engineered programming and then gives a command signal to the final control elements. This is a ESD, emergency shutdown system valve. We know, and from our earlier discussions, these valves are operated through a solenoid valve. So here what is indicated is air supply of this solenoid valve, which is controlling the operation of this emergency shutdown valve. So in case of simplex or voting 1 out of 1, this is one transmitter and one final element. So this is again, the transmitter is only one and final element also only one. So this is only doing the safety function in our example as well as in the actual process. So one instrument has to work or indicate and give the signal to the PLC to take the safety function, to make the safety function to work. So we will discuss about the 1 out of 2 duplex or voting 1 out of 2 or 2 out of 2. Okay, the voting principle of 1 out of 2 was developed to improve the performance of safety integrity of the system based on 1 out of 1. If a failure occurs in a channel, the other is still capable of developing a safety function. Unfortunately, such concept does not improve the rate of false trips. Even see here we are seeing 2 sensors, and in this case the PLC is acting and working on 2 different independent valves. So this is known as 1 out of 2 or 2 out of 2 also can be done during the engineering as per the requirement, process requirement and LOPA study and all. Okay, even worse, the probability of a false trip is almost doubled. Hence, this is considered to be a better design than 1 out of 1. Okay, 1 out of 2 is always better because there is a second transmitter or second valve to protect the equipment. In this 1 out of 2 discussion, so there are 2 transmitters, safety transmitters, which is connected to a PLC, and the PLC is performing the logical calculations and giving the output to 2 independent valves. So here in this case it is known as 1 out of 2. Either one sensor going high and closure of one valve can cause the equipment or the particular process zone to make a shutdown. 2 out of 2. There are 2 configurations. One is 1 out of 2 and 2 out of 2. In this case, both has to work. So here we will discuss about it. The main disadvantages for a single safety system, which is 1 out of 1, is the only one failure will immediately result to a trip because there is no chance. Only one instrument is working when it is indicating a trip level signal like a high temperature or high flow or high pressure, such conditions, it directly gives a signal to the safety PLC, and PLC gives a command to the valve to close. This is a 1 out of 1. But the duplication of channels in a 2 out of 2 application significantly reduces the probability of a false trip, as both channels have to fail in order the system is placed under shutdown. On the other side, the system has the disadvantage that the probability of failure on demand is twice as higher than that of a single channel. So in this case, in the 2 out of 2 configuration, the process pipe will be coming and getting distributed through valves, and the output will be a common input line coming and going to the first valve. Similarly, it parallelly goes to second valve and goes to the process. So 2 out of 2 means both has to close. Then only the process will get disturbed and it will go for a safety trip. Okay, another kind of voting which is considered to be most better, and but it has a more requirement or not. It has a more number of instruments. See, this is 2 out of 3 or triplex voting. Triplex or voting 2 out of 3. In that voting, there are 3 channels, 2 requiring being okay in order to operate and comply with the safety functions. Here you see there are 3 instruments, 3 transmitters. They are connected to the safety PLC and they are connected to the valves. So in this case, what we are looking is only the transmitter part. As told in the discussions earlier, we are concentrating only on the transmitter part about the transmitter subsystem. This is a logic server subsystem and this is a final element subsystem. So our discussion is on the sensor subsystem. Here we are seeing 3 different transmitters. They are connected to the safety PLC, and the safety PLC is doing the logical operations and giving a signal output to the final control elements, valves. So the 2 out of 3 voting principle is better applied when there is a complete physical separation of microprocessors. So the processors also need to be triplex or can be duplex. For the better, as a better engineering practice, it is better to go for a triplex processors. I mean triplex CPU based PLC, which is a triple model redundant. However, that requires they are located in 3 different modules. Although the most recent system have a higher diagnosis level, safety systems based on 2 out of 3 voting still keep the disadvantage of probability of failure on demand, which is approximately 3 times higher than those of the 1 out of 2 based system. See here, the probability of failure on demand on the 2 out of 3 goes higher because this is one disadvantage, and that's why it is requiring a detailed engineering to do the design. So in overall composition, 2 out of 3 is a better design, but on the economics part and for the cost of installation and maintenance and all, because here in this case all the 3 transmitters installation is going to incur a cost, and in future for the maintenance they need to work on the 3 transmitters as a proof testing and routine maintenance, as well as if it is going to be in the valves also, the valves need to be dropped and checked for the zero leakage as per the seat leakage requirements and all. The maintenance cost also going to be high. But on the safety part, there are 2 parts. In the safety part, if you are looking at, and the design requires to use a 2 out of 3 as per the calculations, in the cell calculations, it is ideal to go for a 2 out of 3. On the economics part, it is a bit disadvantage. Okay. So here we are going to see a table about the spurious trip rate and probability of failure on demand, as we discussed briefly in the previous slides. So we need to understand how mathematically how the number looks like, because all this you cannot understand from this presentation only. This required a specific detailed training on the safety instrumented system to get a certification from the authorizing agencies. Okay, this is for our basic understanding about the safety instrumented system. Therefore, the table below, the 2 out of 3 systems has good performance in comparison with a simplex 1 out of 1 voting arrangement with respect to safety and nuisance strip avoidance. Even so, the PFD of 2 out of 3 voting system is 3 times higher than the PFD of a 1 out of 2 system, and the spurious strip rate is 3 times higher than a 2 out of 2 system, while here we see 1 out of 2, it is a spurious strip rate is 9 to the power of e power minus 6. In 2 out of 2, this is 2 to the power of e minus 9. And in the 2 out of 3, it is 8.7 to the power of e minus 9. So this is 3 times higher. I mean, the probability of failure on demand is 3 times higher. From 1.4, 1.6, it goes to 4.3. So, while the 2 out of 3 system is the most complex and costly, it is still popular when higher sills like sill 2, sill 3 need to be achieved, but the plant cannot tolerate the high spurious strip rate associated with 1 out of 2 voting. With 1 out of 2 voting, the higher strip rate, because 1 out of 2 is the safety as well as economics part, this is a better configuration. But the plant cannot tolerate the high spurious strip rate associated with the 1 out of 2 voting. See here, the spurious strip rate for the 1 out of 2 system is very high compared to the 2 out of 2 systems. In this configuration, any one transmitter going to high or going to low as per the LOPA study and SIL study, so that will call for a protection, that will call for a action, safety function, and protect the equipment by tripping the equipment. But the spurious strip rate looks to be on the higher side. So the design has to be considered considering many factors like probability failure on demand, spurious strip rate, and the constructional features of the equipment, plant and equipment, and the sensors, as well as the maintenance in future. So all these things needs a detailed engineering study before implementation. Okay, thanks for your understanding. Hello everyone, I am going to make a presentation on safety system, and this topic will be on safety architecture. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. Safety architecture. What is safety architecture in SIS? A SIS is engineered to perform specific control functions to fail safe or maintain safe operation of a process when an unacceptable or dangerous conditions occur. As we have seen in the earlier presentations, and safety system is not always in action, it's always in silent mode, but it is ready to perform whenever any hazardous condition arises and any demand arises for the system to function, to take to preventive action to overcome from any hazards. The safety system comes into picture. Safety instrumented system must be independent from all other control systems that control the same equipment in order to ensure SIS functionality is not compromised. In the normal plant, you can see the BPCS system is the one controlling the normal process of the plant. The safety system is sitting in the next layer. We have seen about the independent protection layers and all in earlier presentations. So this comes into picture whenever any hazardous conditions arises. So meaning that it is acting independently and the equipment protection is ensured. SIS is composed of control elements including sensors, logic solvers, and final control elements. These are the 3 major components. The specific control functions performed by an SIS is called safety instrumented function. We have seen about the LOPA in earlier presentations. In the LOPA, there are many scenarios being worked out by the process safety experts, plant experts during the initial engineering phase and design phase. They find out and tabulate different type of hazards that can happen across the plant in the process areas. And for each of the scenario, for example, if it is a boiler, the fuel gas or fuel oil entering into the boiler can get into high pressure and create a fire inside the boiler, or it may be getting external to the boiler furnace also. And this is one scenario. Likewise, it can go to low pressure also or low flow also. This will be another scenario for the same boiler, for the same equipment. There may be multiple scenarios as well, and a set of control valves and automated on-off valves which are in a particular gas line or pipeline. They may be functioning to make the protection against any hazard. This is why it is called a safety instrumented system. In SIF, the architecture is decided by the failure tolerance of its components. It may reach a higher SIL level during redundancy. We have seen about the redundancy and voting principle in the earlier presentations. There are different combinations by which the redundancy can be achieved, and it is all depending upon the safety integrity level. Okay, these are all also different types of modules, the control modules in the logic solver, and the final element. This is one type of valve. This is known as butterfly valve, and this is a sensor which is taking the process measurement. It can be a flow, pressure, or temperature and all. We'll discuss about it here. Sensor. What is sensor? It is an instrument that measures process conditions. Sensor devices that measure flow, temperature, pressure, liquid level, etc. Also, not only this is the one sensor what we are talking. Not only this, analytical instruments such as gas chromatographs, oxygen, CO2 analysis, gas detectors also can be a part of the safe instrument system sensor. And also flame detectors in boiler or furnace, and electrical power or current sensors are also used as a sensor. So these are all the electrical components. They are sitting in the switch gear and giving the signal about the power or electric current going into the motor, turbine, or any other equipment like extruder. So many equipments in the plant. So likewise, not only the pressure flow and all, the gas chromatographs in the process industries where the many chemicals are being split to do different processes inside the plant. There may be the components required to see the gas composition. These are known as gas chromatographs. This is widely used in the refineries as well as in petrochemical plants. Okay, logic solver. It is an intelligent microprocessor-based controller device. This is the one what we are talking. That performs logic functions to convert the sensor input into an action command to be carried out by the final element. Here, this is the logic solver what we are talking of. It is getting an information or process condition through the sensor. This is the one installed in the field, and this may be mostly in the control room, centralized control room, in an air-conditioned atmosphere, and dust-free and weatherproof shelter. And this is the final. Again, this will be in the process. So here I can show an example. Say, for example, this is one reactor which is having a temperature measurement, pressure measurement, and it is having both systems shown with both systems here, because here if you see this pressure transmitter is going to the safety instrumented system, and the second pressure transmitter, it is connected to the basic process control system. In the normal plant operation, the basic process control system is the one controlling the process. So this operates the valve, control valve, VS level control valve, and maintains the level inside the vessel. In case the control valve gets failed, or any card from the control process control system get failed, there could be a chance that the control valve may not be able to do the control action and keep on adding the fluid. And when the fluid get excess inside the vessel, thereby the pressure also gets excess. And the pressure sensor here in the safety system senses and gives a signal into the safety instrument system, and thereby the safety instrument system, the logics built inside the logic solver will do the necessary action and take and give the command to close this shutdown valve. So the shutdown valve will get shut so that the liquid entry into the this reactor will get minimized or will get controlled. So whenever this is coming into line, if you see, this is all this pressure transmitter, this safety instrument system, logic solver, and then the valve, these are all acting independently. That's why it's known as independent protection layer. Okay, and final element. This is an equipment which performs the physical action commanded by the logic solver. Final element devices may be control valves, like earlier said, can be a motor or switch gear. The motor operation also need to be stopped. For example, one pump is supplying fluid for this particular tank, whatever we are talking of. That pump needs to be stopped in order to cut the liquid to the tank. So for the motor, there are switch gears which is having the breakers and other components inside that needs to be controlled and switched off. This can also be part of the safety instrumental system. So this slide we have explained about it earlier. Sensor is there and it is going to the logic solver, the signal, and signal further the processor signal goes to the final element to take an action to shut off the process. This is also depicted in a different way. This is a sensor giving signal to the controller, which is logic solver, and it is going, the output from the controller is going to the valve, which is in this case it's a butterfly valve. So this is depicted in a different way over here. So this is a planned process. You can just assume this is a planned process which is having different sensors and different actuators. So the BPCS stands for Basic Process Control System. This control and recovery of the process due to non-critical fault. Actually, in the normal operation, the plant is under control by the BPCS. So in case of any alarm, like if after the sensor, there could be an alarm also. Suppose it is going to measure 0 to 10 meters in a vessel. At 7.5 meters, it will give an high alarm, so that it takes a preventive measure in order to not exit the level, touch the limit. So it will give an alarm. So further to the alarm, the operator, sometimes it may be required the operator to take an action to control our manual valve, to close a manual valve. Further to it, if there is a failure or the manual valve does not work properly due to any reason, XYZ reasons, then it goes to the next level switch, next level transmitter, whatever it is, which can give you a signal. It will be a safety sensors, and this can give you a signal to the safety instrumented system. And by that, the safety instrumented system, it has a programmed logic built inside during the engineering stage of the project. So this will give a command to close the safety actuator. So this is a hazardous, see it's shown in red. So this is a hazardous situation wherein the safety instrumented system is acting to close the actuator. So that's why degeneration of process in a controlled way due to a critical fault. Critical fault means already the level has reached to the very high level. Then the level, the process, what we are talking in our example, reached to the very high level. So in order to prevent the equipment, here it is pressure, it can be level also. So in order to prevent the process to a safe and to going from any further hazard and go to the safe state, this safety instrumented system will act and then close the valve. Okay, this is like a P&ID, a small part of P&ID of the project, wherein we explained about it earlier, the actions. Okay, we are seeing in a different pictorial way only. All are referring to the same type of reactor, which is having a pressure measurement. PT is pressure transmitter, TT transfer temperature transmitter, again another TT transfer temperature transmitter. It is going to the BPCS, it is basic process control system, and it is going to the input output card. From the output card, the signal is going back to the control valve to do the pressure control of this process. And similarly, we have another set of pressure transmitter going, and temperature transmitter, which is going to the input-output model of the safety instrument system. This is a different system, altogether different processor, because the safety instrument system requires a very high level of testing, proofing, everything. So the processor itself may be different, should be different, which is having a high capacity, high processing speed and other capacity. Unlike it could be a redundant processor. Here it is just shown as a simple way in a simple like a single processor, but it could be a redundant processor or triple modular redundant. There will be three processors together doing the similar functions. In case one fails, the second processor takes over. In case two fails, the third one, which is take over, and it will still control the. It is still able to take the action, but it is not safe to run with a single processor in case of triple modular redundant. So there are other safety requirements for the functionality of the logic solver. Okay. And this will in this case, this transmitters will give a signal to the safety instrumented system, and thereby after performing the logic, the output will go to the valves to shut off the process. Okay, again this is in a different way. Here only we see all the components which are shown in different presentation slides are almost similar, only they are showing in a different way for the better understanding of the students. Again, this is a process piping wherein the sensor is doing the pressure measurement sensing, and it is going to the card, the IO card. From the IO card, the logic solver processor will be doing the processing function and give a command to close the close the valve. Okay. So far, we have been seeing about the sensor, logic solver, and actuator, this final control element. Actually, this is a small part of the sub part of the process. And as a whole, if you see, the plant will have different numbers of, because it may be 1,000, maybe in 1,000, based on the plant size and the capacity and the like a refining unit, crude unit, so many units will be there inside the big plants. There will be so many valves and sensors. So they may be connected in a different pattern and giving signal to the basic process control system or distributed control system, also distributed control system. And they are connected to the, because whatever the process is doing here, they need to get to know the operations. The human interface station is the one where the operators is sitting in a control room and they watch the process how it is behaving, and they control and do any action. Normally the process is running in an automated way, but if there is any abnormality happening, the process may go to the high level or low level or high temperature as per the design state. So whenever there is such cases, they need to take an action. So that's why this human interface station is the one where the operators are sitting and doing the control. And engineering station, here the engineers, plant automation engineers, instrumentation engineers who are responsible for the particular plant, they will be doing the engineering functions. They will be doing the building the logics, and sometimes it may be required to change the logics or bypass the logics for operating an equipment or something like this. So the engineering station people, engineers, maintenance engineers and maintenance supervisors, technicians, they will be sitting and doing the engineering activities using the engineering station. And plant asset management, this is for gathering the very critical parameters from the plant and then reporting to the higher level management. Or this is okay, plant asset management is the one which is having the plant asset data and giving the performance reports about the different process, different equipments. Maybe it could be like all high capacity equipments like boiler, some critical vessels like this, etc. And plant information management, this is again an important server based machine, and it is having multiple clients in the different head of the departments like plant VP or plant directors offices, and they will be getting the high level parameters like what is the production as on date, what is the incoming supply from an adjacent plant, what is the recovery happened, on how much is the seawater consumed, how much is the cooling water consumed, what is the air consumption, like that different critical parameters they need to know. So these are all collected using the plant information management server and reported to the high level management. Similar to this DCS control station, DCS control cards and other things, we are having safety instrumented system, processors, sensors, on-off valves, etc. Okay, and all of them are connected through a plant control network. This is known as plant control network. We can see it's more clearly in the next picture. Here, this is showing a more detailed and elaborate view of particular system. This is, I think, for the Yokogawa control system. Each manufacturers, they are having a different topology, a different naming architecture, but overall, if you see, the functionality will be almost similar. Only there may be some engineering changes from between one manufacturer to the other manufacturer. Here we are looking on a larger scale of detailed plant network by Yokogawa control system, and we are seeing all the sensors, valves, all connected. This is field bus is another technology. It will be like a single cable supporting about 8 instruments, and it's not like other normal transmitters. This is a different on different technology wherein the cable requirement will be minimized. And this is different one wherein the conventional cabling is there. For each piece of sensors, each piece of valves, there will be separate wiring, independent wiring going from the control room, right from the control room up to the instrument. So here we have the cards and all. It is connected to the I/O modules, and it is in turn connected to the control system. FCS stands for the field control station, and SCS stands for the safety control stations. This is for the plant BPCS control, and this is for the safety control. And again, this safety control also having different kinds of sensors, valves, etc. connected through input output modules to the respective safety control system sensor. And FIO stands for the field I/O. This is another type of I/O wherein just field inputs are being collected through a distributed input output card, which may be located in the plant area in a safe enclosure. This is known as NEMA, like that. Some different enclosures are there wherein the safety cards or control cards can be placed, and it will be maintained under a temperature, because in many plants in different locations, the high temperature, like in Asian region, the temperatures are normally high, maybe 40, 50 and above. And in colder places like in American continent, Canada and all, normally the temperatures used to lie in 15 degree, 20 degree, and sometime in the winter time, it goes to sub-zero temperatures. So the cords and other things need to be maintained in a constant temperature, like it may be functioning in a good manner between 15 to 50 degree. So they have to be maintained. Normally it is maintained in such a way, like conditioned environment. So if FIO means the field input output cards, it can be sitting in a plant area and then connected through cabling to the safety control system. Okay. And like we saw in the earlier slide, here it is human interface station is there for the operation action. And automation design suite, that engineering suite, SC engineering this is an engineering suite, engineering application, laptop or PC. And PRM is for the plant resource management. This doing scheduling and other different actions. And they are all networked and connected through an Ethernet cabling. Further, it can be connected to a plant information manager network to give a data to the higher level management. Okay, we have seen two different type of one brief architecture and one detailed architecture by the specific vendor. Okay, we will go through the topic. What is safety architecture in SIS? The number of pieces of equipment will depend on the reliability of each component defined in its FMEDA. FMEDA stands for failure modes, effect, and diagnostic analysis. As explained in an earlier presentation, these are all the detailed terminologies and which the students need to learn when they go into the detailed technical training course. As we are just doing an overall presentation, we are not getting into deep into the details. Okay, and the common voting principles in the SIS architecture are simplex voting or 1 out of 1, which we discussed in an earlier presentation, or duplex voting, which can be 1 out of 2 or 2 out of 2, and triplex voting, which is 2 out of 3. There will be, say, like we are seeing here, for an example, we are seeing only one sensor. In such case, if it is 1 out of 2 means it can be 2 sensors here. Like we are seeing 2 different sensors, right? This can be in a 1 out of 2 combination, because anyone showing the higher pressure can give a signal for the safety system controller to work. Okay, this is known as a voting terminology. And sometimes it may be 3 sensors, out of which 2, if it is going high, it can cause for a safe shutdown. Okay. And we'll go over the architectural design requirements. Safety system applications are designed to protect the plant and personnel from hazardous conditions and provide a rapid and coordinated operational response to emergency situations. Hence, they have to be engineered carefully. Time and again, we are looking into the criticality of the plant, because the plant is more important to do the production. Correct? That's why only people are getting jobs and getting salaries, etc. As well as the plant and personnel need to be protected. If there is any hazardous condition happening, because hydrocarbon based plants and all, they are prone for hazards. Anytime fire can catch up easily, and some equipments can failure may lead to production loss, etc. At any point of time, the management is considering the safety, should consider the safety of the personnel as well as the plant equipments. So that's why safety instrumentation systems are in place. Under this architecture, modern SIS systems takes into account to check the reliability of the entire safety loop, evaluate measurement system performance, and extend diagnostics beyond this device to provide process diagnostics. Meaning, the older systems were not much intelligent, and the newer system, which have been developed after 90s and 2000s, they are more intelligent, which can do the performance diagnostics and predict the failures, if any, in advance. Okay. Whenever the engineering takes place and the equipment order takes place, the respective engineer involved in the plant need to order the equipment as per the plant requirement. This architecture to take into account devices predicted lifespan and determine life cycle with maintenance notifications and device alerts as applicable to ensure this integrity stays stable longer. As we told, the integrity of the equipment is very important. So, the architecture, whenever it is being built, like 1 out of 2, 2 out of 3 and all, they are all arrived based on certain calculations. So, even after the calculations, the person who are involved in the design, not only one person, maybe a group of engineers, group of technical personnel, experts, they need to design in such a way that the integrity of the plant is ensured, safety integrity of the plant is ensured, and also the number of years the plant is going to be serving, number of years the equipment is going to be in service, that also need to be taken into account. Okay. Safety systems to meet required architectural requirements by approved manufacturers, because there are multiple manufacturers for the same product, but everyone cannot supply the safety system instruments. So there are certifying agencies, and those certified agencies only can give the approval for manufacturers. And after the manufacturer's products will be tested, they will be going for a rigorous testing. After that, the approval will be given. So the plant owners need to take and put the equipments which are having the approval. SIS system architecture to take a modern approach to increase safety integrity while improving the process availability. This is what the architecture should be made in such a way that they had to see the integrity of the plant always, and process availability, because they doesn't mean that put 4 transmitters, 5 transmitters and keep plant in running always. Same, we have to go for the required number of sensors and final limits, and the reliability and process availability all the times also need to be ensured. The logic solver certified to safety integrity level 3 shall use an electronic marshalling technology as far as possible to reduce maintenance costs. Because we saw in the earlier presentation, this is known as marshalling cabinets. This is shown in the network drawing, but it will be this will be a marshalling cabinet. So that has to be electronic. There are still levels, different still levels, and it is a still 3 or more. Still 3, it has to be in electronic marshalling. But it is being used in even still 1 applications as well. This is as a minimum requirement, design requirements being discussed. Better configurations enables to start hardware design earlier in the engineering process together with ASOP's completion. As some students would have gone through the earlier presentations, ASOP is for hazardous operability conditions. So whenever the plant is being built, hydrocarbon and related facilities are being built, or before that, prior to that, that study will be taken up. Hazardous operability study will be taken up, and then the different hazard conditions would be analyzed, based on which the LOPA, layer of protection analysis, will be developed, and the number of sensors, the safety integrity level, categorization, everything will be decided accordingly. So in the earlier stage, it has to be taken so that the hardware design can be done perfectly, so, along with the ASOP completion. So these are all the different requirements should be considered in the design stage for the better architectural arrangements of the safety intermediate system. Thank you for watching the video. Hello everyone, I am going to make a presentation on safety system, and this topic will be on sys overrides, bypasses, inhibits and MOS. This video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. What is sys override? An override is a mechanism which is applied to prevent the action of a control or protection device, example a sys transmitter. When associated with safeguarding systems, the application of such a device must be strictly controlled. In the normal scenario, all the sys transmitters, sys connected valves need to be in service. They have to be available because hazards can happen at any point of time. It is not a planned one, it is always an unplanned event. So all the transmitters, valves and associated sys instruments need to be in service. In case due to any requirement for the maintenance reasons or some other equipment in this line, the particular line needs to be isolated, for which the transmitter or valve need to be isolated, those things will be taken out of service, so for which the override being applied. So below points to be kept in mind with sys overrides. Overrides are managed and removed, normalized when they are no longer required. So they have to be carefully managed by a procedure. Overrides are only applied by competent personnels. Like anyone cannot make an override. There should be a competent personnel, or if the plant operators is doing this activity, this has to be informed to the shift supervisors, and if at all required to the shift manager. And depending on the type of override, it has to be approved by the operation manager as well. Overrides are not used to keep a system or equipment operational when the conditions are outside of the operating envelope or in an unsafe condition. See, normally these overrides are being applied whenever the plants are running in a safe mode. So if the particular area of the plant or some equipment goes out of the normal operating envelope, so in this condition we need to take care that the overrides should not be kept for quite long time. Overrides are handed over to the next shift if left in place during a shift change, because in the process industries, refineries, petrochemicals and other chemical industries. In the bigger plants, there are people working in the shift. It may be 8-hour shift, 12-hour shift, depending on the area and nature of the process and the geographical location as well. So override may be applied in a day shift. So the operators who are operating the plant is aware of the override which is being applied on a particular equipment or particular vessel. But if the next shift comes, the new operator who is coming in for the new shift may not be aware of this one. So the first shift operator who had applied the override need to inform the second shift operator to take care about this one, and as per the timeline and the maintenance procedures, this has to be restored back to the normalcy. So overrides are inspected and the status verified by supervision at a regular frequency. Like override is applied due to some reasons. It could be a failure of the instrument, it could be another equipment which is in the process need to be isolated for any leak or some supervision or inspection or any reason. So it has to be verified at a regular interval by the shift related person who are applying the override or who are in charge for the particular plant area, and as well as the maintenance personnel who are attending to the fault. Okay, and it has to be restored as soon as possible. Okay, what is sys bypass? In sys bypass, allow maintenance activities, calibration, proof testing or repair of a transmitter or other sensors to take place without a risk of a spurious trip. For safety's sake, the built-in functionality allows managing maintenance bypasses so that they are placed and removed at the right time. Bypass is another criteria wherein the calibration, proof testing or repair of a transmitter need to be done at a planned frequency. So, as we all know, the sys instruments are very critical for the plant and process. So, they need to be regularly tested at the desired frequency, proof test frequency or visual inspection. Visual inspection may not have any impact, only for the proof test of the valves which are inline and the transmitters. When there is a 1 out of 1 case, those transmitters may not be possible to get isolated. So in those cases, bypasses may be required for a shorter period of time to do the proof testing, to check the instrument healthiness and return back to the normal operation. So methods of better management of sys bypass. Maintenance bypass timeouts and reminders can be configured to alert when a bypass timeout is imminent. Again, as we know, the bypass needs to be kept for a shorter duration, maybe for example 4 hours or 8 hours. It has to be completed within a particular shift. As far as possible, it should not extend to the next shift. Okay. Alarms can be configured to annunciate to the operator when a maintenance bypass is active. Timeouts can be defined to either alert or remove bypasses automatically at a defined time, provided the sys logics are intact, restored to operating conditions for plant safety. Most of the time, there are some bypass arrangements in the HMI panel where the operators is doing the operations, like gas ductors in the plant can be isolated by the operations itself just by informing to the maintenance engineers or plant automation engineers. Whereas in some cases, operations cannot do it. They have to be done by the respective maintenance supervisors or the plant automation engineers or instrumentation engineers who are responsible for the plant area. So for them, they will be doing many tasks. The maintenance of bypass is one such activity. So whenever the time, they have to define a time, like 4 hours for transmitter maintenance. This is an example, or 8 hours to do the valve service maintenance and all. If it is not completed within that time, then alert has to be configured and it has to get alarmed in the panel so that the operators will be aware, and they may remind the maintenance personnel to go and finish that activity, go and finish the task and restore the sys bypass. So this is the better management so that the plant will be in safe conditions and it is ready anytime to take care of the hazards happening in case of the in case of any hazards happening in the plant area. What is inhibit? Insists bypass by any other name is just as dangerous, whether referred to as an inhibit, suppression, or forcing. The bypass of a safety system device or automated function nearly always means that this safeguard will no longer be able to provide the full degree of risk reduction and reliability it was specified to perform. As we all know, the sys functions are built in such a way that they take care of the any spurious trips happening across the plant due to some instrument's fault, due to actual operation reasons and those conditions. So that means it is taking care of the hazards which can occur anytime. That's why it's named, either it name it by inhibit, suppression, or whatever it is. So that has to be limited to a shorter time as far as possible. So what does it mean? The necessary spares also have to be kept in hand. Whenever there is any cord fault happening, a spare cord should be available in the stores always to go and replace immediately. Or there could be even a small, small fulcrum in a air regulator which may lead to leak and then may not be able to keep the valve in open position. So even such minute spares also need to be kept in stock in either in the maintenance department or with the stores. So continued safe operation of that facility will usually depend on timely implementation of compensating measures to provide the risk reduction that was lost through the act of bypassing. Bypassing means we are just overdoing, or bypassing means we are just doing those instrument as if it is in live. Ideally, the instrument may gone out of service due to the maintenance reasons. Just to overcome and keep the protection active, it will be bypassed as if the instrument is healthy. For example, it's a 0 to 10 kg pressure transmitter, and at 8.5 kg per square centimeter, and the trip is being programmed in the logic solver. The bypass will make in such a way that the pressure is reading around 6 kg on the particular piping or particular vessel. That is, it's not real actually. It's not a real process. Under the process, as per the operation sequence, operation phenomena, the pressure may get high sometime. So if it is not controlled uniformly, there could be a chance of pressure getting high and leading to the hazardous event. But to take care of the maintenance of the transmitter, we are just forcing by the logic as if the process is healthy, and then taking care of the maintenance. So the maintenance personnel need to complete the job quickly and then return back the instrument to the normal operating condition. The timing is the most critical factor over here. The predictable consequence of bypassing a safety instrumented system device or function lead to the following dual requirements for bypass management: features to prevent and alert unauthorized use, and operator error. Actually, as we saw in the earlier slides also, there has to be some alarm mechanism or alert mechanism to alert the operations that the particular instrument under bypass. So, and it requires a management control, highly effective management of change and access security controls, because it will not directly go in for a bypass just like a normal case by word of mouth and all. We cannot be done. There has to be a written procedure. There has to be a written form. Either nowadays it is all electronic. It may be through some ERP system. So there will be a request coming to the shift manager. Shift manager will assign to the respective maintenance personnel or instrumentation personnel who is in charge of that plant area, and they will review it and see the other process conditions are okay to do the bypass and then do the bypass. Again, when everything is getting normalized, he has to close it in the system, which goes back to the shift manager to close in his end, so that the complete loop is getting completed. What is maintenance override switch? This is another one wherein the operations have the feature to override a particular scenario, particular equipment protection for a again shorter brief period of time. Maintenance override switch are provided to override all field input designated to trip the facility in order to facilitate maintenance of field devices without interrupting the plant operation. So this is done because the plants are running. You cannot, for doing a maintenance on a particular instrument, it is not wise to shut down the plant and bring up the plant, which may cost millions of dollars for the plant facility, and as well as it may cost a big group of team to work to make a shutdown and bring the instrument or bring the equipment back, process back into operation. So which means the time and money. So this is not advisable. So always the facilities are engineered in such a way that there are maintenance override switches are provided wherever is very critical, and the operations are trained and given a procedure to use this in a right time, in a right way. Below points to be kept in mind with sys overrides. There shall be a common MOS key switch in the ESD operator panel. Have two positions. ESD stands for Emergency Shutdown System. That there will be a operation panel inside the control room. It will have a MOS key switch, which is maintenance override switch also, and it will have two positions. One position is MOS enabled and other one is MOS off. When the key switch is in MOS enabled position, there shall be a red status alarm in the ESD operator face panel, which shall flash until the MOS is turned off. The MOS should be in the off position, meaning need not be operated unless otherwise critically required. So whenever it goes into the enabled status, there will be an alarm to remind the operator that there is a MOS override has been done. So it will always alert the operators so that they will have in their mind to restore it back as soon as the work is completed. The alarm status of the field inputs which are overridden by MOS shall not be masked. MOS switches for multiple field inputs used in voting system shall be grouped together. See, there are many alarms which may be some nuisance to the operations and they may ignore it. They may silence it without giving much importance. But MOS should not be done like that way. That has to be given a critical priority and importance. The operations need to be aware which are the alarms related to the MOS, and they have to keep in mind that there is one override in the plant facility that has to be restored. If it is again delayed, the time is not completed within the allowed period, like it's not completed within a shift or something, they need to report it back to the operation manager, shift manager, and then to the maintenance personnel. That's why the alarm should not be masked. This is the word, this is the sentence meaning. So similarly, MOS switches for multiple field inputs, because in particular area there may be some few 2 or 3 or few numbers of sys protections may be happening, like sys functions may be there. There could be a chance they can be grouped together, because for example there may be some gas ductors in the particular plant facility which are voting for a trip, either 2 out of 3, 1 out of 1, 1 out of 2, based on the need, based on the sys calculations and all. So that they can be grouped, and then only one switch can be used. One particular pump or one particular turbine may have around 10 gas ductors around it. For each gas ductor there need not be a separate switch. There will be number of switches and it will give confusion and chaos to the operations. So that gas ductors input can be grouped together on a single switch. Okay, here just we are seeing one picture about the maintenance override switches for your understanding. So this is emergency shutdown switch. Always it will be in the red color in the front, so that to operations and as well as the maintenance personnel know that it is in the normal off position. So whenever this is a switch position, what we are seeing, it's a normal position. The switch contacts are in closed position. That is why it's mentioned here. Main contacts means NC means normally closed position, and which is on, which is the healthy condition operating plant, so that the machine or equipment can operate. So it will not have a like this bypass or something. In this case, plants are running at a normal operation condition. Whenever any requirement comes, whenever there is a procedure approves, then only maintenance override switches will be enabled or latched. Latch remains if you are seeing the contacts over here. See, here it is closed. Both the contacts here, what you are seeing is a contact, it's closed. In the other picture, it is a latch. That means the push button is pushed from its original position to the lock position, which is latched position. Here the main contacts becoming off. The NC contacts, which is NC earlier, here you are seeing the closed position. Here it becomes open. So in this case, machine cannot operate. So this is just for visual view of the switch. Here we are seeing some detailed view of the same switch. So there are three positions, not three positions, three different arrangements shown here. Here we are, what you are seeing is the operating element until this here, the switch, and then the locking mechanism, frame, other things, and here the contact block, which is a switch block, like we saw in the previous slide. So if you see in the normal condition and the button not pressed, button in the reset status or off status, there are different types of switches. This green line is visible. There could be different types. This is a different type of design. This is one design. So in this case, in this particular design, and the switch is not pressed, and the green indication is visible, so that switch is in off position, the equipment is running, there is no bypass or no override. So here the switch contact positions, they are in the normally closed position, and you will see the other one. See, here we are seeing the assembled state, and we are seeing the again assembled state, the switch. Here the button is being pressed, operation status, green light not visible, because when from the off position of the switch, we are some operation is doing a switch operation, MOS switch operation. By that it gets pressed. So joining together operating element and contact block with button being pressed, maintain open the status of NC contact. From the closed position of this contact, here the contact becomes open. In this case, the power coming through one end of the contact reaches to the other end and goes to the circuit to complete the circuit. Here in this case, the power coming here cannot reach it because the contact gets opened. So this is the latched position or operating button pressed position and all, or stop position. Emergency stop means this is the stop position, this is the off position. And in the middle picture shows the same switch when it is detached, when it is removed, because here we are seeing the two different blocks. This is operating element blocks, which is a switch and the connecting components like a frame, panel, nuts, everything, and the bottom portion is the switch position, which is contact block. So in this middle figure, what we are seeing is the detached state. That means the switch itself got some contact need to be cleaned, or need to be inspected, or need to be changed for any faulty reasons. So this is shown as a detached position, wherein the contact block is removed separately and the operating element block is removed separately. Here we are seeing clearly the visible indicator of the green line. Button is not pressed in this case. Okay, this is just for understanding. Here, since it is released, because there is a spring which is being pressed, and in this case, when it's being pressed in its off position, the contacts become closed. But here, this is a detached position, wherein the pressure tension is being removed, and then the switch shows in the open position. Okay, this is for the understanding of how does the switch looks like. Okay, thank you very much. Hello everyone, I am going to make a presentation on safety system. This topic will be on sys, fail-safe and fail-danger modes. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. What is fail-safe in sys? A fail-safe system is one which, due to the characteristics of its equipment and components and the way in which they are integrated, is guaranteed that in the event of any fault appearing, the system will always go to a safe status, normally affecting the availability but never and in no case affecting safety. Meaning, the safety systems are designed and engineered in such a way that it always takes care of the plant safety. In case of any hazardous event happening, takes action and shuts the respective valves, shut the respective equipment to make sure that the plant is kept in safe operating condition. Meaning, conditions in such case arises, the plant operation may stop, the production of that particular facility may go down, but the safety is being ensured. This is the most critical point while designing the safety instrumented system. The concept of a safe state, moreover, does not have to be in itself self-contained. That is to say, perhaps some conventions or rules of use or operation of such equipment or system should be established. This will help all parties to assume that entrance to this safe state. Meaning, all the components within the safety instrumented system, sensor, logic solver, and final control elements, and associated subcomponents are tested frequently at the desired intervals and ensure that the availability is there. Because as we have seen and discussed in earlier presentations, the safety systems is a passive system. It is just kept ready and it is not acting, unlike a control system, whereas sensors are sensing and the BPCS controller is giving action to the valve. The control valve is always behaving. It may be moving maybe 0.5% or 1% or 2% or 5% depending on the need or depending on the requirement. Whereas safety instrumented system valves, they are not doing any control. They are taking preventive action during hazardous conditions. So the systems are ready to act, but in a passive mode. In this, the crucial thing is understanding that the activation of safe states and degraded modes can sometimes be conventional that are implemented in the operation and use of the system in order to ensure safety of the system. This is not always the case, but it can become a strategic resource to be implemented in order to solve a problem of safety. So the safe state, which is the safe state? It can be either the valve can go to close or it can go to open. So the fail-safe condition, according to the process, according to the engineering process requirement, it has to be decided during the engineering phase and implemented in the plant. So the fail-safe action is a vital thing to understand. So for the safety instrumented system, this is arrived depending on the process criticality, depending on the equipment availability, what will happen when this particular area goes in for a shutdown. That has to be taken care during the engineering phase, and the plants has to be decided, and the fail-safe condition for the respective system instruments has to be identified. For example, in a boiler system, there are fuel gas valves. They are having normally two valves in series and one valve as a vent valve in between the main two valves. So these two valves is always in open condition as long as the plant is running and the boiler is firing. Whenever there is any requirement due to plant requirement, the gas pressure going high, the two valves will shut down. That means these two main valves will close, and the vent valve, which remains closed in a normal operating condition, will go to open whenever there is any shutdown of the boiler or any hazard condition happening and the safety instrumented system calling for a closure of the two main valves. In this time, the vent valve goes for open in order to ensure that all the gases trapped in the pipeline goes to the atmosphere. This is one example. This fails concept or intrinsically safe system. This is based on using components with well established and limited failure modes, and that in the event of fail, a safe operating condition is maintained. That is, for any of the possible failures, assume a possible impact on availability but never on safety. So again, it is being explained and described in a different way. Systems are designed in such a way that the availability can get compromised, whereas the safety can never be compromised. In this, Example, transmitter is sensor of a high level safety instrumented function. Transmitter fails high, going to shutdown. Also known as safe failure, because the failure does not have the potential to put sys in a hazardous or fail to function state. This is going to protect the equipment or protect the boiler or protect any firing device, for example. So it is going to a safe state. Safe failures shall be avoided, as each shutdown and each startup are the most critical situations in a plant operation. Meaning, the plant startup and shutdown requiring a lot of manpower, a lot of maneuvers to work on to bring the plant to a normal operating condition from the zero state, from the cold state to a operating condition. Similarly, when the plants are in the production, takes time, maybe depending on the plant capacity, depending on the plant nature, it takes half a day, 1 day or 2 days. So the plant uptime and downtime is most critical. So the safe failures, that is why there are some smart instruments are available these days. Those kind of instruments can be put in service as and when possible, whenever any new facility for assist instrumentation is being added to the plant facility, or any new process area is being built wherein the safety instrumented systems are going to be there. So they can be designed for the fail safe condition. So there the possibility of adding latest type of smart instrumentation. This can do the smart verifications, can run diagnostics to identify any possible failures. Those kind of instruments can be considered. What is fail danger in sys? In sys, fail to danger is a failure mode of the protection system that becomes shut down if there is a failure in any of its components. See, in fail to safe, some of the failures on the respective field instruments or valves can be identified by doing a regular proof testing or doing a visual inspection, by running the diagnostics on the smart instruments. So the nature of failure can be identified and isolated. There is a possibility of isolation of such failures beforehand. Whereas in fail to danger, this failure is a blind one, so which cannot be determined. It's an unknown failure. That's why it is known as fail to danger. Fail to danger fault of a hazardous condition arising, the equipment, process or plant will continue to operate without being tripped, but it has a direct and detrimental effect on the safety. The safety instruments are designed and implemented in such a way that it always takes care of the safety and ensure that the plants are getting shut down due to any hazardous condition arises, to ensure that safety is always available. Whereas in fail to danger modes, there is a possibility because the type of failure is unknown. There could be a pluggage in the safety instrumented system sensor which is not giving a proper flow for the sensing element, and the sensing element may properly sense and it may not sense. It could be 50-50. So meaning that the sensor is not functioning properly as expected, but the choke is not complete. For example, it started plugging the line, chemical getting formed in the impulse tubing. Just like that, it will not happen in one day. It may take weeks, months to get completely choked. But what that maintenance technician should do, he will go and calibrate the transmitter. You'll see the readings, you'll see the range in the transmitter. For example, it's a 0 to 10 kg per centimeter pressure transmitter. You will go and do the calibration on the instrument. Instrument may work properly, and you will say that there is no issue on the instrument, and he will make a flushing. If the line is allowed to be flushed, he may do a flushing one time and see that everything is okay. But again, after a certain period of time, for example a week or month or something, it can again go into choking and start giving a false reading. Eventually it may lead to a trip of the particular facility, particular process equipment. So that's why it's known as a dangerous failure. But actually the process is running at a proper pressure, design pressure, but the instrument was giving a false reading, leading to a trip of the particular process facility. So This is one possibility. Similarly, electrical relay contacts get stuck. See, if the safety instrument system is having a one relay in the switch gear, so the safety instrument system logic solver is giving a command based on the input, for example, the power of the motor or pump. So, whenever the power is with certain limits, the power is exceeding such limit, it will go for a trip, for example. It can happen due to overloading of the motor or overloading of the pump due to the motor bearing getting jammed or pump impeller getting jammed. There could be a number of reasons. So, which may cause for a drawing a higher power by the motor. Eventually, it is calling for a safety instrument system to act, and the command will go from the PLC logic solver to act on the switch gear for tripping the motor. But in certain cases, the contacts may get stuck, and even though the command going from the PLC, it may not act. It will not do the changeover. Only when the contact changeover, for example, it is moving from closed contact to the open contact, then only the power to the control circuit of the switch gear can cut off and thereby stop the pump. If the contacts get jammed and it doesn't move even after the relay signal is coming, so that is one kind of fail danger. So, which may eventually result in the pump keep on running even though there is a command to stop the pump. So, this is known as a fail danger condition. So, this is what happened. There is a requirement for the pump to stop due to the hazardous reason, but the command is going from the logic solver to close to stop the pump, whereas due to the fault in the electrical relay, it keeps on running. So, this is another kind of fail danger condition. So, this is one brief picture showing the safe and dangerous failures. In the failure modes, there are safe failures and dangerous failures, which will fail safe and fail dangerous, what you have seen in the earlier slides. And in the safe also, again, we have detected and undetected failures, not detected failures. In dangerous mode also, there is detected failure and not detected failures. The command for the particular equipment stop is going, and the type of failure can be understood, and the type of the nature of fault occurring which cannot be understood, that is known as not undirected failure. Actually, these are the different terminologies. There are some calculations to arrive at. There is one mathematical term known as lambda being used for understanding the failures. Those kind of detailed descriptions and mathematical calculations can be understood. You go for a detailed safety instrumented system training. Okay, that is a certification training conducted by different agencies. And this is during the failure, the production can affect, which can affect the product quality, and which can result in the loss of production. And life of the equipment gets degraded during the failure. Life of the equipment gets degraded, and which is getting degraded after the installation due to the aging of the plant, aging of the instrument and equipment. It gets degraded. Eventually, the control system components also gets degraded. This is what depicted in the failure conditions diagram. Okay, thank you for watching. Hello, I am going to make a presentation on SIS design, Safety Instrumented System Design. Video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. What is Safety Instrumented System? Safety Instrumented System, by the name, it refers to protecting personal, plant equipment and environment. In the process industry, handling various hydrocarbons, oil and gas, or nuclear and power plant installations, SIS layer acts as a protection layer above the process control layer, BCS, or alternately known as BPCS, Basic Process Control System. In the normal plant operation, controlling the plant for making changes to the various parameters in the process, The safety instrumented system layer is a protection layer which is just sitting above this layer. In the event of any hazardous events happen in the plant, SIS acts by using high performance fast acting emergency shutdown system to contain the hazard. So they have equipped with microprocessors to act quickly and then give the command to the valves to close the or shut down the system, or to thereby protecting the equipment and personnel around. Various international standards such as IEC, ISA and ANSI governs the requirements of this design. We will look about it here. So these are the design standards what we talked earlier. IEC stands for International Electrotechnical Commission. There are two different standards which is applicable for the safety instrumented system. One is IEC 61508 and another one is IEC 61511. IEC 61511 is the one which governs many safety requirements standards. So this is the one for functional safety instrumented system for the process industry sector. This also describes in this standard about the SIS design, how the safety instrumented system has to be designed. And another different standards are ANSI, American National Standards Institution, Instrumentation Society of America, ISA, and the ANSI and ISA have a common standard known as S84. So many countries have adopted this international standard which is IEC standards, whereas ANSI ISA 84 is an alternate standard for IEC being adapted in few countries like Western countries, US, Canada and all. This standard is being applied widely. Okay, safety instrumented system components. SIS is an instrumented protection layer which is designed to move the process to the safe state. SIS system comprises of sensor, logic solver and final control elements. This we have seen in earlier presentations also, and just we are refreshing to make it more clear and better understanding for the participants. Sensor, it's an instrument that measures the process conditions. Sensor devices that measure temperature, pressure, flow, liquid level, etc. Sensors can be for analytical instruments like gas chromatographs, oxygen, CO2 analysis, and electrical switchgear signals like power, current, etc. This is the one sensor what we are looking. Okay. And the second one is logic solver. It is an intelligent device that performs logic functions to convert sensor input into an action command to be carried out by the final element. This is the one, the processor, the microprocessor, which is having a high performance and high speed capacity. This is the one from one supplier known as Emerson. So this is a sensor and this is a logic solver. It will have different type of modules for taking the inputs from the sensors and giving the command to the final elements. That module is known as output module, and for the processing of signals it is having some centralized processors, microprocessor based devices. Final element, it is an equipment which performs the physical action commanded by the logic solver. Final element devices may be control valves, motor or switchgear, etc. Here we are seeing one butterfly type of valve. It could be a ball valve, or sometime it can be a switchgear equipment like some protection relays which is taking signal from the PLC, logic solver PLC, and making the pump or turbine or any equipment to stop. That is in the electrical switchgear panel. Okay, this is depicted in a different way. Process vessel, there are a pressure measurement transmitter PT 1A, 1B. This is the tag numbers what we call it. So to identify the instrument, here it is shown for the two different system. One is safety instrumented system with one pressure transmitter sensor and one on-off valve actuator, and the same vessel is having a control element, control valve, wherein we have one pressure transmitter and a level control valve. So besides that, this system is having a flow measurement also, a flow measurement sensor, pressure transmitter sensor, and is being connected to the basic process control system processor, and by internal logic the output is given to the level control valve to control the level inside this vessel. Whereas the safety instrumented system is taking a signal from the this pressure transmitter PT1A, and if any hazard condition arises and this control valve is not able to control and the pressure inside the vessel getting high more than the designed limits, so this pressure transmitter 1A sends the signal and give it to the logic solver, and logic solver processes the logic internally and then gives the command to shut off this SDV, shutdown valve. So thereby the input to this vessel is getting contained and the pressure will get nullified. So it is similar one which is showing a different P&ID process and piping and instrumentation diagram. It's a part of a vessel. Again, this is a process you can consider like a chemical tank which is having a pressure measurement sensor, pressure transmitter, and here these signals are going to the safety sensors. This is having two sensors going to the safety instrumented system, and another one pressure transmitter, it is being used to do the measurement, and this signal is going to the basic process control system, and also it is having a flow measurement sensor. So based on the cell pressure, this is giving a command control output to the control valve and the pressure is being maintained. But in a similar case, the pressure cannot be controlled within the designed or allowed limits. So when the pressure inside the vessel keeps on increasing due to some reason, for example, this basic process control system is giving a command output and the valve is not able to close. For example, sensing the pressure high, getting high, there is a command going from the basic process control system, a processor, to close the pressure control valve, but due to some internal faults or whatever reason, this valve is not closing and thereby the pressure inside this process getting high. So eventually and the pressure goes high. So these two pressure transmitter sensors senses this one and then gives to the safety instrumented system logic solver. Logic solver process the signal internally and then give a command to shut down these two valves. These two valves will get closed in this condition. So to ensure that the pressure is not getting further exceeded and protect the cell being exploded or further hazards happening. Here we are seeing the drawing about the safety instrumented system life cycle. This is a life cycle for the safety instrumented system, how it has been designed, everything. So it is having about 9 phases. In the phase 1 we are doing the conceptual design for the process, and phase 2 is having the analyze process hazards, determine the safety instrumented system need. That means how many transmitters, how many sensors and how many valves need to be installed, that is being designed. And next one is defining the target safety instrument integrity level. These are all coming in the part of LOPA, layer of protection analysis. We have seen briefly in earlier presentations. So these are all being in the part of the LOPA, layer of protection analysis study. And after this thing, it goes to the next phase, which is the design sys. So this is the topic which we are going to discuss in detail in this presentation and the forthcoming presentations. So this is the design phase of the safety instrumented system. Next one is based on the design. It goes for the installation phase, installation of safety instrumented system, and then commissioning of the safety instrumented system, and operate and maintain the safety instrumented system, and decommission in case of any need. One particular process unit is getting decommissioned due to the process change or any other reason, there may be a need to decommission the instruments which have been constructed in the earlier phases. So this is discussed in this phase. Actually, this is part of the IEC 61511 ISA standards. There could be some more phases which need to be studied and taken care, which we will discuss in further forthcoming presentations. Now we will go over the objectives of the safety instrumented system design. Safety instrumented system, different roles and responsibilities as per the company standard to be defined. For example, automation safety coach, design engineering lead, operation engineer or leader, technical center resource lead, etc. Each companies, according to the global location, geographical location, they have different standards based on the country, government requirement regulations, and the respective country's industrial board or whatever it is. So based on which the standards has to be developed for each company. Maybe it may be unique for some countries, it may be different for some countries based on the region, based on the safety requirements. Okay, so these are all the different roles who are participating in doing the design. And second one is develop conceptual design as per the safety instrumented system requirement. As we see, this is the first phase in the life cycle, the conceptual process design. What are the instruments has to be installed? What is the protection needed for the complete process? And based on which the LOPA, lower protection analysis, will be discussed between with this team, and there could be some more members also as per the plant need, and it will be designed. So this is one of the objective. And review the SIS design like SIS sensor configuration, PLC or ESD system design, configuration, and final control element. Like what we saw in this one, here we have sensor, logic solver, which is a PLC, programmable logic controller, and this is a final control element. All this what is to be installed and what is the type of configuration, all these things has to be ensured. To ensure reviews this design like this sensor, logic solver, and final element, to ensure if the vendor's product meets the guidelines prescribed by the global agency such as EXIDA or TUV. Actually, what we saw earlier is IEC, ANSI, ISA and all. These are the international standards, and EXIDA or TUV, these are another companies who are doing the certification based on the standards, international standards. So all the vendors' products has to go through the certifying agencies to ensure that they get the relevant approval for as per the safety instrumented system design requirements. So this approval part should contain the instrument, whatever the instrument being produced, like pressure sensor, temperature sensor, flow sensor, etc. The instrument tag has to be implemented. The instrument range has to be marked in the instrument. Instrument response time has to be marked. Mean time to repair has to be defined. Mean time to fail has to be defined. And spurious strip rate has to be defined. There is one safety manual for each kind of instrument. So in this one, these parameters has to be defined for each type of instrument. Pressure sensors will have one set of values readings. Temperature sensor, flow sensor, everything will have different set of readings based on the internal calculations and the product type. Okay, ensure that SIS function, sensor final control element, shall work independently without affecting the controls. Earlier we saw there are two different layers. One is the control layer, which is having separate sensor, separate control valve, and safety instrumented system is having a different set of pressure transmitters and final elements. So here what is mentioned is each sensor and other thing need to work separately without affecting the control part. There are some more objectives. Review the design specifications as per the safety instrumented system requirement. Develop conceptual design for safety instrumented system instruments such as proof testing, loop verification, and validation requirements. During the conceptual stage, design stage, proof testing, loop verification, and validation requirements has to be tabulated. Evaluate the design specification as per the safety instrumented system requirement with engineering, operation, and maintenance team. There could be different requirement, different needs for the maintenance to do the routine maintenance activity, testing, calibration, etc. So this has to be analyzed during the design phase. Update sensor final control element configurations in the piping and instrumentation diagram. In the piping and instrumentation diagram, they have to be marked exactly identified as a safety instrumented system instrument, so that whenever the operation person or maintenance person who is going to attend will have extra care. Compare the conceptual design with the specification if it is meeting the SIS requirements. Here what happens, the design is being done by one set of people. They may be sitting either in the plant area who are directly involved with the regular operation team, or could be sitting in a different remote location and doing all the engineering activity and submitting the documents. So in this case, the design will be developed here by one company, like an engineering, procurement, and construction contractor, whereas the installation and the other part will be done by the different operating company. So there may be some gap. So whenever the design is developed, the instruments are going to be implemented and the instruments are bought, they have to be ensured that it is meeting the conceptual design requirements. This shall include proof testing requirements, whether the instrument valve can be tested online while running the process, or any alternate protection instruments in place to protect the people and environment. Process, there could be a possibility that only one instrument may be there, it is working and doing the isolation for a vessel. But for doing the proof testing, it is not possible to shut down those valves. Like in this case, see, in this case only one valve is there, so it is not possible to do the proof testing. Proof testing means we have to test the leak testing part, whether the valve is not doing any leakage or something. Passing, we call it as passing. The valve should not pass. And the operation, some cases depending on the process, it may require to close in 5 seconds, 10 seconds, like that. So these timings, those things need to be tested. So in this case, this particular example, it is not possible to isolate this valve. So there may be need of putting a bypass valve or any other isolation valve to ensure that the testing can be done. This is what mentioned in this point. Okay. Update the sensor final configurations. This is what mentioned over here about the proof testing requirements, whether the valve can be tested online or something, and alternate protection is in place. So complete hardware design, software program coding, etc. as per the design specifications. These are all the objectives has to be taken care during the conceptual engineering phase and as well as in the installation and commissioning phases. Thank you. Hello everyone, I am going to make a presentation on SIS design, safety instrumented system design. This topic will be on SIS work process. This is a little bigger topic, that's why it is split into two parts, and I am going to describe about part 1 here. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. SIS work process, we'll just understand about the SIS design standards. International Electrotechnical Commission IEC has 61511 and 61508, these two standards specifically for the safety instrumented system, and 61511 is a safety instrumented system for the process industry sector, defines the steps for SIS design. This is an international standard having being applied almost all over the globe except for few regions like Americas and maybe in Canada. There they have equivalent standard known as ANSI, American National Standards Institution, and Instrument Society of America, ISA. These two together have formed a standard S84. So this is an equivalent standard which is alternate to IEC, International Electrotechnical Commission standards. SIS work process steps. Actually, it is having 4 different phases. In this presentation, we are going to describe about first two phases, which is phase 1 layer of analysis. Phase 2 is protection layer design. Okay, each phase has multiple steps. We'll describe over the steps over here. First one, identify and define hazards. This is PHA and LOPA study. PHA stands for process hazard analysis, layer of protection analysis. So these two studies will be taken up in the first step. Second step, this is for identify and evaluate highest risk and target factor scenarios. And when the LOPA is being developed, there are many factors to be considered which is affecting the plant, and eventually there could be some hazard happening. So this is a layer of protection analysis workbook. This is describing the scenario and description of the undesired consequence, what can happen, so that can lead to a hazard. And next column, it's a LOPA target factor. Usually the target factor of 6 is being arrived. Some companies have a different standard, but this is a general one. And initiating factor, which event can do this particular cause. So this is an initiating event factor, an enabling factor, and probability of exposure. How many people will be exposed into that region of the process area and all. And on the right side we have different protection layers and the credits associated, which can be taken for each protection layer. One for BPCS, basic process control system. Another one is operation alarms, operator response to alarm. And next is safety instrumented system layer, and further we have mechanical protection layers like pressure relief valves, rupture disc, etc. So all those things will be credited, and each of by which it is able to eliminate the hazard. So by that in the target will be achieved. So in total they have to arrive at the target factor of this one 6. So each scenario will have some credit. This one you have to understand when we do the detailed calculations. So it is part of a detailed technical analysis study by the standard people. So on the third step is perform risk analysis and protection strategy. This is the third step in the LOPA analysis. Fourth is select alternative protection methodology and document them. These are the 4 steps available in the first phase. And this LOPA workbook what we saw earlier. And the second phase is protection layer design. First LOPA is analyzed, and the target factors and other things have been taken care. In the next phase, the protection layer design is being taken up. In this one, the step 5 is for define and design instrumented protection system. See, in this presentations we are focusing about the safety instrumented system. So this is an instrumented protection layer. So always we look into the topics and discussions on the instrumented protection systems. And sixth one is verify instrumented protection system design. Fifth step, it is a define and design of the IPS. Sixth one is verify the instrument protection system design. So whatever is designed is whether it is meeting the requirement. This will be done in this sixth step. And seventh step, it is develop instrumented protection system, operating methods and training. So we'll go over about the detailed descriptions of each step in the following slides. And eighth one is develop instrumented protection system application software. All the applications are running in the microprocessor based high speed processors known as PLC. So it is having a particular type of application software. So that has to be developed. As I told earlier, it is having 2 more phases, third and fourth phases to be discussed in the next presentation. Okay, the first 2 phases and the 8 steps will be discussed in detail in the coming slides. Okay, step 1. Who will do what? Associated plant process engineer responsible to lead safety analysis. This is about the first step of this one. Identify and define the hazards. Okay, we are talking the details about this first step. So the process engineer is responsible to lead safety analysis, evaluates alternatives against the site selection issues, document expert plan for SIS, LOPA, process design and process reviews, supplies input documents. The documents may be different kinds, like first we will be starting with the process piping and instrumentation diagram P&ID, and there could be process flow diagram, there could be control narratives, and there is some safety analysis, and those kind of documents has to be inputted in this step. Identifies hazardous process envelopes for target factor identification. As I told earlier, each of the process area is bound for some kind of hazard that has to be identified, and the how much target we have to achieve, that has to be identified. And updates LOPA target factors, responsible for initial process safety strategy development plan. He is the one responsible for initial process safety strategy. Okay, in the second step, identify high target factor scenarios. Process engineer again, he is the one leading this activity. Use the results from step 1, identify and refine LOPA target factors, and if the answer is yes, communicate the need for a HACCP. HACCP stands for hazardous operability study. Again, this will be done by a team of process experts, chemical engineers, highly skilled chemical engineers. There could be some subject matter expertise in the particular process area and process safety engineers who are having thorough knowledge about the chemicals being used and the reactions that are being happening in the particular process or overall to the overall plant. And there could be instrumentation engineers or automation engineers who are responsible for the plant maintenance, instrumentation maintenance, etc. Responsible for initiation and completion of preliminary structured scenario analysis for the most hazardous scenarios. Target factor of 8 or higher. We saw in the target factor 6, this is, as I told you, this is differs from companies, but target factor 8 or higher, wherever it is required, those kind of scenarios will be taken up and discussed in detail. And initiates as of if required. So when the target factor is going 8 or higher, as up will be required to be done. This is one, can say one factor, this thing higher than the LOPA. Responsible for initiation and completion of consequence and frequency analysis for most hazardous scenarios. So they'll study and then the consequence and frequency for each event happening, those things has to be analyzed. Initiates and completes LOPA evaluation for most hazardous scenarios, including updating LOPA documentation. So this is one particular scenario, this is one example. They have to analyze in different angles and different type of scenarios. What could happen? It could be from any pump hazardous scenario, or it could be failure of one motor, or suppose it is one motor is coupled with a turbine or something, the failure of the coupling or failure of the bearings, or there could be a switchgear getting tripped. That could be one scenario. Or the pump is running and the output pressure is not developing, either due to the impeller problem on the pump, or it could be due to the suction is not adequate. Like those kind of different kind of scenarios which can lead to the hazardous event. Those things will be discussed. And all different scenarios and different safety targets achievement requirements will be detailed and analyzed, and they have to be documented in the LOPA documentation. In the step 3, which is finish risk analysis and protections, the process engineers updates the LOPA here, facilitates planning and execution to identify and evaluate remaining hazardous scenarios using LOPA. This is an elaborate study which may go for months or couple of months, depending on the size of the plant, size of the process, etc. So they'll go through the analysis. Responsible for incorporating results of detailed analysis into LOPA. Ensures all LOPA gaps are closed and protection layers have been incorporated into final design documents. Aim of this process engineers and the team, there could be some LOPA teams also. Their team is to achieve all the, it's about the target factor, no? Just to, they will be going over the different layers of protections which is available, which can be incorporated in the particular facility, and try to achieve this number. This is their fundamental study. And wherever, that's what we mentioned, wherever there is any gap is there, target factor is not meeting to the required one, so there could be some requirement to install additional instrumentation or additional mechanical protection layers, etc. Okay. Fourth step, in the select protections and document, the process engineer initiates the drive to identify the one solution to be implemented. There could be multiple solutions to mitigate one scenario, but he has to analyze and come out with the best one to have a minimum hardware instrumentation as well as mechanical protections to achieve the target. Assess manufacturing engineer responsible in making the SIS list. Initiates and ensures completion of the necessary reviews. Initiate step, then works with manufacturing rep to ensure section 1 of SRS form to complete. SRS stands for Safety Requirement Specifications. This is the one document to be developed after completion of the LOPA study and all. So he has to ensure that first section is to be updated. Provides physical property data for instrument protection system instruments. This is what type of sensors to be used. It is applicable for the particular process technology, etc. Okay, these are the 4 steps. Now we are going to the second phase, which is protection layer design. So we are going to the second phase and the detailed descriptions what has to be done in this one. So here it is comprehended with for 4 steps between 5 to 8. SIS is an independent protection system. BPCS protection functions are also independent protection. Instrumented protection system. Instrumented protection system. SIS is an IPS. BPCS protection functions are also IPS. In the design phase, the manufacturing representative engineer, process engineer, he is the one resolves the plant process engineer related document deficiencies. There are any deficiencies in documentation. He is the one, because manufacturing engineer is the one responsible for the particular process area, so he will be having much knowledge about that area. So he will have to review and verify any deficiencies and resolves the plant process engineer related sharing deficiencies. As we saw in the LOPA workbook, there are different layers available to mitigate the scenario, hazardous scenarios. So there could be some mistakes, there could be some deficiencies. So those things has to be addressed by the manufacturing engineer. Review and agree to the book of conventions and function library. So there has to be a uniform code, uniform book of conventions like notations and PND markups, etc. That has to be uniform across the plant. There could be different consultants and contractors. There may be some difference between them with respect to the application, with respect to the geographical location and all. So that has to be uniformed for the particular plant area. Associates with instrument designer on developing the conceptual test plan and ensures communication of changes between instrument and electrical disciplines and plant automation personnel and maintenance personnel. There could be some kind of conflict and difference between one discipline with other discipline that has to be resolved. So this is the manufacturing process engineer's responsibility, and assist the process engineer for doing all such activities. Assembles the documentation necessary to determine economics are optimized. As I said earlier, there could be multiple ways to protect and mitigate a particular scenario. So they have to analyze and come out with the best possible solution to have minimum instrumentation as well as minimum mechanical protections and ensure the safety is achieved. So by that, there could be some iterations to come out to the best possible mitigation strategy. Thereby the economics is to be optimized. Assembles the documentation for confirming the safety coaches concurrence of design. There could be safety coaches review. So they have to review and approve the layer protection analysis and other instrumented protection system design and all. That has to be obtained, and this is one of the requirement. Works with the plant, maintenance and process automation teams in completing the validation and proof test procedures. The validation and proof test are the mandatory requirements for the safety instrumented system. So whenever the new plant is being developed, new facility is developed with the safety instrumented system, the validation procedure and proof test for those instruments being installed has to be developed. Ensures documentation is assembled and delivered to plant operations in approved format. Each plant will have the philosophy or standard standard documentations with respect to their company standards or the national standards. That documentation has to be assembled. Facilitates development of specific operating procedures with the plant technical authority and operating the plant role. So we have to develop the operating procedures as well, which requires the support from the plant technical authority. There could be a technical team responsible for the particular process. They could be sitting in the same plant area, or they could be working in a remote location. But the manufacturing process engineers has to work with them and ensure that this thing has been taken care. Ensures training materials are assembled and delivered to the plant operations in the approved format as per the plant standards. So the operations need to be aware of the all type of instrumentation, all type of safety instrumented system and mechanical protection layers protections, because they are the one going to operate there. They are the one going to be available 24/7 in the plant and taking care of the plant operations. So their shutdown procedures for each of the equipment and any during emergency what has to be taken care, those kind of emergency procedures, everything has to be developed. So that has to be developed, and every company will follow a different standard. So that has to follow the specific standard for the particular company, particular location. Ensures maintenance training materials are assembled and delivered to the maintenance personnel. Also, the maintenance team has to be aware of the and have the thorough knowledge about the installations across the plant, so that they can do the maintenance at required time and in a proper way. That has to be ensured. Hello everyone, I am going to make a presentation on safety instrumented system design. This topic will be on SIS work process, safety instrumented system work process. This is the second part of the work process. This video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. So in the earlier presentations, we saw the first and second phase. In this presentation, we will see third and fourth phase of the SIS work process. Third phase, it's for verify, install and validate SIS. Okay. The step number 9, it is to prepare procedures for instrumented protection system hardware commissioning. And 10 is for simulate the instrumented protection system software and test. Step number 11 is for assessment of instrumented protection system application software and SIS policies respect to the area authorities. And number 12 is to validate the instrumented protection system software and hardware. These are the 4 different steps involved in the third phase. And fourth phase is for operate, maintain and modify. Okay, in the fourth phase, the step number 13, it is to they have to register the instrumented protection system in ERP system. It could be the enterprise reserved plan, it could be the SAP system or some other system in MIS or something equivalent to this available each different plant. 14 is to operate, maintain and test the instrumented protection system. They have to undergo the specific kind of proof testing and the validation or different procedures are there for the safety instrumented system that has to be taken. 15 is to modify the instrumented protection system. Whenever there is any requirement and any new facility is being added or any gap is seen from the LOPA analysis, to fulfill the gap, there could be some additional instrumentation or additional mechanical protection layers being introduced. That has to be done in this using this step number 15. And 16, it is for decommission of the instrumented protection system. In case of any particular process plant is being isolated, being decommissioned for different reasons. It could be the particular plant areas no more available, or it has been enhanced with a different facility and the old facility getting decommissioned. Those kind of situations can happen. In the below slides, we'll be looking into the details. One is the proof testing. What is proof testing? This is testing that occurs after a startup as part of ongoing maintenance. For the normal instrumentation, which is part of the BPCS, basic process control system layer, they will have to go through the calibration and testing of the instrument at a regular intervals. It could be every year or alternate years based on the type of instrumentation. Whereas in the safety instrumented system, there are some standard requirements. So they have to undergo through a proof testing that has to be recorded and entered in the plant's ERP system. It is a record. In case of any hazardous event happening, they have to analyze if any instrumentation is failed to work. So the proof testing is a mandatory requirement. Written proof testing procedures specific to the IPS instrumented protection system and IPS component define what and how the IPS components are to be tested, as well as specifying who is qualified and what the required qualification are to perform the test. It's not just like any instrument technician or any electrical technician can go and do the maintenance on such instrumentations. They have to have a certification. They have to undergo the criticality requirements of the particular instrumentation and shall be able to do all kind of testing required. So there could be some certification requirements for those maintenance technicians or supervisors who are all involved in the plant maintenance. These tests may be more rigorous than similar PPM. PPM stands for preventive and predictive maintenance testing for similar pieces of equipment that are not part of an IPS. This is what I told earlier. There may be some identical instrumentation available in the basic process control system and another set of instruments available for the safety instrumented system. So the instruments that are in the basic process control system, they need to go for a regular calibration check and zero and span, we call it, for the ensuring the minimum range and the maximum range. If it is a 0 to 10 kg per centimeter, pressure transmitter means the maintenance technician has to go and see that at minimum this thing, sensor reading. And when there is no pressure applied to the sensor, it has to give the 0 pressure, and then maximum is applied, it has to measure the 10 kg per square centimeter pressure. This kind of calibration should be taken up for the BPCS kind of instruments, whereas safety instrumented system, they will have some additional testing to ensure the accuracy, to ensure the repeatability, etc. So that's why it is going for the proof testing. Validation testing. This is, I will explain about it here. Testing that occurs after the construction and before the startup, that is pre-startup test. Once the safety instrumented system equipments are installed in the plant, they have to go for a validation testing to ensure that the instruments and valves associated with the safety instrumented system are performing according to the design. The testing ensures that the system as a whole is operational and performs as intended. This is a whole loop and function test using the installed field sensors, logic solver, computer program, and the actual field equipment, including the control and mechanical devices like pumps, generators, or any turbine, or any other equipments associated with it, or there could be only some on-off valves associated in this safety instrumented system loop. So this is a complete testing. Validation testing means it starts from the sensor until the final control limit. So that complete loop. Sensor, logic solver, and final control limit, all these things put together, they are working for a safety instrumented system, and it is working in a particular to overcome a particular kind of hazard on a particular consequence based on the LOPA workbook. They are called as safety instrumented function. So in the validation testing, all the three components like sensors, logic solver, and the field equipment valve will be tested. Okay, now we'll go over the step 9 of the SIS work process. Commission hardware SIS work process. The manufacturing process representative, who is a person involved in the plant's manufacturing area, so ensures the relevant personnel are identified to lead acceptance testing, instrument installation checkout, and instrument loop verification. So they have to identify who are the persons responsible and who can handle those kind of activities. That means acceptance testing, instrument installation checkout, and instrument loop verification, etc. Responsible for coordinating different plant departments involved to complete the loop check. Loop check is one process wherein the instrument technician or electrical technician has to feed from the field from the plant location and see the respective readings are being registered in the DCS and the HMI operating screens. Ensure all as-built documentation is prepared as needed for plant operation. Responsible for initiating and coordinating IPS, Instrumented Protection System validation. Coordinates documentation updates and ensures the completed successful validation procedure is incorporated into plant operating management system or such equivalent applicable. So he has to ensure that the required validation procedures are being incorporated into the system. Okay, in the step number 10 and 11, it is develop and assess the instrument protection system. Again, the manufacturing process representative, he confirms all operating procedures and documentation is prepared as needed for plant operation. He has to ensure that operating procedures are being developed and made ready for the operating personnel. Ensures all operation staff are imparted training for the required job skills. They have to undergo different kind of training based on their work nature. So he has to ensure that all the staffs are getting trained. Assess all application software are developed per industrial standards and international committee requirements. Application softwares are being developed as per the standards. Step 12, the field validate hardware and software process. The manufacturing process representative ensures that all PLC hardware are installed per design requirements and software application programs are deployed without any errors. The PLC program for executing the particular logic has to be developed and he has to take care about this. Responsible for initiating and coordinating SIS validation process. As we saw in the first part of the slide, the validation process has to be prepared and coordinated. Coordinates the documentation updates and ensures that completed successful validation procedure is incorporated into plant operating management system. The validation procedures has to be updated into the plant operation management system like MIS or some other equivalent system. Okay, we will continue with the step number 13. In step 13, it is document library and training. Again, the manufacturing process representative works with maintenance and operations to ensure the completed instrumented production system IPS validation and proof test procedures and IPS operating procedures are saved in plant operating discipline. Each plant will have operating procedures and operating methodology kind of library. So they'll be part of their operator training, and he has to ensure that the procedures are being developed and saved into the operating procedures manuals. Ensure that list of personnel authorized to change and load the SIS program that is updated for the project. SIS programs, safety instrument system programs, can be handled by some qualified engineers and qualified technical professionals only. So he has to confirm that is updated, who are the persons authorized to change the program. Ensures consistent project document structure for filing in the plant documentation library. So he has to pick up the most important and most relevant documentation and file it into the plant documentation. Leads the training team and facilitates the gathering of project information needed for training and develop specific plant specific instrumented protection system IPS training in curriculum. So the training team has to be formed and the required project information and required IPS related information has to be developed. In step 14 again, it is for operate, maintain and test the instrumented protection system. Provides assistance in analysis of incident history. Any history that is happening during the operation has to be analyzed. That means any hazardous event, something is happening, that has to be analyzed. Provides the target factor information and approves the LOPA, revised LOPA scenarios. If there is any gaps during the validation process, they found it is not meeting up to some standard requirements, that has to be re-evaluated and some additional protection layers might be required to be introduced. Typically responsible for conducting the safety audit. Each plant which is having the safety instrument system implemented, they will have to undergo a safety audit. So it has to be ensured during this step. Okay. Again, further going into the step 14, the documents the safety experts plan. This is being done by the respective project engineer and manager and safety engineer. Documents the safety experts plan for the SIS LOPA design, review and inspection of instrument and valves, and updates the safety experts plan for identified process safety risk analysis issue. So they have to update the safety experts plan. What has to be done if there is any consequence, any hazard is happening, what is the consequence and how it has to be handled, that has to be inputted over here. And in the step 15, it is modify the instrumented protection system. The production leader, plant owner is accountable for many tasks, executes responsibilities for this role according to the SIS work process steps that apply to the scope of the project or any change. And in step 16, it is for decommission the SIS protection layer. As we discussed earlier, if any part of the plant is being isolated, is being taken off from the process, the respective SIS protection which are available in those areas has to be decommissioned. So it is also a part of the step. A plant owner with safety expert decides the facilities which valves instrumentations has to be decommissioned. These cases arises rarely because the isolation and removal of one's facility is not a routine activity. So there could be some chances wherein the plant is going for a different technology, or they are going for an enhanced capacity or increased capacity which requires a different kind of mechanical equipment to be installed. In such scenarios, the decommissioning may be required. In such cases also, the SIS protection layer decommissioning has to be taken care with due care. These are the different steps involved in the safety instrument system or process. So one has to understand all the 16 steps that are involved in the safety instrument system or process for better implementation. Thank you. Hello everyone, I am going to make a presentation on SIS documentation requirements. This video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. Sys documentation. It involves different type of documentation. First one is LOPA documentation. LOPA stands for Layer of Protection Analysis. The LOPA team provides the below information for documentation, which is having SIF number, Safety Instrumented Function number, SIF specification, brief description of what the SIF is trying to accomplish and how it is stripped. In the safety instrumented function, what is the intent and how the trip action is being carried out. This is being described. LOPA reference information. Each LOPA will have multiple scenarios, and in that scenario there will be number according to the plant location and equipment location. So this will be there. Process area of the respective plant with code. Each plant will have an unique code for the respective industries, so that will be there. Description of credible scenario. Whatever scenarios that are having credibility and which is having the target factors under different circumstances, so that will be there. And the reference of all LOPA initiating events where SIF is used. LOPA, as we know, it is having multiple scenarios involved, and each scenario is having a different initiating event. So wherever the safety function is being built based on a particular scenario, that reference number has to be included. So reference of cases, if multiple cases are involved, there could be multiple scenarios. For example, on a boiler or a heater furnace, there could be a fuel gas high pressure and there could be a fuel gas low pressure. On both the conditions, the main block valves, main inlet valves has to be closed as a safeguard to protect the boiler. So these two on-off valves will be a part of two different case scenarios. That's what it's having multiple cases. Any sharing of instruments details, use the P&ID tag, logic solver tag or sensor description. There could be some possibility where one sensor is being used in the multiple scenarios, but ideally as for functionality they will be working independently, but because of the physical installation requirements and challenges, there could be one transporter. This will be very minimal in the plant. Layers of protection analysis assets. All LOPA references numbers to be updated. Next one is proof test. It is another critical and vital parameter for the plant safety operation. So the documentation proof test is also an important activity as part of the safety instrument system documentation. The plant shall maintain records that certify that proof tests and inspections were completed as required, because this is part of the audit requirements also. Whenever any external third-party agencies like Bureau Veritas, TUV or some other major international concerns may be visiting the facility and then do an audit on the facilities, and the audit will be on different sections, and exclusively they will have some specific days for the safety instrumented system. So during that time also these records need to be shown. These records shall include the following information as a minimum: the type, details of tests and inspections performed. This is for the proof test. Date on which the tests and inspections taken up. Maintenance person name who performed the tests and inspections. Instruments, valve serial numbers or other unique identifier. For example, could be loop number, tag number, equipment number and a safety instrumented function number. Again, this as per the geographical location of the company, governmental regulations and the company's own management directions, it could be different from each plant. The results of the tests and inspections and values, that is as found and as left conditions during the initial period of test, initial point of test, the results could be different. For example, if it is a 0 to 10 kg per square centimeter transmitter sensor, it could read 0 to 9.8 or 9.6. 99% will be accurate, but there could be a little bit of change or drift inside the sensor body. And when it is calibrated, when it is tested, the accuracy has to be as close as to actual. Then some documentation need to be kept in the library, which are for the plant lifetime to do the maintenance. Documentation requirements include LOPA, operation and maintenance procedures, result of the hazard and risk assessment, LOPA worksheet if required according to process risk management standard. LOPA worksheet has to be kept safely. LOPA notes and calculations. When the LOPA is developed and the different safety layers are determined, that goes through a risk management strategy. So those data has to be updated. LOPA notes and calculations. While doing the calculation for the probability of failure, demand and safety integrity level, etc., there will be some assumptions, because every scenario, every plant condition cannot be done as a physical. So there could be some risk measurement requirements. So those has to be updated. Safety requirement specifications. Safety instrumented system loop documentation forms. Assumptions used when determining the safety integrity levels. Calculations of probability of failure and demand. Again, these are all the calculations based on the plant safety instrumented system installation. This is done at the beginning of the project or beginning of any additional facility involving safety instrumented systems are being built. And SIS maintenance procedures, a detailed written proof test procedures, validation procedures for each element of the safety instrumented system, commissioning procedures. These are the different documents also needs to be maintained in the library for the future reference. SIS operating procedures, records of verification and validation, system validation, periodic and automatic test results, results of assessments and audits, modification information and documentation. MOC stands for management of change. Any modification done on the safety instrumented system loop are to be documented, and they have to pass through one MOC system, management of change system, which requires different levels of approval. As part of this documentation, the safety instrumented systems, safety instrumented functions also need to be earmarked exclusively in the piping and instrument drawing E&ID. So safety instrumented function shall be according to international standards. If you see here, it will be like that sensors, elements which are involved in the SIS loop will be identified with a hexagonal symbol, and the SIF number, it is a section symbol, means it is used in the safety instrumented system as a SIF function, and it will carry a number. All components in this slope like sensor, final element get the same SIF number. So it will have a same SIF number which is acting based on a particular hazardous condition and on particular scenario. These are the standard documentation that are to be maintained as part of the safety instrumented system. Thank you. Hello everyone, I am going to make a presentation on safety instrumented system maintenance process. This video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. SIS maintenance. When plant facilities having safety instrumented system goes into operation, maintenance has three primary responsibilities, which is perform SIS related proof testing, define the frequency of SIS components to be proof tested, perform SIS repairs as needed. This is to ensure time up to which a sensor in a multiple configuration can be allowed to stay out of service. Normally, this should not exceed twice the scheduled frequency. Otherwise, higher level management authorization is required. Meaning, if the sensor is calculated to be proof tested every 3 years, then maximum it can extend up to 6 years. So, it should not exceed that limit as long as the proof testing has to be done without ending for due. Otherwise, it calls for some sys repair deferral, like that different work process it has to follow through. That's what you mentioned. It has to go for a higher level management authorization. Always maintain documentation about the results of the sys test and repairs. Results of all tests and services performed on the sys safety instrument system should be documented. This should note whether the service was planned or unplanned. Like, it can happen, the schedule can happen. For example, in the month of November, on date 20th November, there is going to be a planned shutdown, but planned proof testing for a particular sensor and final element. But there is a planned trip happen around the 10th or 15th of November, which is a week before the actual shutdown date, actual proof test date, which is a week before the actual proof test date. Then during this shutdown, this safety instrument system would have acted. We can take either those credit, or the shutdown time can be utilized to do the proof testing on those instruments. Rules of sys maintenance. Sys proof test intervals shall be established based on safety integrity level and sys configuration, hardware and software. This is about the configuration of 1 out of 1, 1 out of 2, 2 out of 2, 2 out of 3, like that. Those configuration is being talked over here. So, proof test intervals are arrived based on the safety integrity level, which is done based on the different calculations by the safety system experts. Proof test intervals is to be calculated using relevant tools for sys and ensure it meets the safety requirements. For doing the SIL calculations and all, there are different tools available from international agencies. Those can be utilized. Periodic proof test documentation shall be kept at least for the last 2 tests to ensure that sys integrity. If tests confirming the sys requirement, additional testing to be planned. Supposing any instrument failing the test, so the root cause of those failures need to be identified and then need to be corrected. Maintenance responsibility. The responsibility of plant maintenance team is to do proper maintenance of safety instrumented system in order to ensure that the required SIL of each safety instrumented function is maintained and to confirm the designed functionality safety is maintained for the plant. So, the maintenance has the responsibility to do the testing at the proper intervals and by maintaining the instrument in a good integrity. So, here we are seeing one sample of the maintenance system overview. This is from the ERP tool of a particular company, and here we are seeing the SIF number, SIF 1 to 10, and SIF name. It will be like here it is being example is given as example 1, 2 and all. And the integrity level, safety integrity level, this is SIL 2 type of SIF, and the second one is a SIL 1 type of SIF. And here the description, like here the PZ 311 312 closes, XV311 on high pressure. This is some pressure instruments which creates a signal and then closes the XV, which is on off valve. The first sample. Second example is on LS 100 closes XV100 on high level. This is a level transmitter. When it goes high, it is giving a close command to close the on-off valve associated. It's a segmented proof test, means it will be done in the parts, segmented, and end-to-end means it's for the complete loop. And here the next column, the next test, which is scheduled because it's older data, that's why it is giving a older date on 14/7/2020. And we will go through these lines here. Next test in days, due days is 7 days is due for the next test. Minus 7 days means it is crossed actually. That's why it is having a overdue. Overdue means it has crossed the deadline date. Next test scope is calibration. Sensor element calibration. SE stands for the sensor element. It's calibration. Override active? No. Any override is there? Like bypass anything is there? No. And lifetime issue? Is it a lifetime problem? Yes. Lifetime overdue for this instrument. So whenever it is in yellow, there is that SIF needs to do an attention. Maintenance has to do an activity over this one. That's what here mentioned here. SIF needs attention. Proof test interval exceeded with less than 5% or partly override active or other issues needs attention. When it is exceeding the pre-planned interval frequency time, then it is the particular SIF element is indicated in yellow by giving an alert. When it is in green, here we see the description, the SIF is okay, proof test interval not exceeded and no override active and no other issues. Green means it is healthy, this is done in appropriate time. And when it is become red, SIF is not okay, proof test interval exceeded with more than 5% or override active and or other issues. When it is in yellow, it is less than 5%, that is here less than 5% overdue. If it is more than 5% overdue, it becomes red. So giving highest alert for the maintenance personnel to look at it. So here there are different legends. SC stands for the sensor element, LS stands for the logic solver, FE stands for the final element, and SC means sensor element under calibration. Test always refers to the proof test or calibration. So here whenever the maintenance is doing that activity, they have to record this log, they have to update in the ERP system. SIS maintenance proof testing requirements. The SIS shall be designed in according with the maintenance and testing requirements. A proof test is a physical test to determine if there are problems with a SIS or BPCS IPL component that the online diagnostic does not check. Actually, there are some smart instruments which is having a online diagnostic capability. They run through the online testing internally and reports of any problem. But the physical test ensures that in the physical test, the complete range of the instrument will be fed and checked, and it will be checked for the alarms, it will be checked for the error messages on the sensor electronics. It goes to the many steps, and it will be checked for the constants. If there are any constants configured in the transmitter, that will be checked, whether it is matching to the old last calibration value, any correction factors, K factor, like that. Those kind of data will be analyzed during the proof testing. For example, for a sensor, this could be plugging in the sensor line, a pinhole in the diaphragm, or an undetected electronic drift. The proof test brings out false problems in the instrument, if any. There is a plugging in the instrument impulse lines, then the readings will be eventually not proper. So when the transmitter is checked for the calibration for its 0 to 100% range, and if it is giving a good result as expected, then if the transmitter is not reading as per the process condition, there could be possibility of these three conditions, like plugging in the sensor line, pinhole in the diaphragm, or undetected electronic drift, which happens in the sensor internally, may impact the readings. Depending on redundancy and application, the proof test may be required. Some instruments be pulled out of service or process needs to be shut down. That's what. If there is a 1 out of 1 configuration and the calibration or proof testing cannot be done online, then it is a big challenge. It may call for the shutdown of the particular part of the plant or particular equipment of the plant. Proof testing requirements will go further. This is why it is very important to consider proof testing when designing a safety intermediate system. In all cases, the goal of proof testing is to return the component as good as new, so that healthiness on the instrument is ensured. So it is mandatory to do the proof testing at the desired frequencies, and so that the running condition is being reset. For example, it is being reset and it is ready to go for the next 3 years or 5 years as per the calculations. The performance of all SIS components must be periodically proven via proof testing, including SIS category valves. The degree to which a SIS valve is leak tested is determined by its required functionality. So the leak testing is another critical phenomena. Wherever the valves are in the oxygen line service or any chemical service which may require a tight shut-off conditions, That means it can have only 0.003 bubbles per minute passing. Only this is a standard, APA standard. So exceeds, that means the valve is not meeting the requirement and it is passing. So necessary corrective action to be taken. Probably the valve has to go for a repair. Internally, some lapping or machining of the valve body or stem need to be done to overcome that leak issue. Based on the plant unit criticality, some valves may require zero leakage. That's what I explained now. Those valves that are determined to require a bubble tight leak performance, also called a tight shutoff, due to exceptionally low leak limits necessary to maintain risk mitigation, need to demonstrate this level of performance. Options for bubble tight testings are to conduct the bench testing in the valve shop or inline testing. There are two possibilities. On the inline also, it is possible to do the shop to do the valve leakage testing, or it has to be done in the laboratories or workshops. In some cases, SIFs can accept large leak rate as per the calculations while maintaining the risk mitigation. So it's not mandatory that all valves need to be zero leakage. Some valves in some service, even though it is in the safety instrument system, the service may not be quite critical wherein they need to maintain. For example, seawater system. So it can wait in case this valve is not working, it's passing, it's not meeting the leakage requirements. So it will not hamper anything. Only the valve will be passing. Otherwise, the function will be maintained. Whereas in other critical applications, the passing causes a severe issue for the operations. And leak test for the fine element in this application service may be visual inspection, checking in the field for the stem movement by an experienced instrument technician. Whoever is having good experience has to do the testing. Logic solver testing. This is on the processor. Proof testing, repair and documentation procedures also apply to logic solver. Maintenance frequency of logic solver may be different than the sensor and final element. Usually the proof testing of logic solver is matched with the plant's turnaround or major overhaul frequency, so that operations are not affected, because logic solver is being the heart. It's the heart of the safety instrumented system. So anytime it has to be in line. Okay. Even during the shutdown conditions, the safety instrument system should be healthy. So the operations may be required to stoke some valves, test them. During that time also it's required. So the logic solver selection and application for the SIS is quite critical. Even though the plant goes for shutdown, the logic solver functionality may need to be maintained to maintain some essential services like cooling water, steam, etc. This is what I briefed a little before. So even though the plant is shut down, doesn't mean that the SIS logic solver can be stopped. No, it has to keep in running condition, and the outage for the logic solver processors will be given maybe 1 day or maximum 1.5 day, like that, depending on the plant criticality. So in this time, the required proof testing or all the testing has to be done. The responsible project engineer can bring and do the testing with the help of the maintenance people. The logic solver hardware must be periodically tested according to a written proof test procedure to detect unsafe and diagnosed failures. This is what the logic solver also will have the testing at the calculated intervals. That has to go for the testing. Like in this case, because always if it is a redundant processor, always two processors are working in parallel and ready to do the takeover. Shutdown is the best period wherein one processor can be make the program stop, and immediately the signal, everything will change over to control, everything will change over to the next processor. The second processor will keep running. Once the things are established to the prior condition, again we can switch off the second processor for the first processor to take over. Like that, testing also can be done during the running stage, because logic solver is a very vital and a critical part of the safety instrument system. This has to work perfectly for the total whole system to perform well. Thank you very much. Hello everyone, I am going to make a presentation on SIS parameters definition. Safety Instrumentation System parameters definition. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. Let us understand few parameters essential for SIS, Safety Instrumentation System. First one is scenario. Scenario is a sequence of events that results in an undesired consequence. We would have seen in the LOPA example, LOPA sheets, for each different part of the equipment, part of the plant, there could be multiple hazard scenarios happening. One could be like for the boiler, which is having a fuel gas to fire the boiler. It may be going for a high pressure due to failure of any control valve. This may be one particular scenario. Or pressure failure in the control valve may lead to valve closing and leading to fuel gas pressure going low. This may be another scenario which may result in a different consequence. So this particular line item, when you look into the LOPA sheet, it will be numbered as SIF001, SIF002, SIF003 or something, or it may depend on the plant documentation wise. So this is one scenario. Initiating event, the event that initiates the sequence of events that leads to the undesired consequence. The event that starts the scenario or determines how often it is occurring. This is what I told. Fuel gas pressure going high due to control valve failure. It's one scenario. So this is control valve failure is an initiating event in my previous definition. Independent protection layer. A device, system or action that is capable of preventing a scenario from progressing to the undesired consequence regardless of the initiating event or the performance of any other protection layer associated with the scenario. We have seen about the independent protection layers in earlier presentations also. There are multiple protection layers in a process plant, starting with the normal control with the BPCS system and operator action to alarm, and next safety instrumentation system protection layer. Next comes pressure relief valve, rupture disc, like this mechanical safety devices protection, and then the plant dikes, etc., and community alarm, like that. So each one is acting independently. That's why it is known as independent protection layer. Okay, SIL values. Now we are in this table, we are seeing the SIL values starting from SIL 1 to SIL 4. It is being tabulated over here. SIL 1 is first safety integrity level is a measure of safety system performance. This is being done when the initial calculations are being done for the safety system before its installation. So SIL 1 means the PFD, probability of failure and demand. It starts from point, it is greater than 0.01, 10 power minus 2, and less than 0.1. This is the PFD average for SIL 1. Actually, now all our plants are operating in a low demand mode. There is another continuous mode or high demand mode also, which is for aviation sector and different sectors. Here, that is calculated in the probability of failure hour. Probability of failure and demand, this probability of failure per hour. This is what I mentioned. It is starting from 10 power minus 6 to 10 power minus 5 for the SIL 1 category. And SIL 2, for example, it is 10 power minus 3 to 10 power minus 2 in a low demand mode. SIL 3 is 10 power minus 4 to 10 power minus 3. And SIL 4 is 10 power minus 5 to 10 power minus 4. Similarly, the values for the continuous mode, it is in probability of failure per hour. It is described over here. In the process industries, we will be focusing about the low demand mode of operations only. So, we give more importance to these particular values for each SIL category. Okay. What does SIL 2 integrity mean? Failure of probability of the SIF. It is starting from 1 into 10 power minus 3 to 1 into 10 power minus 2. This is what tabulated over here. It is starting from 1 into 10 power minus 3 to 1 into 10 power minus 2. This is a PFD average. And failure probability of the SIF is 0.001 to 0.01. This is the equivalent mathematical value here. And the SIS, what does it mean? The SIS will fail on average once every 100 to 1000 times when any SIF is needed. There is a probability of failure that can happen every 100 to 1000 times. Whenever there is 100 demands, minimum starting from 100 demands to maximum 1000 demands, there is a probability of failing ones. That is called SIL2 integrity. Similarly, what is SIL3 integrity? For SIL3, it is starting from 1 power 1 into 10 power minus 4 to 1 into 10 power minus 3. We are saying the same over here in this table. So this is the range. And failure probability is again 0.0001 to 0.001. This is the failure probability, and the sys will fail on an average every 1000 to 10,000 times. Whenever during the demands come from starting from 1000 to 10,000 times, there is a probability of one failure. That is known as SIL3. Three forms of proof are required to claim that a SIF achieves a particular integrity level. How do we measure integrity? That is, devices should be approved. That should be approved suppliers list or SIL certified. The instruments and valves which are being used in the safety instrumented system, they should be from approved suppliers and manufacturers. As we have seen in earlier presentations, there are different certifying agencies known as XCDA or TUV. They are the people who give the certification for the safety instrumented system equipments, which means instruments, logic solvers, and final control elements. So every manufacturer who is producing the safety instrumented system related sensors, final control valves, and logic solvers, they need to get certified, and they have to again abide by the international standard like IEC standard, ANSI standard, etc. that approvers who are doing the certification. And fault tolerance requirement, this is how long and how far the instrument can capable of handling the fault and probability of failure and demand. These are the three forms of proof that are required to achieve the particular integrity level. First, we are giving a brief description about the previous 3 points. The first, the devices should be user approved for the operating environment, application, and integrity level. Components of new safety instrumented system should be selected to meet the SIL requirements and be listed in the approved suppliers list. Else meets the criteria of proven in use means the same instrument, same type of instrument being used in a different plant which is having an identical installation, meaning it is lying in the similar geographical zone where the ambient conditions, environmental conditions are almost typical. So whatever the instruments being used in the Western world, Western countries, cannot be 100% equally adapted or it applied in the similar kind of industries in the Asian region or Asia Pacific region, etc. Because the weather conditions, environmental condition, these are all totally different from the Western part of the world to the Asian part of the globe. So second, the device subsystem should meet the fault tolerance requirements. This is the second point what we discussed over here. They should meet the fault tolerance requirements. And third, the overall SIS should achieve the target probability of failure on demand for a demand mode system, or if the SIS is operating in a continuous mode, it should achieve the target frequency of failure necessary to meet the integrity level. So this is the probability of failure and demand. It has to meet that probability of failure and demand based on this table, whatever we have seen for each categories of SIL1, SIL2, SIL3, SIL4, etc. So these are the main parameters to ensure that the safety instrument system achieves that particular integrity level. Okay, now next one is probability of failure on demand, PFD. The probability of a system will fail to perform in a specified function when it is required. Whenever there is a demand for a valve to close, it should work. I mean, the instrumenter should be healthy without any leak, and the solenoid should operate. Solenoid should get because it is de-energized system mostly in the emergency shutdown systems. In the safety instrumented systems, the solenoid should get de-energized and it should allow the air to get vent. By that, the main valve to get closed. So if there is any component failure, like there is a air filter regulator leaking, so which may eventually lead to air leaking, and the valve cannot close even though the solenoid valve is working, or the solenoid coil is damaged. So it will receive the power from the logic solver, but it will not operate. And there could be some other mechanical failure on the actuator part or spring part, etc. So this is the probability of failure and demand. Whenever a demand is placed on the instrument, and there is a probability how much time it can fail. Probability of failure on demand for each system safety instrumented system function shall be equal to or less than the target failure measure as specified in the safety requirement specifications. In the safety requirement specifications, these things will be tabulated and the target failure measure will be tabulated. So that has to meet each components in the safety intermediate function has to meet this one. They shall be verified by the calculations. There are separate calculations to understand about the seal integrity level and quality failure and demand, etc. So that has to be verified. And the overall PFD of this function, we are talking about PFD all times, probability failure and demand. How does it has to be evaluated? The probability failure and demand, it's not only the sensor. There are three main components to operate on the safety instrumented system. One is sensor, another one is logic solver, another one is the final control elements. So the probability failure and demand, it should be for the whole system. Sensor, logic solver and final control elements. The result, we see PFD of the system means it has to be a combination of sensor, logic solver and final control elements. As a thumb rule, the weightage for sensors is 35%. So this all put together should be 100%. The sensors weightage will be around 35%. Logic solvers will be 15%. These are all electronic components. They are housed in an electronic control room, or it is called as a control cabinet room or marshal room, whatever it is. So they are housed in a safe environment, and the processes are having redundancy, so the probability of failure is very less. And third one is final element. Final element is having more mechanical components, like we discussed earlier. It is having a solenoid, or it is having a actuator, maybe having some booster, volume boosters, or some vent valves, etc. So the components are more in the final control element part. And some cases may be having positioners, some valves may have some partial stroke testing device, like that some device are there. So there are multiple components involved. So the probability of failure on the final control element part is more. That's why it is given a higher weightage of 50%. So this 35 plus 15 plus 50 put together, it is 100%. This is a total failure probability for the particular SIF. Okay. How do we understand about the probability failure demand? This is a simple equation for an instant PFD for a CL1 system. This is PFD of PFD is 1 minus e power minus lambda into t. Lambda is the failure rate per year and t is the time constant. PFD is a function of the device failure rate and time. As the time goes on, if the device hasn't failed it, its probability of failing is increases, because every system is in the operation. They are subjected to continuous service. They are drawing the process. For the sensors, they are drawing the process fluid or process gas to do the measurement. Also, it is being affected by the outside ambient environment, and the ambient may be hot weather or cold weather in some countries, or it could be some dusty weather. Some areas it is having a lot of moisture, like that they are subjected to different weather conditions, and there could be some areas with snow also. They will be provided with some warm streamline jacketing, etc. And some areas are having continuous rains, so they have to be protected. The instrument has to be protected. So that's why there is a proof testing. There is one more testing requirement known as proof testing, which is being calculated and provided for each instrument based on the number of sensors or number of final elements available. So they have to go through the proof testing requirement. So time goes on and the instrument is still healthy and it's working, there is a probability of failing is getting increased. So this is one concern. Operation and maintenance has to take care and do the regular proof testing and ensure that the instruments are healthy and work as good as new. Okay, if the mean time to fail is 1 year, then 10 years probability of failure will be virtually 100%. There is one more parameter known as mean time to fail. So if it is 1 year, then for the 10 years, the probability of failure becomes 100%. So that has to be taken care by the maintenance people. A component without repair inevitably reaches the failed state. So that's what the testing, proof testing has to be done whenever any component. For the metal valves, there could be a lot of internal o-rings, mechanical seals, etc. available inside the valve part and also on the actuator part. They have to be replaced at the routine intervals. Say, for example, if the manufacturer is recommended for 5 years or 8 years interval, that has to be those seals and o-rings like that has to be replaced. Otherwise, due to the weather conditions, they may get deteriorated and fail at any point of time. So that has to be ensured by maintenance teams, and the records has to be kept. This is a different topic, like a documentation part. So the component is running without any repair, so then it is a probability of getting into a failed state is quite high. That has to be avoided by the operation and maintenance teams. So for the safety instrumented system, higher focus has to be given, and the maintenance and proof testing has to be done as per the calculated tables. So this is a part of the maintenance stream and it has to be recorded. Okay, thank you. Hello everyone, I am going to make a presentation on Introduction to Safety Requirement Specifications, SRS. The video is being taken on behalf of InstrumentationTools.com and AutomationCommunity.com. Kindly watch and subscribe to the channel. Safety Requirements Specification Introduction. SRS. This details the entire steps being followed in safety instrumented system life cycle. SRS describes the entire steps being followed in a safety instrumented system life cycle. SRS form gives full view of the SIS design, configuration of sensors, logic solver and final control element, and which discipline to be responsible for what kind of action, etc. So this details all the requirements and the multiple disciplines being involved in using the safety instrumented system and their inputs and actions required. And those are detailed in the SRS forms. International standards IEC 61511-1 details the requirements of SRS. So we'll just continue about the SRS requirements. The IEC 61511 standard requires the user to create a safety requirement specification for a safety instrumented system that incorporates all the analysis done during the risk assessment, HAZAP, PHA and LOPA reviews. HAZAP stands for hazardous operability, PHA stands for process hazard analysis, and LOPA stands for layer protection analysis review. So the SRS has to be developed based on the study of HAZAP, PHA and LOPA. This will be done during the initial conceptual design engineering stages of the projects. The SRS falls into two types. An initial conceptual SRS, often referred to as process safety SRS. The process safety engineers along with the plant operation engineers or the plant designers, that means licensors who are involved in the process design, they will sit together along with the automation or instrumentation discipline, maintenance discipline, and then prepare a SRS. And a detailed design SRS which contains all the detailed information. The detail means, conceptual means they will go into the basics based on which scenario, what action has to be done, what is the possibility of initiating event, and what is the possibility of the different protection layer being protecting the particular scenario. So based on these details, the initial conceptual SRS will be formed, will be developed, and then the second step, the detailed design SRS which contain all the design information. There the inputs about the type of logic solver, type of sensor, type of final control elements, and process safety time, heat leakage rate, like that many inputs are all there. Those things will be updated in the second step. SRS form is a detailed Excel sheet containing complete information of the SIS applicable for the particular project. For any project involving SIS, shall form a team from production leader, HSE leader of the respective plant together with the certified safety instrumented system coaches along with the design lead, maintenance representatives and a technology center expert who is well versed with the plant operations. Here HSE stands for Health, Safety and Environment. Each process industry, they will be having one HSE department which is known as Health, Safety and Environment. They are the one responsible for the safety of the plant and as well as the employees' safety and any visitors because arriving at the plant and leaving the plant, their safety, everything has to be controlled by this team. So this is the team formed to prepare an SRS form. Information shall contain complete SIS lifecycle study, major points per below details. So what are the things available in the SRS form? This is SIS design information, SIS verification, SIS validation and commissioning, reviews and approvals. Different disciplines are involved in this step. SIS registration, documentation in plant library. So these are the multiple steps being available and has to be inputted while developing the SRS form. Safety requirement specification form shall be the basic document for design, installation and commissioning of the SIS loops. This SRS form shall be part of the engineering deliverable for all the projects which involves new addition of SIS safety intermediate system or modification of any existing SIS loops across the plant. Actually, the SRS is required for all the safety intermediate system available across the plant in different subsections of the plant, and as and when any existing facility being upgraded with a new safety intermediate system loop. So in those cases also SRS form has to be filled. SRS form shall consist of various sections, section 1 to 12, and each section shall be updated by different personnel involved or different personnel identified role profile per plant manager and department leader. So the section 1 to 12 has to be done by different disciplines. However, it is mandatory that updation of different sections of the SRS form shall be carried out in sequence. Like section 1, 2, 3 up to 12, it has to go in a sequence so that all the relevant information needed for the safety intermediate system and to maintain its healthiness and to maintain the life cycle will be detailed over there in the SRS form. Here we are seeing one sample of SRS form. So what are the things it's there? SIF identification and references, hazard and risk assessment and process details. And there are other sections also due to the space limitation. I just briefed the quick sample a part of the SRS form. It looks similar to this one. So in the SIF identification and references, first point will be SIF name and number. So the unique name or tag number of the SIF will be inputted over here. That could be SIF 001, SIF 002 or SIF A01, A02. This is according to the plant documentation philosophy. And the documentation date, the date of creation of SRS. Revision, any revisions being updated, that has to be input here. SIF description, the describe how the SIF should work, its function and how it will prevent a dangerous scenario to develop. How it can prevent a dangerous scenario, that has to be inputted over here. P&ID, piping and instrumentation diagram reference, that has to be inputted here in this field. H and RA reference, this is hazard and risk analysis reference. From the, this is to be available from the PHA process hazard analysis document. And other references, any other relevant references which is relevant to the particular SIF can be included over here. And the next part, this hazard and risk assessment. Here hazardous event has to be described. Describe the hazardous event for which the SIF is needed. This can be from a process hazard analysis like ASAP and LOPA. These are the two different tools. So the input on this field can be from one of this, the safe state of the process over here in this field, and expected demand rate. How often this scenario will develop if there are any no safeguards present. So that will be inputted over here. How much time it is expected to happen. And the process details, process safety time. This is a field they have to mention for each hazardous events or something. What could be the safety time to recover back to the normalcy? Assumptions and calculations define the period of time between a failure occurring in the system and the occurrence of the hazardous event if the safety function is not performed. So, if the safety did not come into picture, the hazard can get on expanding. If the particular protection here did not act and bring back the process to the normal condition, to the safe operating limit, it exits to the next level and the next layer of protection will come into picture. The next layer also having some issue, it further express to the further next level, like that it can expand. So that details which is the possibility of the next level protection has to be described over here. Allowable leakage rate of valves. We are going to talk about the final control elements valves. Those valves need to have a leakage rate. This is, they can allow only certain amount of liquid or gas as per the seat tightness conditions. That has to be inputted over here. Here again, the assumptions and calculations, if any, has to be mentioned. Define the maximum flow that can leak by a valve used as the final element. So these are the part of the SRS form, and there are multiple sections involving the design specification, type of sensors, leakage rate, etc., etc. So all these things has to be inputted. It is an Excel sheet type of a template. Okay, SRS in detail. As in any requirement specification, it is essential to ensure that the SIS design information is properly conveyed to the designer and avoid any potential for misinterpretation of the requirements. So all the details necessary for developing this SRS has to be conveyed to the designer who is involved in the design of the project or particular system. That has to be conveyed so that all details will be inputted properly without any error. As far as possible, avoid jargon and or three-letter acronyms. Three-letter acronyms is another requirement. In the safety instrumented system, SIS is itself an acronym for safety instrumented system. PFD stands for probability of failure and demand. SIL stands for safety integrity level. HRA stands for hazard risk analysis. MTF stands for mean time to fail. Like that, many acronyms are there that has to be clearly described. TLAs three-letter acronym are used. There could be some four-letter acronyms also there, but in general, most of them are three-letter acronyms. They are used. Then a glossary of terms should be included to assist in comprehension. Another very important requirement is that the quality of the document shall be in such a way that reader can efficiently understand and extract the information. Whoever is going to go through the document can easily understand and extract the required information. So that is also a vital factor. IEC 61511 standard is a performance-based standard that is all about the performance of the SIS and reducing risk. So it is very clear about what SRS should contain. All the requirements for safety instrumented system and its associated safety instrumented function. So the specification should contain all the requirements about the safety instrumented system and the relevant safety instrumented function which is going to perform. It should be remembered that the SIS consists of one or more safety instrumented functions which can consist of a combination of sensor, logic solver and final control elements, including all interfaces and sources of power. So the SRS needs to define two sets of criteria for each shift. There are multiple safety instrumented functions involved in some plants, so which may same have sensors, logic solvers and final elements. So all the details has to be clearly marked. So the set of functional requirements we see. Set of functional requirements and a set of integrity requirements. This is what the two sets of criteria for each shift we have mentioned from the previous slide. One is set of functional requirements and second is set of integrity requirements, which mentions about the safety integrity level, target, etc., indicating the amount of risk reduction required to be achieved. So which is a measure of the dependability. So they should indicate the SIL level required. SIL level required determines the amount of dependability whenever any hazard scenario happening and the safety instrument system are involved to do the mitigation, protect that hazard scenario. So how much can be dependable? That is to be mentioned over here. Importance of SRS. So now we understand about the SRS requirement, what is SRS and SRS requirement, and SRS forms in brief, and what are the inputs and who are the participants involved in the SRS, developing the SRS, like a conceptual SRS and detailed design SRS. Those things have been seen, and different requirements of inputting the relevant information from the ASAP or ASAP study and PHA and LOPA study has been described. And now in this slide we are going to see the importance or criticality of SRS. So for each standard, each specification, there are multiple requirements and needs. So one need to understand why it is important or critical so that the applicability can be well understood. The UK's Health and Safety Executive conducted a study in 2015. This is a bit longer ago, but anyway, this is data available regarding the accident causes involving control systems and concluded that 44% of the causes were related to specification issues. So the team has studied the different kinds of hazards and accidents wherever it had happened and came out with a decision that about 44% of those such accidents with an instrumentation involved are due to the specification issues. So the specification has to be very clear so that the designer, installation team, commissioning team and as well as the maintenance team is the most important. They are very clear to do the proper installation and further maintenance, as well as operation team to identify and mark wherever the hazards are there. So this has to be clearly mentioned. Otherwise, the probability of the accidents or probability of hazards not being properly mitigated getting increased. Having a poorly or ill-defined or vaguely structured specification will lead to increased risk, since the SIS design may not meet its intended safety targets. So why safety systems are involved? These are being built in the process facility, which is handling a lot of hydrocarbons, lot of chemicals and flammable material in the process industries like refineries, oil and gas plants, chemical plants, power plants, etc. So they are installed to overcome any hazards happening. So anywhere the design shall be very properly done so that the chances of hazards getting will be avoided. Therefore, for the SIS, there shall be no room for misinterpretation, and all information in SRS to be clear and specific to meet safety requirements. So this is what time and again is mentioned. All the specification on the installation details, the validation and the verification, commissioning information, everything to be detailed very clearly so that no ambiguity or no mistake is being done during the engineering stage, design stage and commissioning stage, and further it is maintained as per the standards requirement. So because we are seeing about the requirements of the safety system, which means it is protecting the people, plant, equipments and environment around the project area. So every specification and every point needs to be taken care thoroughly to overcome, to avoid any mistakes and to mitigate any hazard scenario if at all happening in the plant. Thank you very much. I am going to make a presentation on safety requirement specification. This topic will be on the SRS, safety requirement specification process. This is the part 1 of the SRS process. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. Safety requirement specifications. We'll go over the basic references. International Electrotechnical Commission IEC, ANSI, American National Standards Institution and Instrument Society of America. These are the different agencies, international agencies for various standards. Again, for the safety instrumented system, these are different standards: IEC 61508, 61511 and ISA S84. IEC 61508 defines the requirements for manufacturer of SIS components, valves, sensors, etc. So the 61508 is mainly for the manufacturers defining the standards. IEC 61511 is the safety instrumented system for the process industry sector. This is for the process plants. How the safety instrumented system need to be installed, needs to be commissioned, validated, proof tested during the regular intervals and maintenance of the safety instrumented system. ANSI/ISA 84. This is an equivalent standard for IEC 61511. This is being adapted in different countries like Americas. I will go over the SRS now. SRS is having 12 sections. The concept is that when a section is completed, the document is sent to the next concerned personnel to continue filling out the form until the complete SIF is specified and approved. SRS is for each SIF, so the 12 steps has to be completed in sequence one by one. Whenever first step is completed by a particular department, particular personnel concerned, the next step go to the respective department, respective personnel to attend. SRS work process to be followed, and SIS needs to be verified and validated before placing it in service. Before placing the safety instrumented system in service, the SRS need to be developed, steps has to be identified and entered. Okay. Adequate details shall be provided in SRS like MERT, MELR, bypass requirements, desired proof test intervals, etc. MERT stands for maximum allowable repair time, until how much time any instrument, if it goes into failure, within how much time it has to get repaired and put it back in service. MALR stands for maximum allowable leakage rate. In the safety instrumented system valves, there is a certain definition to understand about the valve leakage requirements. So that has to be identified. Maximum allowable leakage rate has to be identified. The bypass requirements, decide proof test intervals, etc. and also need to be detailed in the SRS form. Second one is periodic proof testing to be done as per the safety instrumented system requirements. Complete documentation, the electronic copy shall be stored in the plant's library. This is for the future reference and updates. We'll go over the SRS steps now. In the step number 1, operation representative process safety design engineer is to identify and define the hazards related to the project during feasibility study of a project. During feasibility study, the operation team need to sit together and identify the hazards. In step number 2, for any projects, the need for process hazard analysis and layer of protection analysis is to be identified in the front-end engineering and documented. During any project development, during the initial engineering, front-end engineering, the process hazard analysis and layer of protection analysis has to be identified. In the step number 3, if there is a need to carry out LOPA, then the LOPA study has to be conducted by the plant operations representative. As part of this step, section 1 of the safety requirements specification form is to be filled by the operation representative and plant safety engineer. Any process which is requiring a LOPA to be conducted has to be identified and the section 1 has to be completed. In step number 4, from the LOPA layer protection analysis document, the requirement of sys loops, cell target levels need to be finalized in the front-end engineering itself. In step number 5, once the sys loop is identified, the instrumented protective systems need to be detailed to ensure appropriate functionality and capability. Instrumented protection system need to be detailed. In step number 6, this is to ensure the required safety instrumented system is well understood and meets the functional requirements of the scenario. This has to give a clear detail which may give a clear clarity about the safety instrumented system implementation and ensure the hazard is being protected using this for the particular scenario. So key points for developing SRS. We'll go over the key points. Do not treat SRS as any document for every instance because it's an evergreen document and any safety instrumented system addition, modification or deletion needs to be updated and captured in this document. So it has to be like an evergreen document and should not be think as a small document. Have a complete document outline and where practicable, a complete and well organized SRS for reference. The document should be clean for easy understanding. Start the SRS development early and do not allow engineering and procurement to start until the SRS is completed because it is specifying the safety instrumented system after the design. So that has to be identified and updated. Once this is done, exercise done only, the engineering for the rest of the process plants can start and the procurement activities can start. Projects should clearly identify the deliverable dates for the SRS issue, review and SRS approval. They have to give a clear timeline for the completion of the review, SRS issue review and SRS approval. Rigorously enforce these as a milestone upon which the start of other engineering is contingent because development of SRS to be completed well ahead and then the next phase of the process can be taken up. Do not include SRS development in parallel with the detailed design. As explained earlier, it is better to identify based on the cell category, based on the working configuration, the type of instruments, the number of instruments has to be identified and updated. So it should not be done in parallel to the process engineering. Make sure that SRS contains all IEC, ISA requirements so that that has to meet all the IEC and ISA requirements. Use IEC as ISA SRS requirements below table as a checklist and make sure that these requirements are clearly stated in the body of the SRS. So that has to be updated and clearly marked. Further, there are more points. Do not make the users of the document dig for the information. Focus on functional requirements and include engineering details only when they are required to meet functional requirements. SRS is the specific document for the safety instrumented system functions. So it has to be pinpoint and very clear and easy for the people to understand and do the required changes. Do not attempt to make the SRS as a repository for the design documents and specifications. That means it should not be taken as a reference document for the design part. Okay. Do not expect design documents and specifications to substitute for the SRS requirements and specifications. This is what we told earlier. The design documents and specification cannot substitute the SRS because it's altogether a separate document based on the IEC ISA standards, which has to be maintained for the facility having the instrumented systems, safety instrumented systems in service. SRS requirements based on the IEC ISA standards. In description of safety instrumented function is necessary to achieve the required functional safety. This is one requirement. Requirements to identify and take into account all common cause failures. Any procedure, definition of safe state of the process for each identified safety function. Definition of any individually safe process state when occurring concurrently shall create a separate hazard. That is multiple lift fire systems. This is one example. So, different individual safe process states has to be identified and detailed. Assumed sources of demand and demand rate to cipher. What are the type of different demands that can happen, and the demand rate for the particular safety instrument function has to be identified. These are the different requirements. Requirements of proof test intervals that has to be detailed. Response time requirements to SIS to bring the process back to a safe state. Whenever any hazard has happened, and how the safety instrument system is acting and behaving, and bringing back the system to normal operation. This is another response time. Okay, safety integrity level and mode of operation for each SIS. Each SIF, safety integrity level like SL1, SL2, SL3, and mode of operation. This is mostly will be following the low demand mode that has to be identified. Description of SIS process measurements and their trip points. Description of SIS process output actions and criteria for the successful operation, like requirement of tight set of walls, etc. has to be met. Functional relationship between the input and output, including logic. What is the relationship between the sensor part as an input to the safety instrument system and final element as an output? So that has to be identified. Function relationship between input and output include logic is we saw. Requirements of manual shutdown. Any manual shutdown requirement has to be identified. Requirement of energize and de-energize to trip. How the particular action is being achieved, like a de-energize to trip is a common one, or it can be like an energize to trip, that has to be identified. Requirements of resettling SIS after shutdown. So whenever any shutdown happens, it will take some time for the process to get shut down, complete shutdown. So, and then it requires certain time to come back into operations. So that resetting time has to be identified. Maximum allowable spurious trip rate. So whenever any incident happens, how much time it can do, and the spurious rate has to be identified. Failure modes and desired response of SIS. So different failure modes has to be identified, and what should be the response of the SIS has to be identified also. Any procedure requirements relating to starting of SIS. So the safety instrument system sometime may require some bypasses to do and bring back the process back into operation. And this will be depending on the type of equipments to be available in line, or any valves that needs to be stroked, etc. during the startup. Those things has to be identified. All interfaces between SIS and any other system. It has to specify the detail about the safety instrumented system and interface with the BPCS, HMIs, operator, HMI, etc. Description of modes if operation of the plant and identification of if to operate with each mode. Startup, shutdown, normal operation, plant operation, that has to be identified. Application software safety requirements has to be identified. Requirements for overrides, bypass, inhibits, that has to be included, and how they will be cleared. In case of any override or bypass has to be activated, how it will be cleared. So this is also a part of requirement. Specification of any action to achieve or safe state in the event of faults being detected in the SIS. If there is any specific faults has to be identified, that has to be mentioned. So how can it come back to the safe state? That also has to be mentioned. Mean time to repair MTTR, which is feasible for the SIS, has to be identified. Identification of combination of dangerous failures of output states of SIS. So there could be multiple dangerous failures. The details has to be updated. Extremes of environmental conditions that are going to be encountered by SIS. Identification of normal and abnormal modes for whole and part of the plant. Definition of requirements of any safety instrumented functions if required to survive major accidents if any. This is identified. And this is a complete project, and this is a complete step, and the different requirements based on the IEC 61511 and ISA 84 for developing the SRS. Thank you. Hello everyone, I am going to make a presentation on safety requirement specification, step by step SRS process. This is part 2. This video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. Just we will understand about the basic references for developing the SRS. International Electrotechnical Commission, International Electrotechnical Commission IEC, ANSI and ISA. These are the different standards agency who are designing the role of the safety requirement specifications. IEC 61508, this is one standard. It is for the requirements for manufacture of SIS components, valves, and sensors, etc. So this is basically for the manufacturers who are producing the SIS related components like valve sensors, etc., as well as logic solvers. Okay, IEC 61511, this is a safety instrumented system for the process industry sector. This is another standard. And ANSI/ISA S84, this is an alternate standard for IEC, which is equivalent to IEC 61511, being adapted in Americas. In the earlier presentation slide, we saw about the first 6 steps of the SRS process. In this presentation, we will see the next 6 steps. Step number 7 is for proper operating procedures, and relevant training modules need to be established to ensure that the SIS shall be operated and maintained properly. This is the step. 8. Plant instrumentation automation engineer to review the software application requirements for the proposed SIS loops. The automation engineer has to review the software application software with respect to all safety instrumented system loops. Step number 9. The components of the SIS loops are to be field tested as part of project commissioning. Operation personnel in charge of the project is to take the responsibility for the coordinating different plant functions to complete SIS loop checks. Each instrument, before it is going to be put in service in line, that has to be verified for the perfect cabling without any earthing or any other fault, and confirm the sensor which is going to sense the process parameter reading from the sensor reaches to the control system and then to the operators in the HMI panel. So this is known as a loop check. So for each of the instrument, not only in the safety instrumented system loop as well as in the normal basic process control system loop, that has to be ensured, and this is a part of the project commissioning activity. Okay, in step number 10, the SIS application software must be simulated to prove it is functionality before being installed in a running plant. Instrumentation automation engineer shall ensure the same and complete documenting the simulation test results. The application software has to be simulated. There is a tool in the application software program, or there will be having an analytical tool using which the real process condition can be simulated and tested. The logic can be tested whether it achieves the desired intent. This is done by instrumentation and automation engineers responsible for the respective plant. Step number 11, SIS coach shall conduct SIS assessment against specification by code review prior to initial operations. There will be a safety instrumented system coach, or they can be named in a different designation for different industry. They have to review the SIS assessment they have to do the SIS assessment and review and approve the SRS before commissioning. In step number 12, the SIS loop is to be validated in the plant installation, including process equipment, to demonstrate that it meets all respects the required safety functionality. So, in the step number 12, the loop has to be validated, because we are going, supposing particular safety instrumented system loop is doing a level measurement on a process vessel. Whenever the level in the vessel goes above 80%, the respective safety instrumented system valve, which is admitting the process fluid into the tank, has to be closed. So this is one complete cycle. The sensor sensing the high level, giving a signal to the logic solver, and logic solver is doing the mathematical logical functions internally and giving a command back to the valve to close it. So this steps together known as a cycle. So, and this has to be ensured. How to do that? So either the tank has to be filled with the equivalent fluid. If it is an hydrocarbon, may not be possible. So they need put with an equivalent fluid or water or something, and then raise the level and see it reaches 80% level, and at 80% level the sensor gives an indication along to the logic solver. So logic solver do the internal arithmetic and then sends the signal back to the valve to close it. This complete testing is known as validation. That has to be done for respective individual loops. These are the 12 steps to be followed during the safety requirement specifications, and we will go over some development guidelines. The SIS requirements shall be expressed and structured in such a way that they are clear, precise, verifiable, maintainable, and feasible, written to aid comprehension and interpretation by those who will utilize the information at any phase of the life cycle. So that has to be very clear and precise, so that the users and engineers who are going to do it on a regular maintenance has to understand and apply it during the entire plant life cycle. So make sure that SRS identifies the critical owner requirements for design and installation standards and provisions required for robustness and maintainability. Where possible, state design and installation requirements in a separate site design requirements and practice document cited for inclusion as minimum design requirements by the SRS. So the design and installation standard requirements has to be updated and that has to be reviewed. Include the basics for set points, even if this basis is a comfortable operating margin above or below a limit. If the set point is based on equipment limits does not exceed value, make sure that it is clearly identified. Do not include detailed engineering design data in SRS. Do not revise SRS multiple times unless there is a real change that affects the required functions and performance of the SIS or its safety instrumented function SIFs or related functions. Ideally, a SRS would only go through 3 times or maximum 4 revisions as it is developed. So this is the maximum allowable. So it should not, for every small change, the designer, design engineer or plant safety expert, they should not go and keep on updating the document so that the continuity will be lost. So there should be minimum revisions before finalizing the complete documentation. We are having multiple steps and guidelines to develop an SRS, and what we are going to gain out of it. So this is the value of data-driven SRS. Better method of doing SRS is to use a data-driven SRS. In a data-driven SRS, personnel who are knowledgeable and experienced with the SRS preparation define the complete requirements for a SRS contents. A project that is generating the SRS then uses the database to enter the required data and generate SRS report. SRS is complete with a well-designed database that has all the fields filled out with the quality data. See, basically, this is a basic design data and applicable for the safety instrumented system. So it has to have a complete, precise information which shall give a clear-cut picture for the people who are going to use it. It may not be the same person who was designed, who was involved in the design, may be continuing in the same plant or same job. He may be leaving the organizations and a newcomer may join. So whoever is going to do the regular activity during the entire life cycle has to have a clear-cut picture. That's why the data-driven SRS means all the data are there in electronically available, so that any person who is having a background knowledge of the safety requirement system and the safety instrumented system can understand and work on it. PFDs of common designs can be automatically computed from failure parameters entered for SIF inputs and outputs. That means probability failure on demand can be automatically computed from any failure that is happening. Okay, it is then easy to maintain or identify where gaps exist. Use of data-driven SRS has the following benefits to owner operator organizations and project teams. What it will do, it will drastically reduce the cost for SRS development and management, because there need not be a big team doing the SRS development and the design. They can comprise of smaller teams and complete the activity. A well-designed SRS data structure with reasonable examples reduces SRS development times to hours rather than weeks or months. Personnel knowledgeable in SRS requirements and preparation of SRS contents, layouts, and format define a standard that becomes a standard for the organization. Actually, the people who are working on it, they should have a good, adequate, thorough knowledge, so that the development, the different inputs required can be made easily for the people who are going to use it and the maintenance teams. SRS consistency and completeness can be assured, and missing information can be readily identified. SRS data for SIS and SIFs can be copied from other SIS and SIFs in the database. Engineers edit for differences instead of creating from scratch, because once the database is available and the next SIF is similar to the previous one, they can just copy and paste and keep on editing it. Otherwise, it will take much time for them to do it from the scratch. SRS data has a single point of source and access. The latest versions are always available with the changes readily tracked. So tracking should be made available so that any changes has to be updated. SRS data is available to other steps of the safety life cycle. SRS data can be used to generate specification data for physical devices or linked to the LOPA scenarios upon which the safety functions are based. So they can generate a specification data for the physical devices or linked to LOPA scenarios upon the safety functions are based. Thank you. Hello everyone, I am going to make a presentation on safety requirement specification. This presentation topic will be on roles and responsibilities of various disciplines involved. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. SRS principle, we will just have a quick refresh of the SRS. There are about 12 sections in SRS that are to be filled out by various roles. The concept of the SRS safety requirement specification is when a section is completed, the document is sent to the next concerned personnel to continue filling out the form until the complete SIF is specified and approved. For each SIF, there has to be one safety requirement specification form which is having 12 sections. So whenever one section is completed by the respective person, it has to be sent to the next person who has to review, update, and then complete the section, thereby passing on to the until the last section is completed, and finally it is getting approved by the respective authorized plant manager or safety system leader authorities. There are many disciplines involved in developing this SRS. Below slides, we will look into the roles and responsibilities involved in the SRS. Here we will go through the roles and responsibilities, which may describe in referring to the different sections. Those are talked different steps. Those are talked in earlier presentations. So this is correlated with the complete SRS form. Operation representative and design engineer, like operation engineer, process engineer in the safety requirement specification form, whose name is mentioned or whose particular discipline or particular role is specified over there. His responsibility is finalizing the LOPA requirements for respective project, update LOPA process information into section 1 of SRS form, filling of the completed SRS form in plant documentation system library. They have three responsibilities: finalizing the LOPA requirements and putting it in the section 1, and finally it is after the complete form has to be put in the system library. And instrumentation design engineer, he has to update conceptual design information into section 2, 3 and 4 of SRS form, approving the conceptual design and sign off section 4 of SRS form, updating the final design information into section 5 and 6 of SRS form. These are the three different responsibilities that instrumentation design engineer has to follow. Instrumentation design engineer, he has to do provide the required data for registering SIS instrument in MIS ERP system. MIS stands for Management Information System, Enterprise Resource Planning System, like SAP and other tools are there. That information should include tag number, instrument details, and proof testing frequency. These are the different informations to be entered over there. And next one is maintenance supervisor and maintenance foreman. They have to provide required details to maintenance team coordinator for entering the SIS instrument, safety instrument system instrument, in testing plan in MIS ERP systems, resource required for testing, and maintenance tasks required for proof testing, expected duration of testing, and spare requirement. So each instrument testing may involve different roles. Some may require instrument technician, some may require instrument tube fitter to assist him. If there is any leaks, anything is found in the valve, they have to attend to it. Some may require electrical technician who has to work on the electrical relays in the switchgear if it is involving in the safety instrumentation system, which comes under proof testing requirement. So they have to identify the required resources exactly, and the task, different role have different task, those has to be filled out, and the tentative duration, expected duration of the testing, and if there are any spares required to be replaced for the instrument which is being tested also has to be included. Next one is plant instrumentation engineer. He has to update conceptual design information into section 2, 3 and 4 of SRS form, updating the final design information into section 5 and 6 of SRS form, verify and confirm field hardware commissioning, approve SIP and policies, and approve validation test and sign off section 9, 10, 11 of the SRS form. This is about the safety integration plan, and there may be some policies depending on the companies and their safety departments requirements that has to be entered, and provide the required data for registering SIS instrument in SAP. So they have to provide the details for the instruments that are to be registered in the ERP system. One such system is SAP. So they have to provide the tag number, instrument details, and proof testing frequency. So accordingly, as per the installed instrument of the safety instrumented system, with respect to the tag number, all the model number, range, type of instrument, everything will be entered over in the SAP system, so that whenever any spare requirement, anything is there, they have to procurement department will initiate the buying. Safety instrument system coach. So he has to review and approve final design and signs off in section 7 and 8 of SRS form. Secondly, he will verify and confirm field hardware commissioning, approve SIP and policies, and approve validation test and sign off section 9, 10 and 11 of the SRS form. Similar to the plant instrumentation engineers, instrument system coach will review and approve final design in section 7 and 8, as well as he will support in doing the hardware commissioning, approve SIP and approve validation test and sign off section 9, 10 and 11 of SRS form. Though the activities are similar, but instrument coach will have better knowledge and higher exposure into the safety instrumented system. So they will review and provide the required details, and wherever any corrections, any updations required, he will recommend to do that. Maintenance team coordinator, he is the one to register the safety instrumented system in management information system as well as ERP system, and schedule specific proof testing requirements. He is the one to register the instrument in the ERP system of the company. So these are the different roles led by different persons. and they have specific responsibilities to carry out. So according to the roles may be different companies, but basically the titles for each company may be different, but basically the role reflect to the responsibilities assigned to that such role who is doing the activity. Okay, we'll go over the SRS good practices. SRS, it is common practice and good practice to apply more focus on their effective implementation, and similar principles should be applied to safety system documentation, particularly those documents which have a potential to affect whether functional safety can be achieved. So time and again we are talking about the safety instrumented system. It is a critical for the plants because they are doing a protection activity against any hazard, any mishaps that can happen in the plant. So it is good practice to develop the safety requirement specifications during the engineering phase and test the instruments according to the standards and document it. The documents such as safety requirement specification should be given elevated status as being safety related, whilst any changes to the existing SIS or SIF and revisions to projects upgrades are being done, modifications to the SRS need to be given much more careful consideration. There may be some systems or some part of the plant which may require to add additional safety instrumented system, additional features and layers of protection, so which may involve adding more instruments. So any such changes due to any projects or any upgrades need to be documented, and all the modifications has to be captured, and a revised SRS need to be prepared. Thank you. Hello everyone, I am going to make a presentation on safety requirement specification, and this topic will be on SRS documentation and results. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. SRS documentation needs IEC 61511 edition 2 and ISA 84.00.01 require that a safety requirement specification SRS be prepared for each safety instrumented system. Clause 10 describes the requirements for the SRS. Clause 10.3.2 lists the minimum items that shall be addressed in the SRS, and results are saved electronically. So these are the different standards, international standards that specify the requirement for the SRS documentation. The first thing to know is that SRS is required to be before design starts document. The intent of the committees that wrote IEC 61511 edition 2 and ISA 84 was to ensure that the SIS requirements be laid out before design starts and to define the things required to be addressed during detailed design. It has to be a preliminary document during the stage of engineering so that all the required information shall be entered and all the necessary protection safety instrumented system details and their testing and their validation requirements, everything will be entered so that it is captured clearly during the project phases. Okay, the SRS is not a detailed design document. The SRS used to guide detailed design of the SIS, safety instrumented system, and then be used to verify that the design actually meets the requirements. It is a supported document. It's not a basic design document for the safety system, protection system and all. It will have its own topology and design principles based on which the sensors, logic solver and the final elements, configurations, the logic solvers, different type of logics or mathematical computations will be mentioned. And SRS is a supporting document used to do the safety instrumented system testing, commissioning, etc. SRS documentation needs any organization that does not require a complete SRS be prepared and approved prior to the start of detailed design isn't in compliance with the IEC, International Electrotechnical Commission, good engineering practices, and thus it is likely to be spending way too much money during the detailed design phase. So organization or company has to commit to do the complete documentation upfront of the project, failing which they may need to do sometimes re-engineering, which may require additional resources, or they may have to go for additional instrumentation, again which involves more time and money and giving higher cost for the management. If a SRS that conforms to the standards, the subsequent detailed design becomes a lot less expensive and is more effective. So if the SRS developed, once it is meeting to the standards, then the rest of the things will follow and the design and engineering process will go very smoothly. In order that SRS to be effective, there is a lot of learning that needs to happen. It is really a good idea to be able to have a quality SRS example to work from if you are developing your first one. So companies who are going to do the first time has to review and see the earlier completed projects, and they have to take it as a reference to do a new one. Otherwise, whenever we are starting to do with the new exercise, there may be some mistakes, may lead to time delay and more expense. And there are different elements to be taken care during the SRS documentation. SRS helping for hazard prevention. The SRS needs to clearly identify the hazard for which each of its safety instrumented functions is intended to prevent, and the functions that SIFs must perform. They have to clearly identify the SIFs perform what has to do. Operating modes. The SRS needs to define when the SIFs are required to be available and when they are not. The SRS need to describe how and when a SIF is put into service and how and when it is bypassed or removed from service. These descriptions need to be explicit and define what the detailed design needs to enable. So they have to give a brief idea in the SRS about the bypass requirement, when it has to be put in service, when that can be removed, like that and all. The brief descriptions has to be captured. SIF performance. The SRS must define the performance requirements for each safety instrumented function. IEC 61511 edition 2 and ISA 84 are big on making sure that SIF activities upon demand. SIF activates. Make sure that the SIF activates upon demand. So that has to be ensured. Okay. Device functional requirements. The SRS needs to define the performance expectations for field devices such as range, accuracy, response time, shutdown valve stroke time, leakage, certification for use. So these are the different parameters within the safety instrumented system that has to be taken care for the better performance of the instruments and valves. So the range has to be captured properly, accuracy of the instrument has to be taken care, response time, how quick the instrument has to work, that has to be entered, and shutdown valve stroke time. The valves, on-off valves which are acting as a final control element, may have some stroke time, that operating time, that has to be clearly mentioned. They have to go through some leakage requirements as per the APA standards, that has to be mentioned, and certifications for use. There may be requirement that the instrument and valves need to be certified to work in the safety instrumented system. Further we go on. Operation and maintenance requirements. The SRS needs to define the testing and verification requirements for the SIS and its SIFs, safety instrumented system, and its safety instrumented functions over the complete safety instrumented system life cycle. The SRS should define what procedures must exist. So that might be, there are different procedures within an operating plan, in a process plant. So the SRS will define what are the procedures required for the operation and maintenance of the plant. One is operating procedures and initial validation procedures, periodic test procedures, bypass procedures, performance data records. There is any system or instrument need to be maintained, and if there is a requirement to do a bypass, that has to be there, and performance data, how the instrument should perform, that has to be evaluated, those records. And periodic evaluation. The SRS does not include these procedures or periodic evaluations, but needs to identify the requirement, the procedures we developed. But the periodic evaluation, like proof testing, visual inspection and all, not be exclusively mentioned in the SRS form, but they need to give a reference to some SIF, some other documentation which will give the proof testing requirement, visual testing, visual inspection requirement, etc. Okay. These are the different checklists of the safety requirement specification form. So that has to confirm about the hazard prevention and the operating modes, the safety instrumented function performance, device functional requirements, safety instrumented system design requirement, operation and design requirement, maintenance requirements. These are the different items we saw in the earlier slides. SRS results. Now the form is developed and the results has to be verified. So there are different checkpoints SRS review to be taken up at multiple stages as below. And these are the different steps to be checked. After detailed design, check below the completion of specification, completion of P&ID review, review of instrument installation done as per design, review of design meets SRS and business requirements, any common cause failure points to be addressed. These are the 5 items to be verified upon detailed design check. Upon approval of design, review of specification and by instruments and logic solvers, installation of instruments, valves and logic solvers, preparation and review of process, application, test or code, write procedures and other documentation. So once the design is approved, the specification has to be reviewed and the instrument has to be bought as per the specifications. The instruments, valves, logic solver has to be installed as per the design, and process application code needs to be, that means application program needs to be reviewed, and procedures for different operations and maintenance has to be updated. There is some safety instrumented system coach for each plant. They have to do the review as below. Function, they have to ensure that functionality meets the specification and instruments are designed to the specification. All design changes properly documented, like P&ID, LOPA, ASAP study, etc. They are properly updated and documented. Enable or disable instruments. Whenever any instrument need to go for bypass, that has to be disabled. These things to be captured in the procedures which the safety instrument system coach will review. And manipulators such as temperature or pressure compensation, if any instrument need to go through the pressure temperature compensation, that has to be updated. Diagnostic instruments details has to be updated. So these are the different checkpoints the safety instrumented system coach will do a review. So why we have to do a detailed review? There are few requirements which necessitates to do the detailed review. Instead of just going as a one pass, it is better to do a review so that any rework can be avoided. It is recommended to do the detailed design reviews to avoid costly and resource consuming reinstallation, repurchasing or repetitive work. If there is any mistake, anything, there could be a delay in project schedule, which may call for a reinstallation, or if it is a wrong specification, which may lead to the different product than what should be installed. So it may call for repurchasing, which is going to take more time, and repetitive work. Again, preparation of the engineering drawings, preparation of the documentation, and preparation of the new logic programs and testing, everything is going to take time. So these are the things that can be avoided if it is taken in a proper way. The implementation verification tasks are part of the mandatory pre-startup reviews as per the international standard, which ensure that SIF hardware, software and operation procedures prepared clearly. For each of the instrument and equipment, there will be one startup procedure. Again, it depends on the company's standard and policies. So this is an international requirement as per the international standard requirement. So that has to fulfill the safety instrumented function, hardware, software and operation procedures to be prepared clearly. So that has to be made clear to avoid any mistakes, to avoid any rework on the safety instrumented system installation, testing and maintenance. So the beginning of the engineering phase, so these are the details to be taken care and properly entered into the SRS form, so that all the installations testing will go as per the procedures, which may also eventually reduce the rework. So these are the different points to be taken during the preparation of the safety requirement specification. Thank you. Hello everyone, I am going to make a presentation on Introduction to Common Cause Failure, CCF. This is a part of Safety Instrumented System. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. Common cause failure. We'll go through an introduction. Safety instrumented systems are to be designed carefully, taking into consideration many factors. Critical one is common cause failure, which may affect sys functionality severely. We will go in detail about the common cause failure and how it can impact the sys functions. A common cause failure can impact two or more separate elements, leading to a total system failure. Common cause failure opportunities are to be avoided by careful design, thoroughly studied to minimize as much as possible. Common cause is nothing but many instruments sharing a same tapping point, or there are multiple cabling going in a same cable tray, which can impact the measurement part and disturb the measurement of safety instrumented system. These are the details. A common cause failure can impact two or more separate elements, leading to a total system failure. For example, if two flow transmitters are connected to the same orifice flange, a plug could disable both the transmitters. I will explain you over here. See, this is a good practice to use only one instrument, one flow transmitter, using the orifice measurement, or this is known as orifice type of measurement, wherein flow is being measured. There will be an orifice plate installed over here in between these two flanges, and this is tapping. One is high pressure tapping, one is low pressure tapping. So from which there is a root valve. After the root valve, the impulse tubing is going to do the measurement on the transmitter, flow measurement on the transmitter. Ideally, this transmitter has to be separate. This tapping has to be separate for different transmitters. This is the correct way of installation. In some installations, there could be another tubing going to another flow transmitter. So that's what I mentioned in the previous slide. If there is any choking happening in this area, so it can impact both the flow measurements, which is known as a common cause. So the choking or any plugging in this area may impact the measurement on both the transmitters if they are connected together in one orifice flange. This is what mentioned here. Common cause failure opportunities are to be avoided or at least minimized. Since it is almost impossible to totally eliminate the common cause, industry typically assumes a common cause factor of 1 to 5% on most of the safety instrumented system probability of failure calculations. In the orifice example above, common cause must be adjusted up to 10% in the probability of failure demand calculations. This will result in an increased test frequency. So in the safety instrumented system calculation, we are going to do one more this thing known as probability of failure and demand. This is one parameter based on which the cell levels are calculated. So in this, the common cause failure factor is being considered, which is normally supposed to be up to 5%, can go up to maximum of 10%. So whenever we put a higher factor on this, which may call for a frequent testing and frequent inspection. Okay, common cause and independence are inversely related to each other. Perfect independence means there is no common cause. That's what, if it is a installation is similar to this is a perfect independence. So it is having no impact from second instrument or something. So measurement is going to be separate, but unique. So it is very difficult in the piping configurations in the plants to put a similar meter over here and making different connections and all. So thereby we need to go with a different technology or with the minimized measurement arrangements. But if a safety instrumented system calls for providing two instruments on the same process, then it is going to be a challenge. But since there is a rarely perfect independence when dealing with the hardware, software and people systems as related to SI safety instrumented system, common cause must be recognized, planned for and managed. So this is what it mentioned. It is practically very difficult to make a separate instrumentation, make a separate pipe tapping for different instruments doing the safety instrumented function. So there is always a challenge. So we have to go with the best engineering practice to have a minimum interference if there are two instruments going to be used for the same measurement, as well as they are going to be used in the safety instrumented system protection. So the engineering has to be done thoroughly, either to use only one instrument using this RFS flow tapping, another instrument like inline flow instrument, it can be a mass flow meter or vortex meter, like that, some other measurement having a different technology. Okay, this is another example of a level measurement in the tank. So here we are having two different transmitters. This is going to be used in the safety logic solver, which is a safety instrumented system, and another transmitter is going to be used in for the control and monitoring system, which is a basic process control system, BPCS. So here also it is very best practice to have two independent measurement instruments, so that there is no dependency, because that's why in the earlier examples also we have seen that safety instrumented system should be handled as independently. So this is a best practice and best installation arrangement for the safety instrumented system and a basic process control system. That's what is mentioned here. Ideally, sensor for BPCS and SIS shall be separate, so that any failure happening in this instrument or any trouble or programming error and the instrument, etc., will not have any impact on the safety instrumented system function, because this is depending on the other instruments, which is going to work continuously and make the necessary protection. Common cause failure. Safety instrumented system often employ redundancy to enhance reliability, but the intended effect may be reduced when common cause failures are taken into account. It is often assumed that a certain fraction of component failures will occur close in time due to a shared cause. Study on Norwegian refinery by safety experts. The results are based on a review of some 12,000 maintenance notifications from 6 different onshore and offshore petroleum facilities. It is found that the new beta values are higher than what is seen in many other similar installations. This was the correction factor, whatever you have mentioned, is very high compared to the industry standard. That's what is mentioned. This is by a study by a safety system experts on a Norwegian refinery. Beta factor indicates common cause susceptibility. It is a fraction of total failure rate that is attributed to a single cause in common with other typical installation in the group. Common cause failures can occur due to many types of events, such as manufacturing defects in redundant devices, aging components, severity of operating environment conditions, common process connections, and common support systems. These are the different chances of getting a common cause failure. These failures are referred to as dependent failures and are mostly commonly modeled using the beta factor method. Actually, this is a factor which has to be taken into consideration during our SIL and probability of failure on demand calculations. So wherever there is a need to go with the common instruments, the beta factor is going to be high and the probability of failure on demand is going to increase. So as far as possible, the sharing of instrumentation has to be avoided. But in spite of our best engineering, there could be chances that the instruments may fail due to this kind of issues, like redundant devices may fail due to the aging components or severity of the operating environment, etc. This is why the proof testing is another critical requirement as far as the safety instrumented system is concerned. Again, further going on the beta factor, the value of the beta factor is selected based on prior use data in the operating environment. The prior use data can be for a specific device technology. That's what we are talking. If it is going to be a flow measurement using a differential pressure type of measurement, this particular technology in which are the plants having ideal conditions has been installed, and the type of failures, any issues happened on those instruments can be taken as a reference. This is known as a prior use data. So that means verifying the type of failures in a similar environment in a similar conditions. Many plants use a beta factor between 1 to 5% when the devices are user approved for the application and good engineering practices are applied in the design and installation to minimize common cause failure. So 1 to 5% is the ideal one, and it is a good engineering practice. The beta factor can be substantially higher if good engineering practices are not followed. Like what we said in the previous example, if the instruments are not separate and they are using a similar tapping or in some other requirement, at least the valves they keep with the same valve for isolating both the transmitters and all, will have an impact. So those things are not a good engineering. Thank you. Hello everyone, I am going to make a presentation on common cause failure for the safety instrumented system. The details of these common cause failures is going to be described over in this video. So the video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. We'll go over the brief of the common cause failure. Common cause failure include events that multiple components failure affecting one or more sys within a limited time interval. This is explaining how quickly there are failures in the common facility. The following definition of common cause failure has been used during operational reviews. Components, items within the same component group that fail due to the same root cause within a specified time. So, any component or item which is failing in same component group means identical installation. So further, if we dig into the root cause, the failure nature and all, it will be of a similar nature. So, and also this has happened within a specified time because those failures has happened within a span of 3 months. It's not after 2 years or after 3 years. If some failures on a similar instrumentation has happened within a couple of months or within a period of 2 to 3 to 5, 6 months, then it can be considered as a common cause failure. If one failure happened in first year and another similar failure happened in 5 years later, then it cannot be a different one. That could be any other reason like a component issue or any manufacturing error or environmental issue or something like this. If the similar type of failures had happened between one failure to the second failure within a short span of time on ideal installations, so then it can be considered as a common cause failure. Fraction of common cause failure experienced in operation is higher than what is typically assumed in reliability calculations. Actually, calculation basis the failure rates may be very conservative. The manufacturers as well as the system users, developers and all, they may say that the failure rate for such kind of instrument or such kind of valves may be 3 years or 5 years, for example. But this may be based on the calculation data. But on the plant operation, when those instruments are put into the plant environment, they are going through very harsh weather, very erratic ambient conditions in some cases. So in those conditions, the failure rate may be much quicker than the calculations. Okay, we will go over the type of common cause failures for most of the cases in the safety instrumented system and what it will result into. So types of common cause failure and the probable failure. Pressure, flow, impulse line plugging. We saw another video about the impulse lines tapping. So for the pressure measurement or flow measurement, if the impulse line is plugged, so then what will happen? What kind of failure it can happen? Common impulse line of the transmitters can affect the readings, resulting into shutdown. Initially, if there is any plugging and all, the instrument reading gets erratic and it start reading poorly, not exact process measurement, and eventually it may lead into a failure. Two transmitters are connected to one nanobar flow element. Nanobar is a type of measurement being used for some flow measurement. So two transmitters are going to be connected on a single element. What is going to be the failure? Plugging of one or more bores, the internal bores, would influence the reading on both the transmitters. So if there is a plugging on one bore, it may impact the readings on the second transmitter as well. Two transmitters are connected to one orifice, again for flow measurement, pressure measurement and different pressure measurement. If the two transmitters are connected to one orifice, then what can happen? Common impulse lines of transmitters can affect the readings, resulting into shutdown. That's first point. During maintenance and flushing of transmitters may affect the healthy transmitter. If you are going to do a maintenance on a particular transmitter and there is a possibility that it may affect the readings on the second transmitter, which may eventually lead to some shutdown also. Possibility of inadvertently performing maintenance on running instrument by maintenance personnel. Plugging prevents both elements to reach safe position. This is one type of failure wherein plugging may impact the final element control valve to reach the safe position. This is due to instrument supply airline common connection airline plugging. If there are valves, each valve has to have an independent separate tapping from the main instrument header. If there is any where one instrument line is being used for two different valves, so any plugging in this one of the line may impact the air supply going to these valves and result into some failure or some shutdown. Changes in physical properties or ambient conditions influence both the sensors. Example, temperature, density, conductivity, dielectric constant, etc. So these are the different ambient conditions changes which may affect the sensors. So improper provision of heating, cooling tubes or electrical tracing, and depending on the geographical area, some countries the temperature is very low, some countries it's below sub-zero, in some regions it is above 50 degrees Celsius, etc. So wherever the temperatures are very low, they have to provide a steam tracing for making a heating, or if the instrument are lying in a very hot zone, again there also the possibility of the instruments getting error or getting failure will be high. To overcome that one, they may be placed in a box with a cooling arrangement. It may be known as vortex cooler or something, wherein the cooled air will be supplied and the instrument will be retained at a normal operating temperature. So if there is a provision of these things are not proper, and electrical tracing is another thing, wherein pipelines and the instrument tubing, instrument tapping will be heated up. So if these are not done properly according to the ambient conditions, according to the ambient requirements, then the possibility of failure is very high. Electrical signal of both elements is influenced. Example, electromagnetic current EMC, low supply voltage, and any other things. So why the electrical signal of both the elements can get influenced? I mean, both elements means both the transmitters or both sensors and valves, whatever. Power, so this is due to power signal cables running in a same tray. If you are looking into the industries, and there may be lot of cables running from the control room to the field instrument using cable tray. The cable tray has to be designed and the cables has to be done separately for the power cabling and signal cabling, because they are operating at a different voltages. Power cables for motors, big equipments like turbines, compressors and all, they are operating at a very high voltage like 3.3 kilovolt, 6.6 kilowatt, somewhere 11 kilovolt also. And the measurement instruments like pressure measurement, flow measurement, temperature measurement, these type of instrument sensors, they are operating at a very low voltage of 24 volt. So the cabling for the power measurement, for power supply of the heavy equipment, and the cable for the measurement has to be done in two independent trays. By chance, if they are mixed together, then the electromagnetic interference and other things can have an influence. Loss of data communication. Again, it is due to the electrical power disturbance only. So which may result in a signal interference. The readings may get disturbed. Programming error propagated to two independent protection layers. So this is the software error. Whereas the application program, if it is an error, and suppose the logic which is meant for the control of a particular vessel level erroneously entered in the safety instrumented system control program, so it may impact the safety. That's what is mentioned. Probably of various control language, ladder logic, function block diagram may be coded mistakenly with two different transmitter tags within one algorithm. This could be the other way also. The transmitter which is meant for the measurement, if it is wrongly entered in the safety instrumented system, so that is also a possibility to get wrong reading on the safety instrument system, which may lead to the equipment shutdown. Okay, next item. Two-wire transmitter require a minimum supply voltage at their terminals in order to work as required. In the plants, large industrial plants, the control room is at one location, and the field, the measuring transmitters, they are very far away, maybe somewhere between 500 meters to 3 kilometers, 5 kilometers, etc. So in those cases, the cable running operating power for those sensors is being given through the electronic cord in the PLC, safety instrumented system PLC, or basic process control system controllers, the modules, input output modules. Modules is supplying the power, but in case of an instrument location and the control room is quite far away from each other, there is a possibility of voltage drop. Instead of the 24 volt which is available in the control room, when it reaches the transmitter, sometime it may fall up to 15 volts also. So this drop may have an impact, and the instruments may not be able to work at times. That's what I mentioned. At times, due to lengthy cables running from control room to field junction box, there is a possibility of voltage drop, and the sensor is not able to work on the low voltage. Electrical interference due to high voltage in surrounding. Electrical interference may result in loss of signal. That's what I explained earlier. If there is any high power cable for operating a motor, they have to be laid separately in a power cable tray, and the instrument signal cable tray should be located as far away as far as possible to avoid any electrical interference. So these are the different reasons by which a common cause failure can happen and which may impact the measurement of the safety instrumented system sensors, and sometimes it may lead to shutdown also. Common cause failure are important contributor towards the safety reliability. Very few data sources are available on such failures in assessing the reliability model parameters. This is about the analysis. So every time there should be an analysis to identify what went wrong and how to correct it in future. So this kind of failure analysis also very difficult. Sometimes some data for the fraction of CCF common cause failure such as beta factor have been suggested, but these are generally based on safety system experts' judgments and figures from the oil and gas industry rather than actual operational data from some other industries. This was described earlier also. There could be identical failure in different installations, but if they are not located in a similar environment, operating environment zone, and they are very far away, then we cannot take that as a reference. Okay, so that's why we have to get in the opinion of the safety system experts who are having thorough knowledge about the various installations across different locations. So it is therefore more important to collect the data from oil and gas industries to a better reliability modeling. If you are going to do the study and investigation on a oil and gas industry failure, the identical plant failure data from a different location has to be collected and worked upon to understand the nature of failure and to overcome in future. Otherwise, the common cause failure can happen anytime on a similar installation. So we have to go into the similar kind of industry and similar kind of installation between plant A and plant B, or failure A and failure B. So these are the different items to be taken care while designing and installing the safety instrumented system to avoid the common cause failure. Thank you. Hello everyone, I am going to make a presentation on common cause failure and the methods to avoid common cause failure. This is part of the safety instrumented system, and the video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. CCF possible problems. Protection against common cause failure aims to eliminate or reduce the root cause of equipment failure and or to eliminate failures between components. Examples to eliminate multiple instruments failure is to relocate the transmitters from same piping or to go for a different technology. In the pressure measurement, flow measurement, differential pressure measurement, there may be impulse tubings which is going to the sensor. It may be shared in some cases whenever the safety instrumented system requires two instruments to be used. This is done because of the piping configuration and the area of limitation, etc. So which has to be avoided. So working on any one transmitter may cause a disturbance to the second transmitter and it can lead to the tripping. According to IEC 61508, diversity in the measurement instrumentation is the best alternate to overcome common cause failure, but in practicality it may be difficult to go in for diverse technologies due to limitation of installation, mechanical piping and economics. Actually, IEC standards recommend to go in for a diversification. That means two different technologies for the same type of measurement. It would be ideal, but on practicality in the plants the space may be limited, and putting multiple instruments on the same piping may be a challenge, so which may have difficulty for the installation, maintenance, and also the cost gets increased. So this is also a main factor wherein there may be possibility of using multiple instruments using a same trapping. Also, the diverse technologies require different levels of skills to do the maintenance and keeping multiple spares. So the different the technology may call for a different kind of experience to work and do the maintenance. So the people may not be skilled enough to work on both type of instruments. So that's a challenge for the operating plants to do the maintenance. And there are different technology, like one is a differential pressure type of measurement, another one is a vortex flow measurement, or it may be ultrasonic flow measurement. So the different technologies will require to keep multiple spares to attend and do replacement or repair or replacement in case of any need. This is also a challenge and causing economic difficulty to the plant management. Okay, now we will go over the type of common cause failures and the techniques that can be adapted to overcome the common cause failures. Pressure and flow transmitters impulse line plugging. So how to avoid this one? The engineering to take care of using independent impulse lines for transmitters. So this is the one. And secondly, we can consider like diversified technology. And two transmitters are connected to one nanobar flow element. Nanobar is one type of flow measurement. So if the two transmitters are connected to one nanobar, what will happen? So design to take care of using separate flow elements as far as possible. That's what the mechanical piping configuration allows, and there is enough space in the plant area. It is ideal to go for a different instruments. Two transmitters are connected to one orifice. This is for flow measurement, pressure measurement, and differential pressure measurement. The two transmitters are connected to one orifice. There could be a possibility of choking and disturbance happening in both the instruments. So it is the how to avoid this one. It is always recommended to use two transmitters using an independent orifice. Note, wherever the piping isometric does not allow to install separate orifice, proper care to be done during maintenance. Suppose there is a space limitation and the piping distance limitation is also there. Flow sensors and flow orifice should be installed in such a way that they have to have a minimum upstream piping and minimum downstream piping. If this is not able to be achieved because of the space limitations, and in those case the two transmitters are being shared, so the maintenance needs to take proper care to isolate the right instrument in case of any maintenance. Plugging prevents both final elements. This is on-off valves to reach safe position. Design independent impulse line for different valves. Identify with proper tagging. From the instrument air header, the main instrument will be going to the valve to operate. So such kind of tubing from the main air header to the valve shall be made independent. For valves that do not operate for longer intervals, select optimal valve type. Move valve frequently as possible. Wherever possible, there shall be an arrangement to move the valves. Move means to open and close the valves. Recommended to go with a partial stroke testing device. This is another technology for the safety instrumented system valves concerned. So the partial stroke testing device will move the valve to certain extent. It will not, when the valve is open, normally the safety instrument system emergency shutdown valves will close based on the demand, based on the hazard conditions only. But if the valves are staying in the same position for years together, there could be some chance of the valve stem getting sticky, and whenever there is a real demand happening, it may not be able to close. So to ensure that one, the valves operate at any time of emergency, we need to test it as frequently as possible based on the calculations done in the safety system. But additionally, we can go with the partial stroke testing device. This is an additional instrument to be placed on the on-off valve actuator, so which may move the valve little bit, maybe 5% or 10% from its full motion, to ensure that the valve can operate whenever any emergency arises. Changes in physical properties or ambient conditions influence both sensors: temperature, density, conductivity, dielectric constant, etc. These are the different parameters. Use alternative technology or calculate influence and apply the correction factors as far as possible. Whenever the physical properties like temperature is going to have an impact on the measurement, or density is going to have an impact, or conductivity is going to have an impact, we need to use an alternative technology of measurement, or provide, if the temperature is going to be a concern for the cold countries, we need to provide external heating arrangement. or if it is going to be the density measurement issue, you'll have to provide again insulation and keep the fluid temperature constant so that density will not have an impact on the measurement. So the next one is electrical signal of both elements is influenced. If two transmitters are going to be used to have a separate wiring. Otherwise, there may be possibility of electromagnetic conductivity, low supply voltage, etc. So for this, how to overcome? Follow best wiring installation practices. Electrical and signal cabling to be laid in separate cable trays. As we know, the motors or turbines are running and operating at a very high voltage like 3.3 kilovolt, 6 kilovolt, sometimes 11 kilovolt and all. So, and that sensors, that instrumentation transmitters, whatever is in the safety instrument system and basic process control system, they operate at a level of 24 volts only. So, these two cables shall be kept laid in a separate cable tray with enough distance between them. Otherwise, the electromagnetic interference can have an impact on the measurement. So, loss of data communication. So, adequate communication with adequate care with communication fiber optic Ethernet cabling to be laid in separate cable trays. Adequate care to be given while putting these cables, and they have to lay in different cable trays, not mixing with the power cable like 3.3 kilovolt, 3.3 kilovolt, 6 kilovolt, 6.6 kilovolt, and 11 kilovolt. That kind of higher voltage bearing cables and these signal cables cannot run together. Programming error propagated to two independent protection layers. If there is any programming error in the logic solver application program, it may impact the actual logic to be performed. So it is always ideal to have two different type of processors for the basic process control system and the safety instrumented system. Some manufacturers provide same type of processors which can use for safety instrumented system as well as basic process control system, but internally the programming techniques may be different. So as far as possible, we have to use an different diverse technology, diverse architecture. So the application program has to be verified thoroughly. Two-wire transmitters require a minimum supply voltage at their terminals in order to work as required. The pressure, flow, differential pressure, temperature, like that, these measurement sensors level, these measurement sensors require a minimum operating voltage to be available in their field terminals. But some plants, the field instruments may be quite far from the control room from where the main power is taken through the electronic modules. So the 24 volts which is available in the electronic card may drop down to 15 volt, 14 volt or something like this, depending on the type of cable and cable length, etc. So the voltage is going to be very low and the electronics inside these sensors cannot work. So wherever there is any such issue, we have to have any step up voltage resisting devices, or we need to have in between additional barrier. Okay, electrical interference due to high voltage in the surrounding. Proper care to be taken while installing sensitive transmitters like nuclear, radar instruments and all. They should not be so close to pumps, compressors operating at high voltage. This is different technology like nuclear level measurement and radar level measurement. They have to be taken much more care, and they should not be placed very close to turbines or high capacity pumps which require higher operating voltage. So how to overcome all these issues with common cause failure? So there are some best practices which will help to avoid common cause failure. So recommended to keep independency between protection layers. This BPCS, basic process control system, is one protection layer, and safety instrument system is another protection layer. So it is always recommended to keep independency, because they have to have independent transmitters, they have to have independent measurement, control everything. Okay. Allow diversity between protection layers. Actually, as we talked earlier, there can be different technology for each type of system so that the common cause failure can be avoided. Designed to have physical separation between different protection layers. In the engineering design, it has to be taken care to have a physical separation between the different protection layers. So these are the methods to overcome any common cause failure. Thank you. Hello everyone, I'm going to make a presentation on safety instrumented system logic solver and the application level requirement. The topic will be on application level requirement. Video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe. Safety instrumented system logic solvers. We'll go over the basics. Safety instrumented system application program is very vital for the safety instrumented system logic solvers. Users has to follow a uniform approach based on the conditions set by the international safety approval agencies for successful safety instrumented system implementation, SIS implementation per IEC 61511 and other international standards. So the application program is the one which is executing and doing the necessary control and corrective action. So that has to be programmed clearly and any mistakes shall be avoided for the betterment and safety of the plants. SIS logic solver program requirements. We will go over the few points which is applicable for the safety instrumented system logic solvers. The programming application code is to be taken up subsequent to logic solver selection to execute the safety instrumented functions. The type of programming language has to be confirmed, has to be finalized once the type of logic solver for the safety instrumented system is selected. The application program must follow the manufacturer's specification prescribed in the safety manual to ensure the safety and reliability. Each manufacturer of the logic solvers or processors will go through an approval process from the international agencies like IEC and EXIDA to TUV, like those organizations, and based on their approval only they can deliver the products with the required software. So, and for which they have to develop a safety manual also. So that has to be ensured and their best practices to be followed. Supporting documentation such as programming criteria, safety manual and a specific platform's design specification is required for application program development. There shall be a standard rules for the programming. Accordingly, the program has to be written. Safety instrumented functions implemented on a certified logic solver must follow safety manual for that logic solver, which are subjected to international safety certification agencies. This is what we described in the earlier point also. They have to have a certification from the approved international agencies. Written security procedures shall exist to prevent unauthorized or inadvertent changes to the software program. The application program and the relevant software can be accessed, modified and edited and modified if required, and any changes can be made with an approval by the department leader or some concerned authority. So they will have approval and the names of persons who can work on those systems. So that has to be done. Otherwise, somebody will poke their skills and then make mistakes. The plant protection in charge shall designate those persons allowed to make changes to the code, and those are followed to perform program loads. So only the authorized persons can work on those programs and do the changes. Whenever SIF and BPCS application program are implemented on a single certified logic solver, the safety instrumented function code must either be separated from BPCS code, that means separate partitions, or be clearly identified to the safe state or a risk mitigation, hazard assessment, and alternate management to be developed by the operation personnel. And plant operators need to be trained in this response to sustain the plant operations when SIS instruments goes out of service. So whenever any instrument fail happens, the program shall take care and do the independent protection. The safety instrumented system sensors environment shall be clearly marked in the P&ID piping and instrumentation drawings and in the computer software documentation. Implementation of safety instrumented system safety manual recommendations to meet this requirement. New or modified safety function programming shall be verified against its specification by application code review or simulation. There are some simulators available for each type of programming, so the logics can be tested offline without putting it into the real world application. This is logic. So this point is continuing. New or modified safety function programming shall be verified against its specification by application code review or simulation, assessment by an independent safety system coach, and validated by functional tests prior to its initial operation. This is what we discussed. The code has to be written thoroughly as per the standards and it has to be assessed by safety experts. The safety requirement specification and safety instrumented system or process meets the intent of this requirement. Safety logic, safety system logic solver application requirement is also a part of safety requirement specifications or process. So here we are just seeing one basic programming. This is done using a ladder logic diagram for a pump on-off control. So this is by a specific vendor. Here these conditions has to be met for this output to go to the respective pump, either to start it or stop it. Here in this case, this is going to do the selection and do the automatic. For example, in this example, all these signals are through, all these contacts are through, and this output is enabled. The output of this enable energize another contact internally on the sorter side, and the higher level is also not there for this reservoir. The higher level is there, adequate level is there to start the pump. So in this case, the pump 1 automatic control, if the selection is done in the control room, so based on the selection, and since these two signals are already available, if the selection is made to run the pump by automatically, so it will be selected and the pump will start. So how can we do the better utilization of the logic solver program? So these are some methods. Control engineers need proper design documentation to ensure that safety functions are not compromised during program maintenance. Because every time the control engineers has to review the programs and see that all the necessary backups of the programs are taken up, and the codes, the programming follows a best or international practice. So in no point of time they need to go through some shortcuts and avoid any errors. Maintenance personnel need to know that the instrument they are working on is a sys instrument in which application program it is connected to, and take proper care while carrying out maintenance. For the safety instrument system, the maintenance folks involvement is also quite high. So whenever they are going to work on a particular instrument, and if it is in the safety instrument system, also there is only one instrument, they have to approach the respective leader to give a bypass authorization, and again they need to ensure that they are working on the correct instruments identified. Operations need ready access to details what instrumentation is involved in safety programming. So they need to understand which are the instruments available for the safety instrumented system protection and do the respective action, either to give maintenance release work order or to isolate the instrument or equipment to work on them. Like that, they need to do and understand the required level of application programming. Thank you. Hello everyone, I am going to make a presentation on safety instrumented system proof testing, and this topic will be on needs of proof test. Video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. In safety instrumented system, proof testing is very critical to ensure all safety instrumented system sensors, logic solver, and final control elements are functioning healthily as designed. Various international standards such as IEC, ISA, and ANSI governs the requirements of this proof testing. Okay, what is proof testing? Proof testing is a test performed to reveal undetected faults in a safety instrumented system. So, in case of any instrument system deterioration, the system can be restored to its designed functionality as per IEC 61511 standards. Due to the continuous operation and harsh environmental conditions and the process which the sensors are handling, which is passing through the sensors or the final elements, they may get deteriorated over a period of time. So for the safety instrumented system, the proof testing is an essential one to ensure that the instruments are functioning as desired, because all these safety instrumented system sensors, final elements, and logic solvers, they are supposed to work quickly and safeguard the system and plants in case of any hazardous conditions happening in the plant. So high importance should be given for the safety instrumented systems, its components to work healthily. So this hence it is governed by so many international standards such as IEC, ISA, and ANSI. Okay, why proof testing is important? Proof testing is crucial for the plant's safe operation without any potential hazard due to lack of all instruments performance as per the SIS design intent. Proof testing supports early detection of failure so that failure can be attended as quickly as possible and maintain the SIS functionality much more reliable. Proof testing helps to do the early detection of any failure. In the event of not performing proof test on the SIS instruments as per the SIS calculations, it may lead to dangerous failure, which may eventually end up in catastrophic events. So, due to some reasons X, Y, or Z, and the plants are running and the instruments are not able to be isolated, and the proof test is missed, but supposingly there is any demand coming as an safety requirement and the instruments did not work, the pressure sensor which is supposed to sense the pressure and give an indication to the logic solver to give a closure to the final controlment valve, this sensor did not work, or either its electronics failed or its sensing components like diaphragm or something is failed. So it cannot be detected. If the testing is missed, the internal failure cannot be detected. So it may eventually lead to the hazardous situation to happen. Instead of preventing this hazardous scenario, the failure of the instruments may result in the hazardous conditions to happen and result in the particular section of the plant or complete plant to trip. Or it may, in most cases, may lead into some fatalities or injuries to the employees, etc. Okay. Regular proof testing of critical components enhances the mean time. MTBF stands for mean time between failure of a system for two different reasons. Early detection of developing problems. Proof testing may reveal weakness developing in components, indicating the need for replacement in near future. So this supports to indicate any failure, and maintenance teams can take an early action to replace the instrument or repair as required. Regular exercise of components. Proof testing increases the system reliability is by realizing the beneficial effects of regular function. And the testing ensures that the reliability getting increased, because during the proof testing any hidden failures are getting revealed, so that the safety instrument systems are always made available to act in case of any emergencies, any hazardous conditions. Okay, here we'll just go over a graph. Here it is depicting how the proof testing can improve. If this is on the x-axis we have the time running, and on the y-axis we have the probability of failure and demand. See, as the time increases, the probability of failure and demand goes on increasing, so that the possibility of the dangerous failures getting increased. So, for each system, there is an average PFD based, which is to be maintained, and the dangerous undetected failure. If we fail to perform the proof test in time, there is a chance of getting the dangerous undetected failure. So whenever we do the proof testing as per the calculations and do proper maintenance, the healthiness of the instrument and reliability of the system is getting ensured. So the system gets back to this original state, which is in a good healthy condition. So this has to be ensured always. Okay, what proof testing covers? Proof testing cover full end-to-end loop testing, including settings, parameters, and trip points. So in the proof testing, the internal settings of the sensor, electronics, and parameters, some flow meters and all, there are some constant parameters, key factors, like there's some setting parameters are there, or there could be some damping for some instruments with a small time delay. All these kind of things has to be re-verified as per the design conditions. And the trip points, in the logic solver, the trip points will be rechecked, because during the plant commissioning, there will be some set value which is set for the tripping of the particular system. But during the operation, there could be some reasons which may call for slightly adjusting the set points. That has to be within the limits and has to be ensured updated in the records. Supposing a person goes for the proof testing in future and he sees a different value of the trip points between the document and the actual available in the logic solver, he may get confused. So records also has to be maintained properly. So proof testing, the maintenance person can ensure that the settings are done as per the design intent. The in-service proof testing method should also include inspection of hardware to ensure that it is in good condition and meets safety installation requirement where necessary. Some cases, especially in the on-off valves and all, that is not possible to do dropping of the valve. Dropping means removing from the pipeline and taking it to the workshop, do the servicing, do the valve stroke testing, and bringing back to the operation, bringing back to the line. Sometimes it may not be possible due to the time limitations or manpower limitation, etc. So it is recommended to do an online testing, but when the plants are running, there shall be provisional arrangements in the piping facility to make a bypass of the loop to keep continuing the operation and do the proof testing on the safety instrumented system valve. That has to be made sure. This requires suitable systems for hazardous area inspections, equipment condition inspection, and predictive and preventive maintenance procedures. So these are all the categories to be covered during the maintenance proof testing. So here we are just seeing some pressure transmitters is getting calibrated or getting tested during the proof testing. So the instrument technician or instrument foreman is adjusting all the connections and ensuring that the systems are in healthy conditions to continue its operation. Okay. Below project upgrade and modification activities involving safety instrumented system requires to perform proof testing. During the plant running, there may be some requirement to add some additional protection features. So safety instrumented system for that particular plant area may be added, or some additional protection layer may be getting included, meaning some additional instrumentation may get included, which is involving in the safety instrumented system or basic process control system protection. So whenever any project upgrade happening, there are chances of the below points. Introducing the new process lines involving safety instrument system instruments, changing the safety instrument system configuration, adding flush and drain valves where safety instrument systems transmitters, final control elements are in place, adding block and bypass valves with upstream downstream isolations. These different categories require proof testing to be done whenever any changes in the facility is being taken up. Okay. During SIS design, proper care to be taken after finalizing the safety instrument system configuration based on the PHA/LOPA outcome, which may end up in the below items. PHA stands for process hazard analysis, LOPA stands for layer of protection analysis. So based on these studies, so there could be some additional requirements on the safety instrument system as below. Addition of redundancy instruments like 1 out of 2, 2 out of 3, this may be required. Introduction of bypass valves for testing if new on-off or control valves are provided. This may be required to provide a bypass valve. Requirement design for automated online testing. So there is a facility to do an online testing by closing the isolation valves, provided there is enough bypass arrangement for the process to continue operations. Necessity of special tools or equipment like partial stroke test devices. For the final control elements on-off valves, there is an additional device known as partial stroke testing device, which is built into the actuator body. So whenever any proof testing is required and the system cannot be isolated, so the partial stroke test will be done, meaning the valve will be moved from its full open position to small little closing, like it may close for 5% or max 10%, and then get back to full open position, which is 100%. So this facility is being done using a partial stroke test device, and inclusion of software to collect the data when online check is possible. So in the new modern instruments, there is a feature to do the diagnostics and all. So this is by adding software. Accessibility needs to perform testing. Quite important to do and create an accessibility in case of any instruments need to be tested. So this is the accessibility needs which is mentioned. So these are all the few requirements which may come up to do the proof testing during any project modifications or upgrades, etc. Okay. Thank you. Hello everyone, I am going to make a presentation on safety instrumented systems, instruments proof testing. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe. Proof testing of safety instrumented system instruments. Fully defined proof test procedures will help improve planned maintenance strategies, fault reporting capability, avoid unnecessary equipment failures, and show compliance with the safety management policy. Each plant will have a safety management to ensure the protection of the people working in the plant as well as the facilities available in the plant. So the proof testing has to go as per the maintenance procedures and get it vetted by the safety management team. Maybe like health and safety environment team, or it may be called in a different way in each company. So what is proof testing? Proof testing is a test performed to reveal undetected faults in a safety instrument system. So in case of any instrument system deterioration, the system can be restored to its designed functionality as per IEC 61511 standards. Once the safety instrumented function SIF is in service, the organization needs a clear documented regime to ensure it achieves the required integrity level over its operating life. Once the plants are alive in its working condition, the management should have a clear documented records for the proof testing of the instruments. Test frequencies are set as part of the PFD calculations and are recorded in the safety requirement specifications. How to arrive at the test frequency? This is a calculation based on the probability of failure and demand, and that then it will detect what kind of configuration to be have in the instruments, like a 1 out of 1, 1 out of 2, 2 out of 1, 2, 2 out of 2, 2 out of 3, etc. So that will be required. The management of the testing must ensure tests are called and completed in time. Test methods must be clear and comprehensive such that a competent technician is able to complete them without any delay. So the procedure should be made clear. Engineering design also needs to have considered testing as part of the PFD calculations and should include the ability to test with the stated plant conditions. Online tests using overrides. In case of any online test required using an override, that is also need to be captured. Okay, performing SIF proof test and method of test varies with the configuration of sensors, final control elements. 1 out of 2, 2 out of 3, 2 out of 2, etc. And their model details like example, RE phase based pressure, differential pressure level, and another type of radar level. Next one is inline mass vortex flow meters, etc. And pneumatically operated valves, pneumatic operated or electrically operated valves. For each of the type of instruments and valves, the testing may be slightly different, and also based on the type of configuration it may vary. However, below basic procedures can be performed on the sensors at a calculated frequency. This may be as early as 2.5 to 3 years, even if the proof test is calculated for 5 to 6 years. So sometimes it may be required to do at an early interval. Maybe this is due to the plant tripping well before the planned target date, planned shutdown dates, etc. Okay, and what are the type of tests we are going? It is to be performed on the safety instrumented system instruments. Visual inspection of field transmitters. So this will reveal problems that are not identified by the instrument self-diagnostic tests. Instrument will remain unavailable for the function. So that means the instrument is getting taken out of the service. It will not be It will not be taken out of the service. It will keep continue to do the protection. Only the inspection will be as a visual inspection, keeping the instrument in running condition. Wetted part inspection. This is for the process lines. The instrument will remain available for its function. It will result in the instrument will be available for its function. But visual inspection of flow meter configurations and time constants and K factors may get disturbed in intelligent flow instruments if proper soft lock is not programmed. Soft lock means internally there will be a lock, so which requires some enabling key. It's like password protection. This is applicable for the inline flow meters, which are of the later technology. Like it may be like a Coriolis mass flow meters, vortex flow meters, magnetic flow meters, etc. Okay, here again, this is for the pressure sensors. The proof test is being performed, and the instrument technician is doing the instrument flushing and then confirming all the parameters are as per the design standards. Okay, caution for proof test methods. Proof test plan are to be developed cautiously, taking into consideration. Check if proof testing in the field is acceptable from a process point of view as per the plant area, layout, piping routing, chemical hazards, etc. This is what actually, when before taking the proof test, it has to be ensured that like flushing of the instrument line. So in this case, this line may be required to be drained, which may result in loss of little bit pressure. So this should not have an impact for the running process. So these are the different requirement over here. Consider the below factors like electrical area classification, toxicity, ability to isolate reliably without impacting the run plant. Always it is to be taken care that the run plant shall not be disturbed for the proof testing requirement. So this has to be kept in mind and ensured that the systems are running healthily. For in-field test procedures, confirm if all the required hardware such as isolation or bypass valves either exists in the design or to be added to the design. So bypass valve available in the system, for which we are going to the maintenance is going to do the proof testing, then it is fine. If there is no bypass available, then some alternate method to be developed before doing the proof testing so that the process can continue to work. Again, further going on with the cautions, determine if the process application requires any modification to the sys instrument maintenance procedure. For example, whether the testing can get impacted due to an incompatible test fluid. Normally, the test fluids like nitrogen is being used. So, this shall not get contaminated with the process fluid or process gas which is going through the sensor, passing through the sensor body. This has to be ensured. Changes to the application program requires full validation and a proof test of any SIF impacted by the change. There is any changes happening in the application program, so it may require for a full validation. Okay, here in this picture we are seeing inline flow meter is being tested and adjusted for the parameters, and the configuration is being taken up. So, ways to improve sys-proof testing. For inline flow measurements instruments, heartbeat or smart meter verification, self-diagnostic sensor technology facilitates timely and accurate diagnostics of the instrument pulse. These tests can do diagnostic coverage up to 98%. For the instruments with the later technology like Coriolis meter and vortex flow meter, they are available with the inbuilt software known as Orbit technology or smart meter verification, which can run parallelly during the processing and send a error indication about any failures, possible failures. Results of inline flow meters test results to enable targeted, timely, and cost-effective maintenance interventions, ensure safe processes with minimal process interruptions, drive cost-effective maintenance through smart data and diagnostics. Wherever possible, for the new facilities, the management should consider to use those instruments which is having a intelligent processor, and online testing can be performed without any hindrance for the running plant. So the latest instruments with some manufacturers have these facilities like Orbit and smart meter verification. These are all the different methods to do betterment of the sys-proof testing for the field instruments. Thank you. Hello everyone, I am going to make a presentation on safety instrumented system valves proof testing. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. Proof testing of safety instrumented system valves. For a final control element such as on-off valve, it requires full stroking of the element coupled with physical leakage test or other assessments to ensure that the element is having the intended effect on the process as per the IEC 61511 standards. As we all know, many requirements for the safety instrumented systems are being governed by the IEC standards. IEC 61511 is the one for the process industry sector, which has formulated the standards based on which different requirements are being taken care. Another part is visual inspection of valves. Visual inspection is able to find if there are leaks, air filter regulator, booster relays that can be corrected. If there are solenoid valve coil damage, air leak from the spools in connection, the same can be conducted and corrected. So visual inspection comes into picture whenever the valve proof testing is quite longer, maybe 5 years or 6 years, and the plant may not be going for a shutdown. Usually the plants will have a turnaround interval of 6 years, 8 years or something, depending on the plant's operating capacity. So in such cases, the final elements are to be proof tested only in this 6 years or the turnaround period, whatever applicable. So the alternate way to ensure the healthiness of the sys valves is to do the visual inspection. So by visual inspection, we can test all these items like air filter regulator, booster relays, solenoid valve coil, etc. So if there are any air leaks, coil damages found externally, the same can be attended to. So valve proof test. An automated valve proof test helps to discover hidden failures. These failures, if not corrected or removed, may impair the ability of the sys to take the process to its safe state. When an abnormal process condition is detected, the automated valves are in the process to isolate the process media going to a tank or process media going out of the tank to a process area. So they always handle hydrocarbons, oil, gas or chemical components which may have potential hazard to go in for a catastrophe like fire or leakage may cause inhalation issues for the human beings, etc. So they are very critical for the operating process plants. So that is why proof test is required as per the IEC standard, so which can help to do all the hidden failure, to find out the hidden failures, etc. A proof test should be performed as per the proof test interval specified in the safety requirement specifications. This interval is usually determined an average probability of failure on demand calculation. There is a calculation for the probability of failure on demand, how far the instrument can go to fail, how is the possible probability of that instrument or valve can go to fail. So by that PFD calculations are being done, so based on which the proof test is also arrived at as per the calculations procedures. Some users may choose to proof test based on fixed intervals, such as test final elements every 48 months instead of relying on the PFD average calculation, which is not recommended. In some cases, few manufacturing companies or few companies may prefer to do the proof testing based on a standard interval, which is not recommended by IEC. Again, further going to valve proof testing, automated valve proof tests can be done offline or online. Offline proof tests are usually scheduled during a turnaround when the process is completely shut down. Offline means removing the valve from the position out of the piping and take it into the workshop, do the necessary servicing and repairs if any on the valve, and do the soft parts change like many gaskets, O-rings, like that. Soft parts, they are known as soft parts. They may get damaged or deteriorated over the period of working, maybe 6 years or 8 years, after which the valve is being removed from the piping. So all these services will be done at front at a workshop, and then the proof test will be arranged by connecting the relevant air supply and putting the valve in the test bench, etc., and connecting the required pressure lines, etc. Proof testing an automated valve online usually requires a unit or equipment to be shut down or the valve to be bypassed to prevent a spurious trip, making it inconvenient and costly. The valve needs to be tested online within the pipeline, may require that particular system to be shut down, or if there are any alternate valves in the piping, like a bypass valve is there, so that can be used to keep the process running and test this valve, which is a safety instrumented system valve. Otherwise, there could be a chance that the testing may result into closure of valves and lead into the process trip, which has to be avoided. So to overcome all these difficulties, the design should take care to provide a bypass valve wherever possible and make sure that the sys valves can be tested during the desired during the calculated intervals, proof test intervals. Whenever a process trip, proof testing under process trip, this is another possibility. Whenever a process trip occurs, when the sys detects an abnormal process conditions via sensors such as temperature and pressure, or also flow, differential pressure, etc. may be there, and level also may be there, executes the logic and places the process in its safe state by tripping the final elements such as closing an automated valve, stopping a pump, etc. So these are all the automated actions for the safety instrumented systems, sensors, logic solvers and valves. This works as per the process requirement according to the standards, according to the engineering. The sys may communicate with the basic process control system to close a valve downstream of the automated valve as a secondary action. In the piping, usually there will be an automated valve which is like on-off valve, which will make 100% open or 100% close, and during the normal operation of the plant, the valves will keep in open position, and downstream of it there will be a control valve which can also open from 0 to 100%, but gradually. So that's why it's known as control. So normally the control valve is being operated through the basic process control system. It is doing the normal process variations to keep the, for example, to keep the level or maintain the pressure or maintain the temperature, etc. So during the condition of process trip, anything is happening automatically due to the process conditions. So the automated on-off valve, which is actuated through the safety instrument system, will close, and as a secondary action, the control valve will also close. So this makes sure that the system is safeguarded. Fortunately, the automated valve is equipped with a DVC. DVC known as digital valve controller. The proof tests of the valve can be considered performed with the diagnostic data captured by the DVC. Also, a comparison of the diagnostic data with the valve's baseline can help discover valve deficiencies and degradations that may not show up in a proof test. DVC is known as digital valve controller. It is an intelligent electronic, so which collects the valve information data and keeps a database. So during the overall of the valve or initial installation of the valve, those valves will be tested and the baseline data will be recorded. How much in pressure the valve is moving to what position and what is the thrust required for the valve, etc. There are many parameters. So all these things will be stored in the memory card inside the digital valve controller. But similarly, during the process trip condition, it will capture all the information when the valve is actuating. So this is a helpful tool to confirm that the valve moved according to the desired or according to the design standards, and it meets all the requirements. If there are any deviations, much deviations, the same can be taken care and attended. So by this, during the valve, any process upset or process disturbance, the valve is being stopped and the proof test coverage is being taken into account. Digital valve controllers. We are going to get into more details about the digital valve controllers here. Digital valve controllers not only provide intelligence benefits in terms of performance and safety by allowing partial stroke test online, but also provides additional benefits in terms of ease, simplicity, flexibility, diagnostics, and improved reliability of the safety instrumented function, etc. By eliminating expensive conventional local test mechanism, which was laborious, time consuming, and requires specific talent. We saw about the valve testings in the online, means when the process is in running condition, processes in operating condition. So during such time, making a stroke test on the valve is practically impossible unless there is a bypass arrangement. So there are some devices known as partial stroke testing devices, which helps to move the valve little bit, closing to 0%. It will just move from 100% to say 90% or 95%. The little movement of the valve can be taken as a credit as a proof testing is completed. Alternately, there is a digital valve controller being supplied by some manufacturers, which is an electronic device, intelligent device, and it helps to record all the information of the about the valve internals, valve movement, thrust, any air leakages there, and output position, how much it is reaching. All this will be recorded in the digital valve controllers. Again, during the initial installation or after an overhaul of the particular valve, all this data is also taken. So the technicians can compare the data between the initial condition and the current one. So they can arrive at the decision about the healthiness of the valves. Digital valve controller reduces complexity and simplicity of the test process. Digital valve controller predictive maintenance capability provides the complete final element health analysis and reduces the amount of scheduled regular maintenance by extending turnaround period. So whenever these valves are installed with the digital valve controllers, so it helps to read the internal data about the valves and do an analysis, so which helps to increase the turnaround interval in case of any requirement based on the market conditions or based on the raw material availability, etc. So all such cases, digital valve controllers helps to confirm the internal failures if any, and also do a baseline data verification. Otherwise, testing the valve online is a Herculean task, which is mentioned over here, because we need to do a support for the valves in case in the site, and then connect an external instrument air supply, isolating the main supply which is available on the valve, like a milliamp calibrator, like that we need to do it, and test the feedback conditions, etc. So which requires more energy as well as more manpower, materials, etc. So by deploying the valves with digital valve controllers, it eliminates all these additional requirements and additional expenses. Only the initial cost of the valve may get increased by some percentage. Okay, here we'll just go over the small photograph about the digital valve controller, so it can be used. This is the sys valve test automatic with the digital valve controller using an AO stands for analog output, which is a 4 to 20 milliamp signal. From the safety instrumented system, the logic solver, there are different types of modules: analog input, analog output, digital input, digital output, etc. And some communication modes also may be there, which communicate to the other systems, and besides the processors and power supply units. So this is an arrangement with the analog output of 4 to 20 milliamp signal, which is a normal operating. So from here, the signal is going to the valve, the digital valve controller, and the valve can be used to stroke and test. The travel feedback, how much it has traveled and all, can be measured from the same device. This is one arrangement. Additional different arrangement is sysval test schematic with a digital valve controller using a digital output 24-volt DC signal. Another one is a 24-volt DC digital signal, so which can go from a digital output model of the logic solver. If you see in this picture, both these pictures, the logic solver is sitting in a non-hazardous area, which is a safe zone, and it may be away from the process area depending on the plant's architecture. It may be in half kilometer, it may be in 200 meters, or it may be in few kilometers as well. And they'll be connected through a fiber optic cabling, etc., to the field instruments. So this is a non-hazardous area, and all our valves and sensors which is installed in the plant process area, they are known as hazardous area. So here only the safety requirements may come up, and any incident can lead into fire, gas leak, etc. So we need to protect the equipments, people, etc. So this arrangement is for the digital output signal of 24-volt DC. So from here the gain signal is going through a line conditioner. This is to overcome any feedbacks coming back from the system, from the DVC and the field devices. So there is a conditioner and the digital output is going. Again, the valve is the DVC is being installed, and based on the signal coming to the DVC, it operates the valve, opens and closes the valve. So these are two different arrangements, and this is being on supplier known as Emerson. Similarly, there are equivalent devices available from different manufacturers as well. So valves inline proof testing and inline testing applications such as smart valve monitoring can monitor the emergency shutdown system valves for faults based on comparing an original full closure fingerprint of the ESD valve assembly and components such as solenoid valves against a partial stroke test. This is smart valve monitoring is another product which is equivalent to digital valve controller, which helps to identify the valves, etc. And their system can perform all the tests at the emergency shutdown valve, designed closure speed without shutting the plant down. So this digital valve controller and smart valve monitoring, these devices, when they are installed existing on top of an automated on-off valve, helps to do the online testing and avoid dropping the valve, taking it to workshop, doing the necessary valve servicing, stroking, and then bringing it back into the line. So which is time consuming as well as involve more money. So this such kind of smart devices helps to avoid those expenses. So common cause failure of so we are talking about the requirements of the safety instrumented system automated valves, which is more critical for the process to isolate and bring down any hazardous conditions. The valves has to be 100% available to do the operations. So what are the possible failure with the common causes? So we'll just go over it to understand why it is more important. According to the ISA technical report 96.01, the most likely root causes of automated valve degradations which can lead to a process trip include partial or intermittent streaking of hydraulic or pneumatic system components such as solenoids, pilots, speed controller, etc. due to moisture, debris, or alignment issues. This causes a loss of functional margin and makes a valve slow to open or close. So such kind of valves, being an isolation device for a process, they have to act quickly within a certain operating time. They have to go from full open position to full close position, maybe in 5 seconds or 10 seconds depending on the process requirement. But the components, the internal components like solenoid valve and the boost relays, anything, they are and pilots, they are just accumulated with heavy dust or any moisture is there in the airline, which may lead into the slower operation of these components, eventually leading to slower operation of the total valve, and it may not prevent the hazard as intended. So this is one common cause of failure. Binding, haling, or other degradations of valve seats or related flow control trim that restricts or resists valve movement. Again, similarly internally on the mechanical part of the valve, there could be some binding, galling, which means it becomes more tricky for the valve seal to move. So even though there is a command and there is an output going from the solenoid valve to do the actuation, the valve may not move due to the mechanical failures internally. So that also a common cause of failure. And actuator seal degradation caused by compression, wear, and looseness that reduces the pressure available to actuate the valve. There is one actuator for each of the valves to operate, so that also has to be in a good working condition. But internal wear and looseness of the seals, etc., may delay the actuator closure operations. Minor damage to the valve plug, disc, or ball caused by system conditions, leakage or debris, including buildup of hydrocarbon products. This causes also leakage. Actually, sometimes what happens, the process itself may get leaked through the valve stem, etc., and get accumulated in the instrument air filter regulator or any other pneumatic components. So this kind of debris again hamper the valve actuation and delay the valve closure. Complete failure of hydraulic control system components such as solenoids, pilots, speed controller, etc., due to moisture, debris, or alignment, the valve will fail to open or close. There could be some reasons, extreme conditions, which may totally block the operation of the pilot valves, solenoid valve, etc. And this could be due to the accumulation of moisture, accumulation of dust, or any other debris, and this may totally avoid the valve movement, thereby leading to the failure. Thank you. These are the different common causes that can happen. So the sys valve installation maintenance proof testing is a very critical one for the process plants. Thank you very much. Hello everyone, I am going to make a presentation on safety instrumented system. The topic will be on probability of failure on demand, PFD. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe. SIS, probability of failure on demand. For safety instrumented system, probability of failure on demand, PFD calculation, is carried out as part of SIS design after the LOPA PHA study. LOPA stands for layer of protection analysis. PHA stands for process hazard analysis. After this study, the PFD is being calculated. Probability of failure is calculated term based upon reliability data, which reflects the possibilities or likelihood of a SIS fail to operate. So this is based on the any possibility or any likelihood the particular component can fail to operate. Typically expressed as probability of failure and demand, this term is important in determining the design configuration and test intervals. This is again for the safety instrumented system, sensors and logic solvers, as well as final control elements. This topic covers the definition of PFD and allowable limits. SIS, probability of failure on demand. The higher the safety integrity level, SIL, the lower expected PFD average for demand mode, or the lower the average frequency of a dangerous failure causing a hazardous event. The hazardous event is happening in plants whenever there is any dangerous failure occurred to a particular component, say a sensor or a final control element components, etc. So when the SIL is higher, PFD average is getting lower. The required SIL shall be derived taking into account the required PFD, required probability of failure on demand. Overall, SIS should achieve the target probability of failure on demand for a demand mode system like continuous mode of operation. It should achieve the target frequency of failure necessary to meet a calculated safety integrity level. It is based on the calculations of safety integrity level. Okay. Further going on, for the PFD, most safety instrumented functions operate in low demand mode. Generally, the process plants, they are operating on a low demand mode as far as the sys is concerned. These sys are normally not taking any action but are available when needed. The safety intermittent system is always active, but they are not moving components every time. So, as far as the system execution is concerned, they are like a passive system, and they operate whenever there is any demand, any hazardous events happening in the plant on the particular zone. That time only the sensor does the sensing of the process parameter measurement, and then the logic solver makes logical calculations and provides an output to the safety instrument system, for example, for valves, and then operate. So that means they are always available but keep silent. Normal operating conditions, only the control part, the BPCS control, basic process control system, is doing the action of the plant operations. For a shift to meet the low demand mode definition, the specific shift demand must occur less often than once a year, and at least 2 proof tests must be conducted between the demands. So this is a definition for the low demand mode. So the demand can occur once in a year, and at least between 2 proof tests that can be conducted between any demands. Any demand means any action which is required to operate. PFD is the appropriate failure measure for safety instrumented function shifts in the low or high demand mode. Okay, now we'll go over the values of PFD. Safety integrity requirements, PFD average for continuous mode of operation. See, these are the different safety integrity level. We'll go from 1 to 4. So, with the safety integrity level SIL being 1, the PFD, probability failure demand average rate should be more than 0.01 and up to 0.1, 10 power minus 2 to 10 power minus 1. So, required risk reduction, which is the inverse of this PFD average, should be more than 10 and less than 100. And for SIL2, it is between 0.001 to 0.01, the PFD average. Similarly, the risk reduction is from more than 100 to less than 1000. For SIL3, this is 0.0001 to 0.01, 0.001 for the SIL3. For SIL4, the PFD average is 0.00001 to 0.0001. So, similarly, the risk reduction, required risk reduction is on the inverse of this one. This is more than 10,000 and less than a lakh. So, these are the different values of the PFD for a continuous mode of operation. So, average frequency, danger frequency is failures per hour. For continuous and demand mode of operation, this is defined in failures per hour. So, for SIL1, it is greater than or equal to 10 power minus 6 to less than 10 power minus 5. SIL2, it is greater than 10 power minus 7 to less than 10 power minus 6. And for SIL3, it is greater than 10 power minus 8 to 10 power minus 7. And SIL4, it is greater than 10 power minus 9 to less than 10 power minus 8. Note that this is in hours. PFD budget. Now we'll know about the PFD budget, how it has to be taken into account. The probability of failure for a sys loop is really the sum of the probabilities of failure of the individual components, namely the sensors, logic solver, and final elements. So the PFD total is sum of sensors PFD plus logic solvers PFD plus final control elements PFD. So weightage factor is distributed as below. For sensors, it is 35%. For logic solver, it is 15%. For final control elements, it is 50%. Why it is kept differently, this weightage? Because logic solvers, they are located in the non-hazardous area in a safe location, and they have only electronic components parts available in the system. So probability of failure is very low. Hence, it is considered as 15%, the lowest of the three. And for the other two parts, sensors, it is kept at 35%. Sensors always stay in the field in the harsh environment with hot weather conditions, cold weather conditions, windy weather. Some areas it is snowy and with moisture as well. So with all those conditions, the cards inside the sensors, they have to work, and hence the probability of failure may increase compared to the logic solver. The final control element, which is on or false, it is kept at 50% because the wear and tear of the components are very high. We have the actuators, valve stem, and springs for the actuator to restore to original position, solenoid valves, and sometimes booster relays, pilot relays, like that. Many components are there. So there are number of mechanical components having motion. So there is a probability of failure on demand is very high. Any demand is placed to shut down the valve, it may fail sometimes. So that's why the budget for the final control elements is at a higher level. So by standard followed under many industrial convention, the portion of the overall failure probability is normally budgeted to the individual components in the following way. This is what is explained in a different methodology. 35% for the sensor, 10% for the logic solver, and 50% for the final element. This is why the distribution is having difference because of the wear and tear of the components, and which may have much impact on the probability of failure on demand. So this is a general industrial standard being used in across the industries. Okay. Further going on the PFD budget, analysis and industrial experience has shown that historically 50% of the time that a SIS fails, it is due to a failure of final element. And 35% of the time the failure reason is caused by a failure of the sensor. And 15% of the time real fail is caused by a logic solver. So therefore, when we design a SIS final limit but PFD to be 50%, the probability on failure on demand for the final elements is kept at 50% for a particular safety instrumented system loop. So the final element gets a higher weightage because of its more moving components and wear and tear of the different components. Comparatively, the sensor is having little lesser weightage of 35% because it is having very minimum moving components. Rest is all electronics and some training mechanism for the DP type of sensors or pressure sensors, etc. So movement, mechanical movement is very, very less compared to any element, and hence the weightage credit is little lower at 35%. And thirdly, on the logic solver part, it is only 15% because they are in the electronic parts and components working from a controlled environment. Mostly it is a non-hazardous area, and then deterioration of the electronics is less compared to the valve or sensors. So the weightage is given at 15%. So in all, putting the logic sensor, logic solver, and final element together with all associated components like a booster relays, an air pressure regulator, any pilot relays, solenoid valves, everything is there. So all the such components put together, the overall probability for a particular safety instrumented function shall be 100%. So that's what is mentioned. Finally, the total sums of the individual PFD average is 100%. Okay, thank you. Hello everyone, I am going to make a presentation on safety instrumented system, PFD probability of failure and demand formulas. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe. Why SIS probability of failure and demand is needed? Critical instrumented system prevent hazardous events of situations in which people could be injured or worse, and the environment could be polluted. So this is the main reason. So basically the safety instrumented systems are in place in the process industry to safeguard the personal and equipment. So the maintenance of such systems should be taken on a high priority. The standards IEC 61511 of 2017 and IEC 61508 2010 define the criteria for safety instrumented functions. These two standards, International Electrotechnical Commission standards 61511 and 61508, dictate the criteria for safety instrumented function. A safety instrument function shall be fit for purpose, preventing the identified hazard. The integrity level of a SIF defined as SIL 1, 2, 3 or 4 provide risk reduction. A SIF may be compromised by systematic failures and random hardware failures. SIF functionality may get worsened by means of any systematic failure or random failures. First PFD tool developed for use in the chemical company was based upon a standard industry method using IEC 61508. IEC 61508 defined the standards at first for the calculating the PFD, probability of failure and demand. Okay, how PFD is calculated? PFD is basically calculated using a method as per IEC 61508 standard. Calculated PFD takes into account the architecture of the SIS, safety instrumented function architecture, like 1 out of 1, 1 out of 2D, 1 out of 2, 2 out of 3, etc. So the estimated dangerous failure rate of each subsystem, a sensor, common cause, diagnostic coverage, proof test intervals, and repair times. So the calculated PFD is taking into account all these parameters: common cause, diagnostic coverage, proof test intervals, and repair times of the sensors, logic solvers, and final element components. Okay, approach for probability of failure and demand. In the process industry sector, the demand rate is often less frequent than once per year. When the plants are running safely, the demand is very less, unless otherwise there is a serious concern of any hazardous event. So the following PFD values are required. For the SIL 1, the PFD average should be less than 0.1. 10 per minus 1 is 0.1. For SIL 2, it should be less than 0.01. SIL 3 is PFD averages less than 10 power minus 3. SIL 4, PFD averages less than 10 power minus 4. So IEC 61511 provides the following information. Several modeling approaches are available, and the most appropriate approach is a matter for the analyst and can depend on the circumstances. So there are different approaches. So the designer and safety expert need to take the appropriate one, which is based on the circumstances as well. Approach for probability failure and demand. The available tools, there are many tools as mentioned before, and there are many tools and methods. So these are all the different tools: cost consequence analysis, reliability black diagrams, fault tree analysis, Markov models, Petri nets model, etc. These are the different tools available for calculating the probability of failure and demand. So people who are going into the advanced training of the safety instrumented system can understand few of the tools available. Factors to be considered for PFD average. What are the different factors that affect the PFD average? Configuration of the SIS, like 1 out of 1, 1 out of 2D, etc. Estimated rate of failure of each subsystem, sensors, logic solvers, and final elements includes detected and undetected failure. So some failures are detected, some failures goes undetected. Failure of an electronic card or electronic component in a final cut element, this is an undetected failure. A spurious trip causing by any mechanical plunger lock inside the solenoid valve or inside the pilot relay, it is an undetected failure. This cannot be detected upfront. Susceptibility of SIS to common cause failures, diagnostic coverage, proof test intervals, environmental and specific application efforts which may have an impact on the PFD average, repair times like mean time to restoration, and mode of SIF operation, in which mode it is operating, like low demand mode or next demand mode, etc. Estimate of dangerous failure rates, safe failure function. This is another terminology to calculate the dangerous failure rates. So these are the different factors that has to be considered for working out the PFD. Okay, below are the formulas for different configurations. So this is again based on the type of configuration, 1 out of 1, 1 out of 2, 1 out of 3, 2 out of 3, etc. So viewers can go through these formulas by themselves. So I'm not going to elaborate everything in detail. These are the different configurations possible based on which the different PFD average formulas are being given. So PFD average is the average probability of failure on demand. Here lambda du, dangerous undetected failure rate of the item n, and lambda du minimum, this is smallest of all dangerous undetected failures. T is a test period, beta is a common cause factor. So these are the different formulas available to calculate the PFD based on the type of configuration of the sensors and elements. Okay, 1 out of 2 example. So 1002 refers to 1 out of 2. So if either of this is for the sensor, we are going to give a small explanation. If either of the sensor is at its strip condition or logic, this is the or logic. For example, we are talking about a level sensor. So level sensor 1 is high or level sensor 2 is high. This is the combination for 1 out of 2. 2 out of 3. Supposing there are 3 sensors on the safety instrumented system. So 2 out of which 2 sensors need to go for tripping condition or failure. So if any 2 sensor is at its trip position, trip condition or logic, the level sensor 1 is high or level sensor 2 is high or 2 or 3 is high or 3 or 1 is high. These are the different combinations possible. So this is the 2 out of 3 voting. So here PFD sensor is a total of configuration, mean time to fail, diagnostics coverage, proof test interval, etc. So factors affecting PFD average. There are several sophisticated PFD calculation software. The PFD average used to be calculated very precisely. However, the results depend on common cause beta factor. As we know, there are multiple sensors available on a same output. Possibility of sensor getting failure is quite high. So that's why it is always advisable to have different sensors or different technology. Different sensors means different sensors with individual tappings for a differential pressure or pressure measurements, or different technology altogether. So proof test coverage and lifetime. A frequently used basis to determine beta factors is the informative annex D of IEC 61508-6. By filling in scores, a beta factor will be determined. Beta factor means the common cause factor, common cause failure. So beta is 5%, is a standard across the industry. Accordingly to a thorough performed study by safety experts, the actual common cause factor is in between 10 to 15%. Even though for the calculation purpose it is given as 5%, on the practicality, on the actual conditions, it may go as high as 10 to 15%. Thank you. Hello everyone, I am going to make a presentation on SIS validation and verification. This is an introduction topic. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe. SIS validation and verification. Safety instrumented system verification and validation are very critical for safe implementation and functioning of SIS, safety instrumented system. The performance of any new safety instrumented systems are to be verified and validated before the system is taken into service. Certain steps in the SIS work process comply with the requirements of SIS verification and validation. We have gone through the safety instrumented system work process, which is having multiple steps. So one of the step is calling for SIS verification and validation after the implementation of the field instrumentation sensors, valves, on-off valves, and logic solvers and all. So then it comes SIS verification, and subsequently when the process side connections everything is ready, it goes for the validation. It is necessary to use return loop verification procedures for the loop check and the commissioning of the SIF sensors, logic solvers, and final elements. Once the safety instrumented system related sensors, logic solver, and final control elements are placed in service, placed in line, they have to do the loop verification process, and subsequently when the systems are ready, the one for the complete loop, meaning which is including the functioning of the sensor, logic solver, and final elements together, they have to do an validation. We'll go over it in the coming slides. SIS verification, we will look into it. What is SIS verification? SIS verification is the activity of confirming by examination, checking of the SIS instrument, sensor, logic solver, and final control element meets the SIS design requirements of the safety function have been fulfilled. So this is to ensure that the all the SIS components are meeting the SIS design requirements. Second, SIS verification performed on the entire loop by simulating the process conditions and ensure the sensors respond properly and valves perform stroking. Return loop verification procedures shall be used for loop check and commissioning of the safety instrumented function sensors, logic solver, and final elements. So there has to be a return procedure in order that the testing goes properly, so and the verification is completed successfully. SIS verification confirms that a system element meets the design to or build to specifications. Throughout the system's life cycle, design solutions at all levels of the physical architecture are verified through a cost-effective combination of analysis, examination, demonstration, and testing, all of which can be aided by modeling and simulation. In certain cases, there is a level sensor which is requiring the tank to be filled up to 10 meters or 20 meters even. So it is practically difficult to do a level building. So in such cases, we have to do on the level sensor by simulation, either by filling the level chamber or by injecting the required equivalent composition of like water or any other equivalent media to bring the actual level until the 10 meters or 20 meters and ensure that the reading is appearing in the control room HMI stations. Also, if there are any alarms built in the particular level sensor in between the maximum range, that has to be verified as a part of the SIS verification process. Okay, SIS validation. SIS validation is the activity of demonstrating by inspection and testing that the safety related system under consideration after the installation meets in all respects the safety requirements specifications for the safety related system. The performance of safety instrumented system shall be both verified and validated before being placed into service, because safety instrumented system is the one safeguarding any hazards happening within the process area. So they have to be tested, verified, and the functioning of the safety instrumented system sensors, logic solver, and final element has to be validated. Validation means testing all the components together. Whenever a particular level sensor is going high, that is giving an indication to the logic solver, and the logic solver is performing the internal logic internal logics, and then sends the output to the valve to do the closure of the particular tanks income inlet valve. So this complete loop is known as testing is known as validation. Validation is one-time process in the entire sys life cycle, which is performed before commissioning of particular system or loop. So validation is done only once, whereas verification will be done whenever the sensors or final elements are being removed for the testing purpose or proof testing purpose, whenever they are taken away, or any maintenance or repairs is being done. Those times also the loop verification has to be done. Every time whenever the instrument is removed from location or repaired and put back in service, under those conditions, the instrument final elements has to be loop verified. Whereas validation is a complete testing of the sensor, logic solver, and final elements together. So it has to be done only one time during the safety instrument system life cycle, which is the first time of the commissioning of the particular system. Validation procedures shall functionally test the entire system during initial validation. Each element in a SIL loop, from measuring element through the logic solver to the final control device, shall be validated as defined in the validation procedure to fulfill the safety instrumented function. Validation activity has a clear meaning per IEC 61511 and IEC 61508. It is a validation of SIS in respect to SRS, Safety Requirement Specification, including implementation and resolution of resulting recommendation. Validation procedures shall functionally test the entire system during the initial validation. Each element in a SIL loop, from the measuring element through the logic solver to the final element, shall be validated as defined in the validation procedure to fulfill the safety instrumented function. So the verifying of the all components in a single stroke, meaning activating the sensors up to the trip level, very high level or very high temperature, very high pressure, and activation of the logic solvers logic commands, and closure of the respective inlet valves, isolation valves, emergency shutdown system valves. So all these three put together has to be tested in a single go. That's known as validation for the safety instrumented sensors system. Okay, we will go over the complete synopsis. Validation is the activity of demonstrating by inspection and testing that the safety related system under construction or translation meets in all respects the safety requirement specifications for the safety related system. The performance of safety instrumented system shall be both verified and validated before being placed into service. This is the most critical requirement for the safety instrumented system, sensors, logic solver, and final elements, to ensure that they operate at the time of demand, because we are always talking about the safety system and all. They are in the service, they are put in the process plants for the safety, for maintaining the safety of the plant and safeguard of the operation personnel, maintenance personnel, and the personnel working around, as well as the equipment and environment. So no chance shall be taken to defeat the purpose, the working of those instruments, valves, etc. So the validation and verification has to be performed as per the design requirements and as per the written procedures to ensure that they operate perfectly during the time of demand, because during the time of demand they have to act at that time, testing and see whether it can work or no, like that. the chance cannot be taken, because being the safety instrumented system, we have to be given utmost priority. Thank you. Hello everyone, I am going to make a presentation on SIS validation and verification detailed approach. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe. Need for SIS verification validation. While a process is being designed, particularly one where products are flammable or toxic, safety specialists study it carefully to determine all the areas where things could go wrong. For example, what will happen if this valve is stuck? What if the reactors get too hot? Could this tank overflow? Then the specialists imagine what kinds of hazards or damage these situations could cause if realized, and likelihood of a problem actually developing. So while making a plant design, process design, especially for the petrochemical, oil and gas industry, where the flammable gases, hydrocarbons are present, the safety specialist along with the team of process experts sit together and make a discussion. This is what the initial study of ASAP, etc. So in this condition, these questions are being put between the teams and a solution is arrived at. If they believe the consequences of the specific problem occurring are beyond what the company is willing to risk, safety specialists design a remedy and create a safety instrumented function to carry it out. In a complex unit, there can be hundreds of individual safety instrumented functions. The hazards they cover may overlap, creating multiple layers of protection. Therefore, if one fails or proves to be inadequate, another remains to avoid a more drastic escalation. Thus, upon implementation, SIS sensors, logic solvers, and final elements to be tested to overcome any hazards. So whenever the process team along with the safety experts sit together and put the questions between them about the any hazardous conditions that can happen, they find out and come out with a remedy which is acceptable for the company's policies and the governmental regulations, and accordingly several protection layers are built. That's why they are known as independent protection layers. We have seen in earlier presentations about the independent protection layers. So different layers are built. So in some cases they may overlap each other. So if there is a failure of a previous layer, first layer, the second layer, for example, if the failure of the DCS protection layer happens, so the safety instrument system layer comes into picture to take an action. In case safety instrument system layer protection fails, the relief valves, next level of protection, mechanical relief valves comes into picture. Like that, many independent layers are there which can act independently. They come into picture. But since we are focusing on the safety instrumented system, so our thrust will be on the safety instrumented functions. And in this topic, we are discussing about the verification and validation. So based on the safety instrumented function requirement, the sensors, logic solvers, and final elements are placed in the system in the process area. So they have to be verified and validated before placing into service. SIS validation and verification, we will go in further details. Verification and validation are very critical for safe implementation and functioning of safety instrumented system. Verification takes the form of checking key design deliverables as per the input documentation. So therefore the documentation is very important, based on which the design conditions will be verified. Verification shall be carried out by engineers who have more experience in the field instrumentation, installation standards and maintenance. So this is and the practicality in the field level, they will be carried out by experienced guys who have wide knowledge about the installation standards, maintenance, etc. In addition to this, depending on the SIS implemented in the plant, the verifier may have to be independent of the project from another department or even from outside the organizations. Usually the verifier may be a third person who was not involved in the basic design and engineering of the project and implementation, and he will put in a different eye view so that any faults, any errors that had happened during the implementation can be identified and can be corrected before going for the verification step. This is the intent. Validation is the process of checking design outputs comply with the design basis functionality as detailed in the safety requirement specification. So this is to check the design outputs as of the entire loop which we had discussed earlier also, to confirm the functionality. SIS verification details. Details of SIS verification. Verification according to the SIS work process covers loop design, instrument selection, instrument installation, logic solver hardware or software for the instrumented protection layer under the BPCS and SIS. Sometimes BPCS also acting as a protection layer as per the LOPA study, layer of protection analysis study. So in such cases, so verification covers the BPCS part wherever it is implemented for the safety function and safety instrumented system. Written verification procedures, measures and techniques including the implementation. Roles involved with the SIS verification including personnel name, departments and organization responsible for these activities. So these are the different requirements for the SIS verification. Software program also to be verified for proper coding, system memory, redundancy required, and then subjected to safety coach review. The verification has to be conducted in two phases for the software application program. Design verification involves the detailed check of instrument and automation design documentation prior to approval of the final design. This is done during the design stage. And installation verification intends to verify the field installation and final software application code as per the functional requirements and implementation of applicable safety standards. So the second step is being done upon installation to verify the hardware and software. Detail of SIS verification. SIS documents auditability of the documentation confirming the completion of SIS verification that has been performed. Okay, SIS validation. What is SIS validation? SIS validation procedure shall be developed by a team of instrument design lead and operation representative, because they are the people having more knowledge about the complete process and the safety instrumented function which is doing the protection, which will be doing the protection. So the validation procedure has to be developed jointly by instrument design lead and operation representative, and define all the required to test SIS loop during the including the timing for specific tasks with responsible personnel and expected results. So which has to define all the required parameters that needs to be tested during the SIS loop. Validation involves bringing all available sensors for the SIS loop under commissioning to alarm condition, verifying the activation of the appropriate alarm and to ensure moving of the final elements to their fail-safe position within the specified time. So validation involves testing of sensor, logic solver action and the final element action together. So in this testing, it has to be ensured that the final elements goes to the fail-safe position in the specified time. Detailed steps in validation: confirming the logic solver activation, the required outputs and operator interfaces, and field verify movement of final elements to their fail-safe position within the specified time. This full loop validation applies to new or modified SIS safety instrumented system functions and for the BPCS basic process control system with the LOPA scenario. Wherever in the LOPA sheet, layer protection analysis worksheet, the BPCS protection is identified, there also the validation has to be performed. Okay, we'll just go over the small example in a process. For example, this is one reactor which is being fed with the feedstock of the load line for the process, and the level is being built, is being raised here, and the pressure sensor, level sensor and pressure transmitters, they are the components involved, and this loop involves the protection due to overpressure. This is example, and this is the outlet, this is the second inlet line of a different product maybe, and the reactor is being heated through a steam coil with the control valve being in line, and the tank's products pressure is being measured using the pressure transmitters, which is with the safety instrumented system, and another pressure transmitter for the basic process control system, and level transmitter, which is again for the basic process control system. Because since you see this two are in black color, they are going to the measurement function in the basic process control system processes. This red lines indicate that they are part of the safety instrumented system. So the pressure sensor, pressure transmitter is connected to a logic solver, safety instrumented system logic solver, and that output is going to the relief valve, which is a emergency shutdown valve. So when this valve is open, this goes to the holding tank. So in the normal operation, probably this valve may be in closed position. In the normal operation, this valve in closed position. So whenever the pressure exceeds the tank, so this opens and then relieve the product into the next vessel. So here this particular vessel's pressure going high will be detected by this pressure transmitter, and the logic solver gives a command to open this valve. So what is the validation here? Building of the pressure up to the set point, maybe 10 kg per square centimeter or 20 kg per square centimeter according to the process, and which will give an indication to the logic solver to open this valve. So this is testing of the pressure sensors, action of the logic solver and action of the valve. All this testing together is known as SIS validation. SIS validation procedure of application program. Validation of the application program shall determine whether all of the specified application program safety requirements are correctly performed. The application program does not jeopardize the safety requirements under SIS fault conditions and in degraded modes of operation, and for BPCS fault conditions for any interface between SIS and BPCS. In the process plants, there are many data flowing between the basic process control system and safety instrumented system. So whenever there is any fault in the basic process control system, either in the processor or any of the input or output modules, that should not have an impact on the safety instrumented system, because this communication will keep on going, but it is only for the data communication, data exchange, and usage in the logic program wherever it is mentioned or wherever it is coded. So any failure, any disturbance on the basic process control system, logic solver or input output model should not have an impact on the SIS system. The application program does not jeopardize the safety requirements by executing unused software functionality. And in the application program software, there could be rarely some programs written and modified due to the process requirements and which left unnoticed, and they may remain, and it may do the execution while the process is running. It may do the execution, but actually may not be connected to any output, thereby it will not have any impact on the process. So any such condition should not have an impact for the safety instrumented system testing. That's the part of validation. Restoration of the system after SIS validation. So during SIS validation, it may be required to do lot of simulations, lot of bypasses to ensure that the pressure or level or temperature are going to the high state, and then giving a command to close the respective confinement valves. So whenever the testing is completed, the SIS validation is completed, it is mandatory to restore them to the original state. After the SIS validation and prior to the identified hazards being present, following activities shall be carried out. All bypass functions, logic solver and sensor forces and disabled alarms shall be returned to their normal position. All process isolation valves to be set according to the process startup requirements and procedures. All test materials, example fluids, nitrogen, etc., shall be removed. There could be some fluids or nitrogen may be injected into the process lines to ensure that sensors like pressure sensor is reading or the process temperature is reading correctly as per the requirement, etc. And those has to be removed, because during the actual process condition, there could be some hydrocarbons being sent to the same process line, which may create an hazard. Likewise, all the bypass functions and force means that is simulating for a particular level, for a particular pressure to come and then do the logic action. So sometime it may be not feasible to do the field simulation, and thereby it is being done in the application program. So those has to be removed as part of restoration process. All commissioning overrides and force permissions shall be removed. Sometimes the SIS bypasses are forgotten to be restored to normalcy due to the urgency of equipment, system and plant startup. This is very vital, and proper care shall be taken to restore the bypasses, timer constant settings to the actual running conditions. It is very important, otherwise the program do execute and then it can misbehave. The actual operations can misbehave, and which is another point of hazard or probability of chances to go for a tripping or never. Whenever it is in bypass condition, sometimes the plants can never trip even though the actual process condition goes beyond the limit. So this is a very dangerous situation which has to be avoided. All the bypasses, forces of any time constants or any other time settings to be removed carefully, so that the process will run healthily with all the safety requirements in place, with all the protections in place to ensure the safe operation of the process and plants. Thank you. Hello everyone, I am going to make a presentation on safety instrumented system, instruments, inline proof testing. This is a basics topic. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe. Sys instruments inline testing is quite useful for sys instruments valves. Inline testing enables safe operation and functioning of sys safety instrumented system. In this article, testing refers to proof testing of sys instruments as well as valves. End users should consult vendor safety manuals to determine recommended diagnostic online and offline proof test methods and associated coverage. Ensure system design and operation procedures are in place to support testing and repair activities. Every product manufacturer for the sensors, flow sensors, pressure sensors, temperature sensors, DP level sensors, along with the transmitters, as well as the valves, final instruments valves, those manufacturers, they need to prepare a safety manual pertaining to the product about the type of electronic card used and its failure rate, that lambda values, etc. A lot of safety related concerns which are required by the IEC standards, International Committee standards, that follows IEC 61508 recommendations, has to be updated in their safety manual and sent along with the product whenever the instruments are being supplied as a safety instruments. So the user has to look into the different aspects to determine the different online offline test methods possible with that instruments. Moreover, it is imperative to conduct proof tests at the intervals in the safety requirement specifications. In general, the safety requirement specification determines the proof test coverage to be done in certain period, like 2 years, 3 years, 4 years, depending on the type of instrument configuration as well as the number of instruments available and the voting systems. It has different categories based on which the proof testing period is being determined and entered into the safety requirement specification form. The purpose of a SIS is to reduce risk through instrumentation. Proof testing is an effective means to detect failures that reduce system reliability for low demand shifts and thus enable timely repair. So why do we do proof test? Because this is to ensure that undetected failures cannot happen, because during every proof testing, the internals, the electronics are being checked and the instruments it made healthy as a new. So that's why the proof testing has to be conducted without fail at the calculated intervals. An operation team must understand how decisions such as extending proof test intervals, turnaround cycle, affect demand rate and sustainability. Supposing some instruments are planned to be tested in 5 years and the plant's turnaround period comes as 6 years. So, in this case, whether it is good to isolate the instrument or isolate the equipment to do the proof test in 5 years, or it is wise to keep it running until 6 years. So the decision has to be taken cautiously by the operations team along with the safety experts, and which shall not impact the sys reliability also. Diagnostics as well as online and offline proof testing can be useful in detecting device failures, so repairs can be implemented and devices return to services. So the diagnostics is an additional feature on this safety instrument system, so which can help detect the device failures, if any. Okay, inline safe testing, we'll just go through a small process related graphic. Here this is a final control element which is being fed through a logic solver, and this is the flow sensor available in the process piping, which is giving an input to the logic solver, and to test it, either it can be tested directly using a hot device. It is one type of device that can use to test the instruments and see the calibration parameters, any time constants, other settings, everything, including the range, instrument tag, instrument description, etc. And value can be simulated to ensure that the reading happens as per the calibration, or if there is a requirement, the instrument need to be calibrated. Similarly, there is a loop calibrator which can be used to calibrate the valve and stroke it. In this case, being an on-off valve, it will be stroked from 0 to 100% by giving a command from the DCS. So this is just given as a reference, as a total loop safety integrity level is which is equal to PFD of PLC, PFD of sensor, and PFD of final control element. So this is for the understanding. So in this case, the instruments are being tested inline. Okay. Requirements for better inline testing. Inline testing implies that testing can be accomplished without a process shutdown. There are several requirements to be considered for accomplishing this. Redundancy is mostly used for sys components, especially sensors, wherever possible based on configuration. A test of one sys sensor can be done while the other sys sensor continue to function. If there are two sensors, obviously it is easy to do the maintenance and proof testing on one sensor, keeping the other sensor in line for the safety protection functions. Bypasses could be installed around sys final limits valves so that testing and maintenance can occur while the process is in operation. If there is a bypass, that valve can be opened according to the process requirement, and the main valve, which is the emergency shutdown valve, can be stroked and proof testing can be performed so that the process keeps on running. In batch plants, inline testing might be accomplished by shutting down one train of equipment while keeping the rest of the plant running to eliminate or reduce any potential production loss. If it is a batch plant, there may be identical trains, which is known as a similar kind of product will be coming out from that process. There could be 5 lines, 6 lines, 8 lines, depending on the capacity of the plant. So if that be the case, one line can be easily isolated and the product output which is coming from that particular line can be shared to the running lines. So in this case also, production will not be affected. So whatever the line to be tested only will be isolated, whereas other lines will be running maybe at the same capacity or at a higher capacity to accommodate the loss of production for the particular line being tested. Documenting occurrences where the required automatic action has occurred during the operation of the plant, such as a pump trip based on the same process condition that is required by the LOPA function. So the documentation has to be kept thoroughly so that any incidents about the failures can be analyzed immediately. And wherever there is a requirement, the repair and maintenance actions can be taken up. Okay, automated testing and record keeping may be an option in some plants for a subset of the testing requirements. But all the aspects of testing requirements, including visual inspection of the installation, leak testing, etc., must be met according to the required calculated proof test intervals. Some plants may overrule the proper documentation requirements and which may eventually call for some safety related concerns if at all happening in future. Then the auditors who are coming for the auditing and to evaluate what kind of damages happen and all, they may go through the records about the testing of the safety instruments and valves for several years, maybe 10 years, 15 years from that period. They found that the records are not being properly taken or not done. So the insurance claims cannot be done. This is the one concern. Automated testing and record keeping may be an option in some plants for a subset of the testing requirements, but all the experts for the testing requirements must be met according to the calculated proof test interval. Thank you. Hello everyone, I am going to make a presentation on safety instrumented system, inline proof testing for instruments and valves. This is a detailed presentation. Media is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe. Safety instrumented systems, inline testing is very much useful for safety instrument system valves. Inline testing enables safe operation and functioning of sys as process plants are running continuously for many years, say 6 or 8 years per the process requirement. It's quite difficult to find an opportunity for proof testing of the sys instruments and valves. It is not practically possible for shutting down a part of the system, plant or equipment for the sake of proof testing. Hence, modern day technology needs the instrument valve suppliers to find an equivalent devices that enable online testing. Alternately, the piping system is designed in such a way that valves can be tested online without taking into workshop. The main intent of this presentation is to understand how it is feasible to do an inline testing, because safety instrumented system need to go for a proof testing in a decided cycle. It could be 2 years, 3 years, or 4 years based on the type of safety integrity level, type of the configuration of the sensors or final control elements. Accordingly, that proof test interval may vary. Eventually, since the plants are running continuously for many years, it may be possible in circumstances wherever there are standby instruments on the same service. But if there are no standby instruments, making a proof testing could be a challenge because it may hamper the process. So, the method to identify an inline testing facility which can test the internals of the electronics and do an online diagnostics to ensure that the instruments are healthy enough to take an action in case of any hazard. Benefits of inline testing. The benefits common to all of the options above: minimize the downtime and reduce the maintenance costs for sys-proof testing. Automated inline testing, like triggering a small movement of the valve, say 2 to 3% using smart digital positioners, may bring value by extending or eliminating offline proof testing, but may require additional instruments for comparison, like secondary flow pressure transmitter or mass flow meter, etc. So, by putting a smart digital positioners in the valves, it is possible to move the valves little bit to ensure that they are working properly as per the process requirement. Flow meter inline testing. Now we will go over the flow meter. In the future slides, I am going to describe about the valves inline testing as well. For the simple DP means differential pressure type of cell and RFI spray types. The most common approach is to inject a differential pressure signal simulating the flow into the cell. However, this does not test the impulse lines and isolation or equalization valves for possible blockage. So, whenever the DP type of instruments are being tested by injecting the fluid, it tests on the sensor part only. But actually, from the piping, there are impulse line running up to the flow sensor, and that part there could be choking due to that type of process being handled. It could be a solidifying service sometimes. So, there are possibilities that it can get choked on the main impulse lines, or equalization means to balance the pressure between high pressure impulse and low pressure impulse. There will be an equalization line. So, that could also possibly block over the period of time. Regular maintenance, impulse line flushing and draining on a redundant sensor, and calibration of the sensor instrumentation enhances the inline testing and the reading from the instrument. If there are standby instruments, then it's very easy. So, the instrument under testing can be used to drain, flush the instrument and vent any trapped gases, etc. But in case of any common tapping from the same impulse line, this will be a challenge again. So, that's why it is recommended to go for a separate taping. This is another effect known as common cause trouble. So, again, during the engineering stage, that has to be taken care. But wherever there is separate instrument line tapping for these devices, it is possible to isolate the device which is being tested and keep the system live running. Flow meter inline testing further go on. Flow meter installations must include the necessary configuration to allow the proof testing of the instrument and the required testing interval. The type of installation required will depend on the required test interval and the desired shutdown interval for the plant. The following online diagrams examples for the installation that allow testing to be accomplished. Actually, if there are two diagrams, one for the single instrument, there is a single flow element instrument. There could be one drain valve upstream of the flow element to drain and enable it to be tested online. If there are two flow meters in series, this drain valve has to be in the middle. So, it can be, this particular one can be drained, keeping this flow meter in active condition, running condition, and on the other hand, the second meter can be drained and tested. Temperature elements inline test. We saw about the flow elements inline testing, and next one is temperature elements inline testing. Temperature elements installed in pockets of a process gas heater, furnace are tested online, as most of these installations form part of triple redundant systems with a 2 out of 3 voting. And there are many installations with a 2 out of 3 combination. They use a thermocouple or PT100 simulator from the connection at the head and check for ingress, integrity and connection security. How to test this temperature elements? To inject the signal from the transmitter head so that the entire loop until the control room will be tested. So, and ensure that the loop is healthy enough. When inline, the technicians check for the differences in reading between the three instruments to detect the drift. So, whenever it is being tested, the technician may understand if there are any big drift between the three instruments. To improve confidence and reliability, the maintenance team shall plan to change the thermocouple regularly in addition to simulation and check contact with the end of the packet. So, simulation and testing is one method which is more economical, but since the temperature elements in some cases they are subjected to continuous wear and tear, they may be inserted inside a furnace or a boiler or any high temperature containing fluids, so they are subjected to high wear and tear. Such kind of installations can be recommended to go for a replacement after maybe 2 turnaround intervals. If the turnaround interval is 6 years, after 2 turnaround intervals, after 12 years, that particular transmitter element can be replaced as a better practice and good engineering. Temperature elements in inline testing. Another method of inline test is to inject a current, voltage or resistance signal to simulate temperature and so test the operation of the safety system. The signal can be injected on some type of probes together with the electronics, and so only the sensing element is not tested. So practically in many cases the sensing element may be inserted inside the process piping or inserted inside the furnace, so it is difficult to remove such installations. So an identical thermocouple or PT100 elements can be used as a testing element and connected to the same transmitter head to up to the control room. So, and that can be tested. On some other probes, the signal is injected after the electronics, particularly where the installations are on higher elevations and unreachable locations. Again, some more installations and the temperature elements may be at very high level, at 30 meter, 40 meter, 50 meter, etc. So, it is practically difficult for the electrical instrument technician to climb up and then do the testing. In such cases, the injection can be done from the nearest junction box head after the temperature sensor. Now it comes to valve testing. Why this valve testing is important? With the periods between plant shutdowns being extended sometimes, emergency shutdown valves may remain in open position without movement for lengthy periods. Experience has shown that after extended periods without movement, there is a tendency for the valve to stick, because the valves which are outside a vessel or which are outside and the outlet of the compressor or the outlet of the turbine, etc., they remain open for years together. Since the movement is not there, naturally the chance of stickiness and dust accumulating into the valve stem, thereby affecting the valve stem movement, etc., are quite possible. So that has to be avoided. This would result in the shutdown of the system, result in the shutdown system failing to operate in the event of a genuine demand of the shutdown system, despite all other tests on the system being completed satisfactorily. When the valves are sticky, even though there is a command coming from the logic solver for closing that valve, it is not possible for that valve to get closed, because being stickiness and dust or moisture around that valve stem may restrict it to. So this has to be taken care of. How to overcome this? An inline testing application such as smart valve monitoring can monitor the emergency shutdown system valve for faults based on comparing an original full pressure fingerprint of the ESD emergency shutdown system valve assembly and components such as solenoid valves against a partial stroke test. Normally, whenever the valves are being supplied or they are being overhauled after a period of 8 years or 16 years, or depending on the turnaround interval, 6 years or 12 years. So, what happens after that? This period, 6 or 12 years, initially, during the installation of those such valves, there will be a reading taken about the healthiness, about the valve movement, the time taken, and time taken to open, time taken to close, etc. So this is captured in an electronic format or in a record format, which is known as a valve signature. And whenever the valve is being tested as a proof test interval, again it can be stoked wherever there is a bypass arrangement for that particular process. This valve can be stoked and the operation time can be noted down. Their system can perform all the tests at the ESD valve designed closure speed without shutting plant down. So the smart valve monitoring can support to test the valve without being actually closing fully, like by a small jerk of movement. It can ensure that the valve is capable of doing its action whenever there is a demand. Okay. Procedure to test adding drain valves wherever system control limits are in place. The typical drawing depicts the installation requirement. This helps to inject instrument air at the upstream and ensure no leak in the ESD. So this is what mentioned. The drain valves can be provided at the upstream and downstream of the process line. Similarly, here on the upstream and the downstream of the process line. This can support to inject fluid to test the valve. So this is a process piping showing the emergency shutdown valve or safety system shutdown valve. Both are same, and these are manual block valves. Similarly, the other two are manual block valves with one safety shutdown valve with a vent valve going back to the atmosphere. So in this case, by providing two drain valves at the upstream and downstream, it is possible to do the online testing. A manual block and spectacle blind is typically installed at the safe distance from the boiler, etc. Example, at the battery limits or 50 feet radius from the boiler. This is what mentioned. So this piping will be in the boiler area, and the previous piping can be 50 feet away. And I mean not previous piping, the spectacle blind means there is a possibility to isolate it and remove. So this can be at a 50 feet away. Okay, this is a typical arrangement of the valve testing device. This is a smart positioner or digital valve positioners, and 0 to 24 volts the output command is being sent to the solenoid valve to operate the main valve. So this valves for the actuation of the output, the pressure is being measured by this digital valve positioner, and the solenoid valves opening, closing, and its healthiness also being monitored by the digital valve positioner. Besides it, it is having one more valve position indicator inside the body. So this is into the BCS using a 4 to 20 milliamp transmitter signal. There will be sensor inside the actuator assembly, and it will give a signal to this speed sensor, and 4 to 20 milliamps will be sent as an analog signal input to the cards in the logic solver to read the actual percentage opening. So this is a typical drawing showing the different connections for an emergency shutdown valve. Such kind of arrangement with an digital valve positioner, it is possible to do an inline stroke testing. Okay, procedure to test. Alternate method, there are different methods. So alternate method is to test emergency shutdown valves in line by blocking the solenoid vent with a pressure gauge and operating the valve. This is like a mechanical method of testing. This is also possible. This caused the valve to move slightly and also gave an indication on the pressure gauge of the solenoid operation. This is not a standard practice. The system may work well, though the installation and subsequent removal of the gauge would need to be carefully controlled. Doing a mechanical test is not a standard one, so it may work well whenever it is being installed. Whenever the gauge is removed and is placed in service, it may be good. But whenever it is required to remove the gauge, during the removal time and the insertion of the gauge, there will be some time lapse, which may lead to instrument air being venting out and closure of such valve. Another method that valves can often only be tested when the plant is being shut down or actually shut down. That means whenever the plant is going for a shutdown by manual action, or whenever it is getting actual shutdown, that time the valve can be tested. Tests are generally limited to tripping the valve and observing that it moves to the open or closed position. Because whenever the plant shutdown is there, either it is a planned shutdown or it is an automatic shutdown for XYZ reasons, closure of those valves, closure or opening in some cases of those valves can be taken as a testing. This test realizes that they can only carry out limited checks on the effects on flows through the valve, there is no bypass. So if there is no bypass, it is very difficult to understand whether the valve is doing a proper flow passing through it. Thank you. Hello, I am going to make a presentation on Safety Instrumented System Application Program Basics. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe. Sys application program is vital for sys logic solvers. Users has to follow a uniform approach based on the conditions set by international safety approval agencies for successful safety instrumented system implementation, sys implementation. As per IEC 61511 standards, the application program of the sys shall be in accordance with the application program safety requirements and all the requirements for all cell up to and including cell level 3. Meaning the program by different manufacturers on a different application should follow an uniform standard. Otherwise, it may be confusing and the real safety point of view, the required safety may not be able to be achieved. That's why international agencies are there to govern and set the model. Accordingly, all the individual manufacturers has to develop the strategies. Similarly, the engineering and design companies, the manufacturing plants, they need to follow an uniform approach to implement the safety instrumented functions. Even if there are multiple vendors supplied the safety instrumented system across the plant, the type of blocks, type of programming structure has to be consistent across many plants. Sys application program as defined in ANSI and ISA 84. These are the two international standards. The user shall ensure the application logic is documented in a clear, precise and complete way. Only application logic under the control of a formal revision and release control program shall be provided and considered for use on a safety instrumented system. The application logic formal revision and release control program shall be provided and maintained by the user. There could be a requirement in the applications in the process for any small changes, or it could be sometimes it could be major change due to a project's implementation. So there may be multiple revisions coming on the programs. Every time whenever there is an revision, that has to be properly maintained and updated. There could be some small changes, there could be some major changes which has to be recorded and updated, and the earlier version of the program before any change has to be saved in a separate portable media or something, so that there is any chance of program getting corrupted or any error occurred during the downloading of the program, it will be useful for the user to recover from the old program available in his hand. So that's why the revision has to be maintained strictly and the procedures has to be followed. Only software under the control of a formal revision and release control program shall be provided and considered for use on a sys. The embedded software and utility software formal revision and release control programs shall be provided and maintained by the sys manufacturers. The manufacturers shall also provide and maintain a bug list and advise customers of any software faults which may lead to a failure to function on demand. The manufacturers always develop the program and test it in their bench. So even after testing, there could be a possibility for a bug in a program when the application is running on the processor. There could be an error which may lead to the particular part of the plant or equipment going for a shutdown. So if there are any program bugs is found by the manufacturers, that has to be notified to the all respective customers who are using their products. This is something like a Microsoft for the operating systems goes for multiple revisions and changes due to any enhancements. The user shall not modify the sys embedded or utility software because they are pre-configured, so the user should not play on it and then do any modifications on the embedded software. The user shall ensure the application software is documented in a clear, precise, and complete way. The application software formulations and lists and programs shall be maintained by the user. These are all the different conditions set by the ANSI ISA 84. This is a sample program. The parameter assignments and other input parameters will be available. So the user or engineering person involved in the plant maintenance, they will pull the relevant blocks and then add it to it to build the required logics. So the logic we basically built by the engineering procurement and construction. After the engineering procurement and during the construction, and it will be vetted by many people who are all having the control system as well as process knowledge, and it will be implemented and rolled out for the plant operations. Whenever any changes is required to be implemented due to the process needs or the project implemented in the particular area, that portion of the logic has to be updated according to the site requirement, and that has to be uploaded to the respective programming processor CPU of the safety instrument system, and that can be monitored by an engineering station which could be located in a remote area. So this is a frequent activity during the operation of a plant. So similarly, for the application software and embedded software, there could be diagnosis available. Each manufacturer will have their own independent diagnostic facility, and the program could be in a different manner for the diagnosis. So if there are any requirements for any error happening, so the diagnosis software will help to troubleshoot and find the fault where it is happening. Application program configuration requirements. The programming application code is to be taken up subsequent to logic solver selection to execute the safety instrumented functions. The application program must follow manufacturer's specifications described in the safety manual to ensure safety and reliability. So the ultimate aim for each plant owner is to run the plant safely without any hazard, or even if there is an hazard happening in the plant, that has to be contained without going for a major disaster. It could be the human being getting injured or getting life threat, or the equipment getting damaged due to the safety hazard, or the hazard not be contained due to some reasons keeps on spreading. It may be spoiling the community surrounding the plant area. So all these things has to be avoided and controlled as minimum as possible by the respective plant managers. Supporting documentation such as programming criteria, safety manual, and a specific platform's design specification is required for application program development. Each manufacturer has to prepare a safety manual to do any diagnosis and troubleshooting on their CPU and processors and other input-output modules, communication models, etc. So in that they need to provide the different failure rate, because all the manufacturers need to undergo the testing as per the requirements set by the international agencies like IEC, ANSI, ISA and all, and they have to bring out the results which will be again verified and approved by the respective agencies. SIFs implemented on a certified logic solver must follow the safety manual for that logic solver, which are subjected to international safety certification agencies. This is what I explained earlier. Written security procedures shall exist to prevent unauthorized or inadvertent changes in the software program. Only experienced guys who are all having familiar hands-on experience on the safety instrumented system to work with the logic solver and who are all certified to work on the particular area can only do the modifications, not the persons who belongs to different plant area. Even though he is knowledgeable, he may not be having a certification to work on a different plant. Like for example, from plant A, the engineer cannot come and directly work in plant B. So in case of any requirement, the plant B engineer is not available, is sick, is not reporting to duty. In such cases, based on their manager's approval, plant manager's approval, the person from plant A to can come and work in the plant B, because plant process could be different from each plant. So the persons who are all working in the respective plant will undergo the certification requirement, and it has to be reviewed and revalidated from time to time, maybe 3 years or 5 years based on the requirement. Plant production in charge shall designate those persons allowed to make changes to the code and those that are allowed to perform the program loads. Wherever SIF and BPCS application programs are implemented on a single certified logic solver, the SIF code must either be separated from BPCS code, like separate partitions, or be clearly identified in the program so that it can be distinguished from other program. Whenever any particular logic is being utilized for the safety applications, that has to be highlighted, and it should not be a part of the normal basic process control system loop. All safety instrumented systems and approved critical instrumented systems shall have safety trip set points protected from unauthorized changes, for example, unchangeable constants. Like there could be a number of timers, constants used in the programming. Those can be modified only by the competent personnel. Not everyone should be able to do the changes. Different level of authorization for technician, supervisor, and plant control engineers shall be configured. If designs employing single component, that is one out of one configurations with the diagnosis and automatic testing, must have an alarm on detected failure. The SIF final limit must either go immediately to the safe state or a risk mitigation hazard assessment and alternate management to be developed by operation personnel, and plant operators need to be trained in this response to sustain the plant operations when SIS instruments goes out of service. The SIS instruments has to work in case of any critical hazard and any demand arising. But should there be any failure of such instrument, then the operation personnel need to take over and they need to do some manual operations to protect their plant and equipment. That's why it is very essential for the operation personnel to have an adequate knowledge on the safety instrumentation part, basic requirements, so that in case those instruments did not function or some valves did not function, operations will have a idea to do a manual isolation of the process in case of any safety incident happening in that particular area. The safety instrumented system sensors and elements shall be clearly marked on the P&IDs in the computer software documentation. The piping and instrumentation diagram should have clear marking about the safety instrumented system sensors and final elements. This is to make sure and aware that the operations or maintenance personnel who is going to work on it will have a caution, because they cannot go and simply close the isolation valves of a transmitter in case of a safety instrumented system transmitter. So because this will lead to non-sensing of the process and it may create a trouble for the particular section of the plant. New or modified safety function programming shall be verified against its specification by application code review or simulation, emulator software where possible, assessment by an independent safety system coach, and validated by functional tests prior to initial operations. This is also a requirement. In most of the manufacturers, they provide an emulation software for their applications. So instead of the real plant process to be a real plant process happening with the parameters, the control system engineers or instrumentation engineers working in that plant area, they will have an access to work on the emulator, which means it's a simulation. They can simulate the parameters required and test the program, application program for its effectiveness. So this is a mandatory step before the initial rollout of the particular plant's safety instrumented system. The safety requirement specification and safety instrumented system work process meets the intent of this requirement. These two rules which will set the requirement of the safety instrumented function application program. Okay, thank you. Hello everyone, I'm going to make a presentation on safety instrumented system application program. It's a detailed requirements, and this video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe. This application program is very vital for syslogic solvers. Users has to follow a uniform approach based on the conditions set by the international safety approval agencies for successful sys implementation. There are many standards governing the safety instrumented system implementation and maintenance, commissioning, decommissioning, etc. So all the sys related logic solver developers need to undergo those requirements and then meet the rules set by the international agencies. As per the IEC 61511 standards, the application program of the sys shall be in accordance with the application program safety requirements and all the requirements for all cell up to and including cell 3. This is all these application requirements are eligible up to cell 3. Sys application program detailed requirements. The safety instrumented system, sensor and file elements shall be clearly marked on the P&IDs and in the computer software documentation. Implementation of sys design manual recommendations to meet this requirement, because piping and instrumentation diagram is a basic drawing for the understanding the plant and how is the piping is connected and what are the instruments available across the piping, and there could be some additional layout drawings, plant, plot view, everything. So the P&ID will have a clear idea for the operations and maintenance engineers for understanding the process. New or modified safety function programming shall be verified against its specification by application code review or simulation by emulator software wherever possible, assessment by an independent safety system coach, and validated by function tests prior to initial operations. All the programs can be simulated and tested before going in the real process operation. So this testing has to be vetted by a safety system expert, and that has to be tested. The complete functional test to be tested before the system is being put into service, is being put into process. The safety requirement specifications and safety instrumented system work process meets the intent of this requirement. These two specific documentation which are related to the safety instrumented system for the respective plant governs the requirement. So that has to meet, application program development has to meet the requirements. So there are multiple additional requirements. We'll go through those items. First one is templates. Standard software functions are to be used wherever possible for safety system programming. Standard templates are available for common sys functions on most certified systems. The safety interlock programming guide shall define file structure when implementing safety instrumented system. Multiple vendors has to follow an uniform approach to develop the standard blocks, function blocks, and timers, constants, etc. And that has to be reviewed and approved by the international agencies. So the template for different manufacturers on a similar same application should be identical for ease of traceability and maintenance requirements. Second one is security. Extreme care to be considered for safety application program code must provide protection against changes to sensor ranges, sensors being placed in manual, final controlments being placed into non-safe operation conditions, changes to the safety instrumented system, set points and delay timers, and SIF conditions being bypassed. So bypass, change of times, constants, etc. has to be minimized to much extent possible. Accessing application program. Assessments of new application program and safety program changes are required prior to implementation. Plant control engineers, safety system coaches who are not involved in the application program design and development to conduct assessments for safety application program. The safety system coach to complete the program review prior to startup of new or modified safety instrumented system readiness to be put into service. Because whenever the program is developed by a particular engineer A, so that has to be reviewed and approved by another engineer like B and his supervisors or his manager, and as well as process safety system experts who are having thorough knowledge about this process. So they have to review it and approve it. Then only it can be implemented in the plant. This application program safety cycle requirements. Further, this application program development maintenance shall follow the SIS safety life cycle requirements as below, because the implementation, maintenance, etc. follow based on the safety life cycle. Application program development and architecture. Application program architecture to fulfill the specified requirements for application program safety. Review and evaluate the requirements placed on application program by the hardware architecture of the SIS. Specify the procedures for development of the application program. Application program development and the basic architecture has to be addressed and educated for the people who are all involved in those process. Application program design. Develop the application program design. Identify a suitable set of configuration, library management and simulation and test tools for the safety life cycle of the application program. So all the library which is inside the processor software has to be updated, and the simulation test tools for each type of program logic controllers for the safety instrumented system has to be updated. And there could be some test tools like emulator or simulator may be there, that has to be reviewed and approved during the design. SIS integration test. Integrate the application program onto the target logic solver, including interaction with a sample set of field devices and or the simulator. That's what. This is like uploading the program respective processor and then verify the healthiness of those processor by giving a simulation in the field for the input and selecting the right valve to operate and reviewing the output. This is one of the requirements to do an integration test when all the sensors, sys logic solvers and final elements are placed in line. This is a sample program by the Siemens, by vendor Siemens. These are all the standard library blocks. So the user can call the library and then pull the respective block to add and create his own program. And this is another screen showing the diagnosis which can be used to troubleshoot any error, anything in that application. So again, this is one sample ladder logic drawing. Here one pump is going to be operated using the ladder logic drawing. So these are all the different blocks being used in programming, and this represents the brackets, two brackets represents the coil, and this two straight lines represents the contacts, This shows an open contact. This is normally open, we call, and these are all normally open contacts. Similarly, these are all normally open contacts. But whenever the system is in operation, that has to fulfill all the pre-requirements for the pump to run. So when all the pre-requirements for the pump to run is set, like it may have a lubrication for the bearings. The lubrication supplying oil tank should have adequate level, and there could be some cooling water for reducing the temperatures on the bearings, etc. So the cooling water temperature has to be within a operable limit. You cannot go to 60 degree, 80 degree and all, wherein the cooling cannot happen and the equipment bearings cannot get prevented. Like this, all these interlocks has to be satisfied for the pump to run. And this shows the small application program based on the ladder logic programming. This particular ladder logic is being used across many manufacturers. Only the type of implementation and the type of blocks may little bit differ from each manufacturer. However, all of them has to be approved as per the approval of the international agencies. Operation and maintenance team responsibilities on the SIS application programs. Operation shall have access to details about what instrumentation is involved in the safety programming. Control engineers need proper design documentation to ensure that safety functions are not compromised during the program maintenance, because they will have to follow a documentation. Otherwise, the maintenance engineer may not know what is the application program developed, what is the logic built inside the application program and all. So they have to have a quite adequate knowledge to work on the particular safety instrumented system logic solvers. Maintenance personnel need to know that the instruments that they are working on is a SIS instrument in which the application program is connected to undertake proper care while carrying out maintenance. So the maintenance personnel has to be knowledgeable enough to do the maintenance and avoid any spurious actions or trippings of the plant. That's all, my friends. Thank you. Hello everyone, I am going to make a presentation on safety instrumented system, testing and repair deferral basics. Video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe. SIS testing and repair deferral. In safety instrumented system, when it is designed, decisions and assumptions are made which factor into establishing the proof test interval. SIS proof testing is a routine maintenance activity to be performed for SIS instruments at a periodic interval. Like the routine maintenance for the other normal instrumentation and many electrical and mechanical devices in the plant, for the safety instrumented system, the proof testing, it is called a proof testing, which is arrived by making different calculations, which has been seen in the earlier presentations, and also as per the international norms, IEC standards, ISA standards, the proof testing has to be done. So proof testing is a different type of test other than the normal routine maintenance activities. So that has to be done in the periodic interval. At times, the proof tests cannot be done as per the schedule, and in such cases, deferral has to be made according to the IEC standards. This topic describes what is required when the proof test interval cannot be met. So here in this presentation, our interest is to know how to tackle the cases where this testing may not occur in the scheduled interval. There are reasons for not performing this testing. There may be a possibility of postponement of the plant shutdown or turnaround. The instrument valve which is scheduled to get proof tested, which is the instrument valve which is scheduled for proof testing, may not be possible to do it online and require equipment or unit shutdown. Plant operations is not in a position to shut down the plant due to high market demand for the product or availability of raw material in huge quantity. The process plants, safety instrumented system, valves and instruments are installed across many areas. Some areas there will be standby equipment so that isolation is possible and the instruments can be taken offline while the plant is in continuous production mode, and the proof testing can be performed. But in some cases, there could be only one instrument which is also on the main process line, and shutdown of such instruments is not possible due to the equipment continuous running, and there is a huge demand for the market for the particular product. The plant operations will not be ready to stop the production and give an isolation for the sake of proof testing. So they would like to make it to a next available opportunity. What is deferral? When the SIS proof testing is not performed on time as per schedule, there is a possibility to take deferral to certain extent. Deferral process initiation is done based on evaluation and confirmation that it is safe to allow the deferral. This is done by first identifying and involving key production, maintenance and design personnel, including safety experts. So the decision has to be taken cautiously so that the safety integrity level will not be compromised and the equipment is still healthy enough to perform the function when it is demanded. Then, by reviewing the equipment history, conducting a visual inspection, performing probability of failure and demand calculations, and gaining the acceptance and approval of plant management, operation of the unit may continue up to the limits of the deferral period. These are all the several precautions that has to be taken before taking a decision on the deferral. Problems due to deferrals. Despite the extraordinary consequences of delaying important repairs, deferred maintenance is common inside facilities and manufacturing plants. It also contributes to safety hazards, energy inefficiency, and reputational damage for organizations. Ideally, whenever the plants are running and they have to get certified and recertified during certain period, maybe after 3 years or 5 years, by external auditing agencies like ISO and Bureau Veritas, like that. Many agencies will be there to conduct an audit about the safety instrumented system deployed in the plant and ensure that they are being tested and maintained as per the international norms. So whenever the plants are running continuously and the operations may force to run it and avoid the proof testing by taking a deferral. So this is a common problem across many plants. So in the other way, it contributes to safety hazards, energy inefficiency, and reputational damage because the records and the proof testing has not been performed regularly as per the international standards. The auditing will capture and make it an action. So which is not ideal for the good industries. Deferred repairs are often put into a maintenance backlog that creates a vicious cycle. As necessary upgrades are postponed, system failures start increasing at a greater volume and frequency. This puts maintenance teams in a mode of reactivity with less focus on preventive maintenance. So, whenever there is a chance and getting postponement of the proof testing, so by taking a deferral, it amounts to huge accumulation of the maintenance activities. So, moreover, the upgrades like Microsoft and many upgrades are coming in the plant run time. So, whenever there are upgrades and it is not taken care and immediate attention and upgrade is not done at the right time, it gets accumulated and the maintenance teams gets more work orders or more maintenance tasks at a certain point of time. So deferral procedures. Deferral procedures should be developed so that the potential need to defer preventive, predictive or reactive maintenance is an exceptional event. not a matter of routine. So what happens whenever a deferral is taken and scheduled maintenance is being postponed and it is getting delayed by months or couple of months. So whatever the task which was already pre-scheduled in those time will get impacted. Like it could be a reactive maintenance, it could be a predictive maintenance, or any other routine maintenance. So that could be impacted. These are all the problems with the deferrals. Deferrals can be handled using the management of change process or by approved procedure. Deferrals should undergo technical review to ensure the company's risk criteria is being met. In the event of company's risk criteria would not be met, then temporary compensating measures should be put into place until the protection is returned to as good as new condition. So whenever the safety risk criteria which is already designed cannot be met, so there could be a requirement to make an alternative or compensating measures. The most common deferral request to delay inspections, proof tests or repair. Common reasons for deferral are as follows. Equipment that safety instrumented function is protecting is out of service. The SIF must be tested before the equipment is returned to service. This is a preview of ISA, the standard TR 84.00.03 issued in 2019. A turnaround is scheduled shortly after the scheduled test of the safety instrumented function. The intent is to perform the test during the turnaround. So there is any test planned just after the shutdown, it will be ideal to take it during shutdown and complete the task in a safe way. Spare parts or other required resources are not currently available. This is also one of the reasons. Sometimes the proof testing is not done in a right time, appropriate time, and goes for the deferral. So the maintenance team has to look into the required spares and get it identified and procure it in time before the scheduled maintenance proof testing activity. The equipment cannot be accessed or repaired online. So this is what when the production is running and the single equipment is there in the process line, there could be a reason that the equipment cannot be isolated, the instrument cannot be isolated and tested online. So which means taking a forced decision to take a deferral. SIS testing and repair deferral. Industry best practice is that deferrals be approved and authorized by competent personnel who are accountable for safe operation. This competence includes understanding the equipment operation, the risk SIF is designed to reduce, and the equipment reliability history. These are the several factors to be considered. Typically, operations, maintenance, and technical representatives are involved in the approval process. In some cases, this is one particular company strategy may indicate different levels of required review and approval dependent on SIF complexity, the safety integrity level, the potential event consequence severity that the SIF is protecting against, and planned deferral length. This is for a particular company. They have a different strategy by calculating the required risk and then take the deferral. So deferral approval matrix. So when it is in compliance, less than or 30 equal to 30 days beyond the test or inspection due date. It is done within 30 days of the due date, it is in compliance. And if it is going from 31 to 60 days beyond the test or inspection due date, it requires unit supervisors and managers approval. And the testing goes beyond 61 to up to 90 days beyond the planned test schedule, then it requires the site manager's approval. When the testing goes beyond 90 days beyond the test or inspection due date, then it requires the approval by the operations vice president or safety department vice president and all. So these are all the constraints whenever the plants are running continuously and the maintenance activities is proof testing activities getting postponed, which results in deferral. So as far as possible, the SIS instruments has to be tested at a desired interval schedule to in order to have the safe operation and keeping instruments in healthy conditions always. Thank you. Hello everyone, I'm going to make a presentation on sys testing and repair deferral about the maintenance requirements. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe. Sys repair deferral in safety instrumented system, when it is designed, the decisions and assumptions are made which factor into establishing the proof test interval. Sys proof testing is a routine maintenance activity to be performed for sys instruments at a periodic interval. At times, the proof tests cannot be done as per schedule, and in such cases, deferral has to be made according to the IEC standard, International Electrotechnical Commission standards. This topic describes what is required when the proof test intervals cannot be met. Maintenance or testing design requirements. The safety instrumented system shall be designed in accordance with the maintenance and testing requirements defined in the Safety Requirement Specification. The design shall allow for testing of the sys either for full system or in parts, where the interval between the scheduled process downtime is greater than the proof test interval. Then online test facilities are required to perform testing. So whenever the scheduled process downtime, that means the scheduled shutdown for the plants is more than the proof test interval period, then it requires an online facility to be developed for doing the proof test online. The maximum time the sys is allowed to be in bypass, repair or testing while safe operation of the process is continued shall be defined. What is the maximum time allowed to run the plant without any protection has to be defined. What is deferral? When sys proof testing is not performed on time as per schedule, there is a possibility to take deferral to certain extent. Deferral process. Deferring test without proper evaluation and approval is not acceptable. The sys test deferral process is to be followed when delays in excess of the defined schedule date. If a proof test is not completed by the end of the month in which it was due and an approval deferral is not obtained, the test will be considered overdue and a test recovery plan shall be developed. There is a certain allowable time limit up to which it can be done. Normally it is 1 month, but a safe factor, it is considered like it is the end of the calendar month shall be like a deadline. If it is not done within that time, then it is marked as overdue, so that additional attention will be given by the maintenance and operation teams. Okay, sys testing and repair deferral. A test deferral up to 50% of the prescribed inspection frequency beyond the scheduled test date requires approval by production leader, safety leader, and technical center in charge. Test deferrals beyond 50% but not exceeding 100% up to a period of maximum 1 year require an additional approval by technical center in charge and plant operation leader. However, 1 year is the maximum duration allowed for sys deferral. This is the maximum period the instrument testing, proof testing can be postponed. Verifying deferral. Even though the deferral is an alternate option while not able to perform sys proof testing as per schedule, precautions to be taken before approving sys deferral. The test be reviewed, verified by many agencies, and then only deferral can be operated. Review the equipment history. Gain the concurrence of the qualified expert to the deferral. Define the communication plan. Obtain approval signatures for the required leadership levels. Update the required information in the maintenance management system. File the deferral form in the sys file and applicable LOPA documentation. So all this history of the particular instruments which is under testing has to be done. So when repair is needed, at the time of a failure or malfunction is noted, an assessment on the repair is made by the owner, safety coach, and maintenance personnel. Repairs not complete within the time it was due and an approved deferral is not obtained, the sys loop is considered impaired. So this instrument is continuing to function and the proof test is not done as per the planned schedule interval, as well as it went into some repairs and repairs are not attended to. So then it becomes that particular loop becomes a segment. So deferring repairs without proper evaluation and approval is not acceptable. The sys test deferral process to be followed when the delays in excess of defined proof testing are expected. So whenever the deferral goes beyond the limit, and there are certain steps to be followed for taking deferral, and it requires a different level of approvals to make attention to the responsible persons and leaderships. Approval must be obtained from the business leader to put alternate protection in place and document in sys records. Whenever the sys instruments are not available and the plants has to run without stopping the production, then it requires an alternate protection so that the safety integrity of the plant is being maintained. If essential operation of the process must be discontinued, it is required that the repairs has to be done or proof testing has to be done. So if it is ultimate to be done, then it requires the plant to be shut down for a particular period of time. Repair deferrals applies only to those sys components which are redundant. So whenever there are redundant instruments only, the repair deferral process can be applied. So this is a deferral approval matrix. And the deferral is less than or equal to 30 days beyond the inspection due date, it is considered to be in compliance. When the deferral goes between 31 to 60 days beyond the test or inspection due date, it requires the unit supervisor and manager approval. When it goes from 61 days to 90 days beyond the test schedule interval, then it requires a site manager approval. When the deferral goes beyond 90 days of the test due date, then it requires approval from the Vice President Operations and Safety Department in charge. So why this different kind of approval is in place? Whenever the sys instruments are taken out of service or the proof test cannot be done due to the continuous function of the plant, then that has to be given high priority and attention to the top management. That's why the up to certain limit the managers within the plant managers can manage. When it goes beyond certain period like more than 60 days, it requires attention of the site manager who is a higher level person, and he can put more resources or he can take an action by discussion with the operation to do the proof testing. Or when it goes further extend beyond 90 days, it goes to the attention of the Vice President Operations, so that the particular instruments has to be given an attention, or the Vice President Operation or the plant top level people should be aware that the particular system is running without a proper proof testing. So the consequence or probability of dangerous failures happening may be high. So these are the reasons why the deferral approval requires to different level of people, and whenever the time is getting extended, it gets escalated to the higher authority. Thank you. Hello everyone, I am going to make a presentation on safety instrumented system maintenance. This is a basic topic. Video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe. Maintenance needs. It is very important to perform timely maintenance on safety instrumented system for safe, reliable operation of the plants. SIS maintenance is also auditable by external certifying agencies on safety systems, applicable as per government regulations, varies in each country. Because safety instrumented system is being deployed in the plants for the safety of plant equipment, protection, and people as well as the surrounding environments. So, any violations with respect to the installation of such safety instrumented system is being auditable, questionable, and various government have different kind of strict regulations based on the region. Accordingly, all the respective plant owners, or if it is a government agency, the government shall do the proper maintenance and keep their instruments and equipments in a safe operating condition. SIS maintenance is part of SIS life cycle, which is responsible for operation and maintenance of the plant facilities involving safety instrumented system. We have seen about the life cycle starting from the scratch, like evolving safety instrumented system by doing the LOPA, PHA study and all, and making SIS design, SIS implementation, commissioning, validation, testing, verification, and operation and maintenance. So the maintenance is also part of a safety life cycle. Various components in SIS maintenance. We'll go over the critical items which is important for the SIS maintenance. Installation testing. Testing which occurs immediately after construction. This testing include the below items. Grounds are installed and healthy. See, we are discussing about the safety instrumented system, wherein the sensor, logic solver, and final elements, they have been wired and powered by different power sources like 24, maybe 24 volts, in some cases 110 volts, etc. So all these instruments, whatever installed either in the plant site or in the control environment like enclosure house, control room enclosure house, they have to be properly grounded so that any fault coming in the instrument or on the particular line, it can be grounded and any accidents due to wrong grounding can be avoided. So this is the first requirement. Second one is energy sources are connected and operational. So whenever the construction is happening, there are multiple agencies working in the plant, and somebody will be laying the cable, some other contractor will be doing the termination, some other contractor will do the termination on the switchgear side. So there could be a mistake. Some people, one contractor may do the cable laying and then just leave it. The second and third contractor has to come and do the connections. Probably that may be missing. So these gaps has to be cleared, identified, and then ensured that all the connections are done at both ends and the tightness is checked, and so that it is ready for operation. So any debris material are removed. So we are talking about the various sensors like pressure, differential pressure and flow and all, having a tapping from the piping part, and then it is coming up to the instrument sensor level. That piping, the instrument tubing from the main piping up to the instrument may get choked due to any debris or any dirty materials coming inside the tubing. So those has to be cleaned up. So the instrument has been properly calibrated. And next one is all the instruments which are put into service are calibrated and they are available for the required operating range. Supposing the pressure, for example, a pressure transmitter is supposed to work from 0 to 10 kg per square centimeter, and the design might have chosen a pressure transmitter for the range from 0 to 15 kg per square centimeter, giving some margin on the higher side. The working range may be 0 to 10 kg per square centimeter, whereas the instrument range may be from 0 to 15 kg per square centimeter. So in this case, the instrument has to be calibrated for 0 to 10 kg per square centimeter. So that has to be calibrated at the factory before dispatch, and as well as when the instrument arrives at the plant facility, there also it has to be calibrated and verified for the proper operating range. Input-output signal circuits are tested for healthiness. This is again the cable loop check, we call it. The cables has to be tested and ensure that all the circuits are healthy, all the loop wirings, everything is healthy and connected properly. Next one is validation testing. This is the testing that occurs after construction and before startup. This is known as pre-startup tests. This testing ensures that the system as a whole is operational and performs as intended. This is a complete loop test using the installed field sensors, logic solver, and actual field equipment, including valves and mechanical devices like example pumps, generators, etc. So validation testing means we have to simulate the conditions according to the actual process. It could be like if it is a fluid flow line, some cases it may be water, some cases if it is a gas fill line, it may be nitrogen or an instrument tire that could be used and tested. So in this case, the sensors will be tested according to the calibrated range, and the logic inside the logic solver will be doing the performing function. Finally, the final element will be closing. So the complete loop starting from the sensor and operation of the logic solver and final element, the complete loop is testing is known as validation testing. So this is a pre-requirement before any plant startup. This is known as pre-startup test. Okay. And mean time to repair. This is another terminology which need to be known for the maintenance people, which is very essential. Average time required to repair or proof test a particular instrument once a failure has been detected for multiple sensor configurations. This is the average repair time required between failures. For example, assume that a repair part isn't available and must be special ordered. The repair part is unlikely to arrive before the MTTR is reached. In this case, the production manager should be informed of this likelihood as soon as possible, as special operation actions up to and including the plant shutdown may need to be taken up if twice the MTTR is exceeded. So, the meantime, the repair is arrived as, like for example, 24 hours or 72 hours, for example. So, the maximum allowable, if it is a 72 hours, maximum allowable, which is 3 days, then the maximum allowable time is up to 6 days only. So, in this case, priority should be given at a very high level so that it has to be taken up to the production manager's knowledge so that any management actions will be in picture to speed up and restore the instrument and then the safety instrument system part. Proof testing. This is a testing that occurs after startup as part of ongoing maintenance. Written proof test procedures specific to that sys and sys component define what and how the sys components are to be tested, as well as specifying who is qualified and what the required qualifications are to perform the tests. So for the proof testing, there shall be written proof test procedures, and the people who are all involved and working in this safety instrumented system need to be certified as well to do the testing. These tests may be more rigorous than similar preventive and predictive maintenance testing for similar pieces of equipment that are not part of SS. Similarly, we will have a pressure transmitter for the which is connected to the safety instrument system. On the same line, there will be another pressure transmitter which is connected to the basic process control system. A basic process control system connected transmitter may have a calibration cycle once in 5 years or something like this. Whereas the instrument which is on the safety instrumented system may be having only half of the period, like 2 years, 2.5 years, 3 years, based on the SIL level available for which it is installed. So, meaning that instruments on the safety instrumented system part will have a more rigorous testing as part of the proof testing. So, this is what we are talking. Assuming this is a piping, and wherein there are two valves. This is known as on-off valves, and in the piping there are pressure transmitters which is measuring the pressure of the process flowing inside the piping, and all the pressure signals are being connected to the logic solver, sys logic solver, which is known as safety instrument system logic solver, and the logic solver senses the signal from the 3 transmitters, and this is in the 2 out of 3 voting mode. So whenever any two transmitters going for a higher pressure and gives a signal to the logic solver, then it will perform an action and give a command to close the valve. There are either A, if it is, it may be numbered as A, B, C and all. It could be AB, AC or BC. So in either one combination, whenever it is going high, then the logic solver will put an action, make an action to close these valves. This is why this is known as 2 out of 3 voting. Any two going above the limits will give a signal for the valve to act. Maintenance. The plant shall maintain records that certify the proof test or inspections were completed as required. These records shall include the following information as a minimum: description of the test and the inspections performed, date of the test and inspection. So what kind of test is being performed has to be updated in the record. Person name, designation, who performed the test and inspection, serial number of the instrument, system tested. For example, the loop number, tag number, equipment number and safety instrumented function SIF number. Results of the test and inspection. For example, as found and as left conditions. As an example, if it is a 0 to 10 kg pressure transmitter, when it is calibrated and is taken for the proof test, at the beginning, the same 0 to 10 kg pressure has to be applied and checked in the transmitter or the sensor part, whether it is responding, whether the 0 from the calibrator gives the 0 reading from the sensor, and the 10 kg per square centimeter gives the 10 kg per square centimeter reading in the sensor. There could be some small error. Instead of 0, it may go to 0.5, and 10 it may go to 9.5 or 10.1, 10.2 like that. So if there is any such error, then the pressure sensor has to be calibrated according to the predefined range, which is a design range. So the maintenance technicians has to note down the actual reading in the beginning, which is known as found reading, and the calibrated value, which will be the as left condition. These are all the points to be taken care in the maintenance. Thank you. Hello everyone, I am going to make a presentation on safety instrumented system maintenance, detailed process. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe. Maintenance and design interfaces. Whenever the plants are going into operation, there could be many kind of interfaces between different groups for the safe operation of the plant. So maintenance and design interfaces, we'll look into it. The design shall allow for testing of the sys either end-to-end or in segments, whether the interval between the scheduled process downtime is greater than the proof test interval, then online test facilities are required. So the safety instrumented system part shall be capable of doing maintenance on instrument wise. The design should be done in such a way that each instrument can be taken up for maintenance as and when required. When an online proof testing is required, the test facility shall be an integral part of the design. So in some cases, there could be only one instrument which may not be able to be isolated while the process is running. So there shall be a provision to do an online testing. So the design should have considered for making such a provision. Maintenance needs. When the test or bypass facilities are included in the safety instrumented system, they shall conform with the following. The sys shall be designed in accordance with the maintenance and testing requirements defined in the SRS. SRS stands for Safety Requirement Specification. The operator shall be alerted to the bypass of any portion of the sys via an alarm or operating procedure. Whenever any safety instrument system is taken out of service, then the operator should be highly alert. So, in case of any hazards happening in that area, he will have to do manual action to contain the hazard. That's why an alarm has to be provided, and also the operating procedure will be there for the operations to understand and take a preventive action. Okay. Various components in sys maintenance. Forcing of inputs and outputs in sys shall not be used as a part of application program operating procedure, and maintenance. Forcing of inputs and outputs without taking the sys out of service shall not be allowed unless supplemented by procedures and access security. Any such forcing shall be announced or set off an alarm as appropriate. Forcing means bypassing. If there is any requirement for a particular system to work, there shall be many interlocks which may be required to be satisfied. So, in the normal operating conditions, it will normally get satisfied. But in some cases, these conditions may not arise, which may call for a bypassing or forcing. Forcing means we are manually forcing the required pressure range or required flow or temperature as the case may be. So this may be required to be done during the plant running condition for different reasons. If such forcing is being done, that has to be alarmed and annunciated, so the operations will be alert. Maintenance and engineering interfaces. Maintenance engineering interfaces shall provide the following function with access security protection to each. Sys mode of operation, program, data, means of disabling alarm communication, test, bypass, maintenance. All these activities shall be required to be done during the plant in operation, which means this is also in operation. Sys diagnostics, voting and fault handling services, including add, delete or modify application program. There shall be features to do the self-diagnostics on the self-instrumented system, and the program may be required to be modified whenever the process is in working condition, process is in operation. So such kind of requirement has to be done during the engineering stage. Data necessary to troubleshoot the sys where bypasses are required, they should be installed that such an alarm and manual shutdown facilities are not disabled. Whenever any bypasses are required, so shall be a provision to do that bypasses and shall be alarmed to highlight that that particular system is in bypass. Enabling and disabling the read-write access shall be carried out only by a configuration management process using the maintenance engineering interface with appropriate documentation and security measures such as authentication and user secure channels. So there could be some bypass requirements which may need to enable, for example, a pump run may be an enable requirement. Actually, in the process, that pump may not be running due to the non-requirement of the plant or etc. So in such cases, there could be a need to do a bypass as if the particular pump is running. In such cases, all the actions shall be captured in documentation so that any mistakes or any failures can be corrected. Proof testing requirements. The sys shall be designed in accordance with the maintenance and testing requirements. A proof test is a physical test to determine if there are problems with the sys or BPCS. IPL means independent protection layer. Independent protection layer component that the online diagnostics does not check. For example, for a sensor, this could be plugging in the sensor line, a pinhole in the diaphragm, or undetected electronic drift. So these are all hidden failures. So during proof testing, these failures could be revealed. That's why it is always intended as recommended to go for the proof testing as per the calculated arrived cycle. The proof test brings out faults, problems on the instrument, if any. If there are any such problems, thus that will be highlighted in the upfront. Depending on the redundancy and application, the proof test may require instruments be pulled out of service or process units to be shut down. This is why it is very important to consider proof testing when designing a sys. In all cases, the goal of proof testing is to return the component to as good as new so that the healthiness of the instruments is ensured. So not only the instrument healthiness is ensured, but the protection for the people and environment as well as the mechanical equipments is taken care. The performance of all sys components must be periodically proven via proof testing, including sys category valves, The degree to which a sys valve is leak tested is determined by its required functionality. This is a requirement about the sys valve leak test requirements. There are some leakage classes set by the APA standard. APA 598 is a standard for doing the leak test requirement. Based on the plant unit, the criticality, some valves may require zero leakage. Those valves that are determined to require a bubble tight leak performance, also called a tight shutoff, due to the exponentially low weak limits necessary to maintain the risk mitigation, need to demonstrate its level of performance. Some valves in the plant may require to have a zero leakage, which means class 6 as per the API 598 standards. So if that be the case, the internals will be designed to meet that zero leakage requirement. As well as during the testing, when the valves are coming into inspection, they can be tested for the zero leakage case. Options for bubble tight testing are to conduct bench testing in the valve shop or in inline testing. For example, this valve requires a zero leakage. These valves need to be tested in the workshop inside the plant to have a zero leakage. In case it is not achieving the zero leakage, then the plant owner has every right for the manufacturer of the valve to come and replace it, or he will do some necessary repair by putting a better seal or making a proper lapping in the valve body, etc., to make sure that the valve is going for a zero leakage. Sys logic solver testing. Proof testing, repair and documentation procedures also applies to logic solver. Maintenance frequency of logic solver may be different than the sensor and final control elements. Usually the proof testing of logic solver is matched with the plant's turnaround or major overall frequency so that operations are not affected, because proof testing of the logic solver is a really challenging one. During this time, the entire plant may not operate, or taking into manual the all isolated devices is very cumbersome and difficult. So in this case, the testing of the logic solver is always planned along with the plant shutdown or turnaround times. Even though the plant goes for shutdown, the logic solver functionality may not to be retained to maintain some essential services like cooling water, steam, etc. Even though the plants go to some short shutdown, still the cooling water requirement, instrument requirement and air requirement, everything will be there. It is not easy to do to do the testing of the logic solver, even if it is just short shutdown. That has to be performed proper calculation and enough resources to do this one. Otherwise, during the small shutdown also, the plant process will be keep on running. Only there is a major turnaround when all equipments will be isolated. So that time only the logic solver will not have much impact. The logic solver hardware must be periodically tested according to a written proof test procedure. Unsafe and undiagnosed failures. So that order has to be tested as and when possible. Okay, thank you. Hello everyone, I am going to make a presentation on safety instrumented system failures. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. Sys failures. It is very important to understand the types of failures on safety instrumented system and methods to improve the reliability. Failure types. There are two types of failures which are important to be considered in design of sys and to improve safety instrument and system performance. Random failures and systematic failures. These are the two major categories in which the safety instrument system can fail. Random failures. This is a type of failure occurring at a random time which results from one or more degradation mechanisms For example, aging of sensors. This is applicable for the sys sensors. For valves, damaged diaphragm, O-rings, leaks, etc. The valves have a lot of mechanical components like seals, O-rings, and pneumatic devices. Any damage in those diaphragms and all can result into a random failure. Random failures can be effectively predicted with statistics and are the basis for the probability of failure on demand based calculation requirements for safety integrity level. As we know, with the terminology, the failure itself is a random. So the type of failure cannot be predicted. However, this can be done over the period of many years across different industries, performing the similar operations or similar environmental conditions. So the nature of failures may be typically similar from one plant A to plant B. And these kind of failures are they are about the internal components of a valve or a pneumatic booster relay or air filter regulator, or it could be in the actuator components wherein lot of small mechanical components are there. So failure of such parts is quite difficult to understand from the external view of the equipment and instruments, valves, etc. And secondly, for the sensors, due to the aging, the diaphragm part, which is the one sensing the pressure and giving an indication through the microprocessor based electronics back to the control system, basic process control system, or a safety instrumented system. This can get failed due to continuous service and whichever is in long time operations in the process. Bathtub view. So the failure behavior of a population of hypothetical devices over their life cycle, that is from production to disposal, is commonly represented by the bathtub curve as shown in figure below. This will just go over it. This is the figure. We'll go over it, the description, and then see the diagram. This plot shows how the overall failure rate of a device changes with time. The initial failure rate of the hypothetical devices is driven by its burn-in or infant mortality rate, which declines rapidly. This is the initial failure rate immediately after the production or within few days of operation, etc. The middle flat section of the curve represents the useful life of the device and is typically characterized by a constant failure rate. The middle part, which is in green, is the useful life, and in normal circumstances, the healthiness and operation of any instrument over this life period is quite long, and there could be some rare failures. This SIF performance calculation is based on this middle section. The last part represents the wear out or end of life failure rate and is characterized by an increasing failure frequency. For example, if a sensor is designed for a healthy life of about 50 years, this is for an example. So this early life is up to 1 year may be considered. So up to 1 year period, there could be a chances of failure due to any manufacturing defect, or it could be a common component failure, etc., which can happen during the early life of the instrument. And the useful life, which can spread around, for example, if the total life of a sensor is 50 years, and the useful life may spread around 45 years. So in this period, normally that sensors will work healthily without any issue, but there are some chances due to the harsh environment or the process self, or it could be due to some electronic failure due to high temperature, etc., which can result in a failure. This is what mentioned as due to wear out. Useful life ends when failure rate starts to increase due to wear out failures. If this curve is going to be exist for 40 years plus, maybe 25 years to 30 years, the sensors can work healthily, and then it can start failing at a quite higher frequency. And this last part, which is known as a wear out period, here for sure there could be chances of failure happen quite frequently, and that's why this is shown in red zone. So in the yellow zone and red zone, the probability of failure is quite high, and in the green zone only, the instrument healthiness and effectiveness of its working is for many years. So this is the years of shipment. This is the x-axis is represented by years after shipment, and y-axis is represented as return rate, mean time between repairs, MTBR. Okay, this is shape of the curve is like a bathtub. It is given as bathtub curve. This is applicable for all instruments and also specifically for the safety instrumented system. And another type of failure, which is known as systematic failure, a failure that happens in a deterministic, not in a random way, predictable fashion from a certain cause, which can only be eliminated by a modification of the design or the manufacturing process, operation procedures, documentation, or other relevant factors. In this type of failure, all the failure happening in a systematic way, which could be identical from plant A to plant B. So similarity of this type of failures or 4 or 5 instruments in different plants, it can be identified as a systematic failure. So how to correct these systematic failures? Only by improving the design or in the manufacturing process. I mean the process itself, there could be some erratic method which may lead to this such kind of failure of instruments. So that can be modified, and the operating procedures of this particular equipment or instrument can be modified. And documentation means there could be some testing or checking at a regular frequency that could be documented and can be improved. Here we will see in detail about the systematic failures and how to improve it. There are few examples of the systematic failures. Systematic failures are not age related but due to mistakes, errors made in supplier manufacturing process, design, installation, improper maintenance practices, or unpredicted process changes, flow, pressure, etc. If the process is changed, process operation is changed due to get a higher production output or throughput, the flow or pressure in the particular piping can go high, which can go out of the design limits at certain times. This is not always possible. That there could be some chances, rare chances of going to out of design range. And lack of quality assurance testing and certification during the manufacturing process. Mistakes in design specifications, wrong actuator sizing, wrong material selection, including O-ring, seals, etc. The O-ring, seals and all, they are very critical and minute components that are situated in different parts of the actuator, and they are also impacted by the environmental conditions with the temperature, the dust environment, etc. So on the type of O-ring and seals, there are different material. The materials can be of lesser temperature capability. So if you put this in a higher temperature environment, naturally it is prone to fail. So the type of materials used for the type of service and the process as well as the environment need to be evaluated before electing the respective seals or O-rings, etc. Poor initial installation, improper maintenance or calibration practices, configuration of software mismatches, for example, range, time constants, etc. Poor management change procedures, some process changes, verify technology and capability of the system. So these are all rare, but because the operation, they may be interested to increase the productivity or increase the quality of the product. So they may be concentrating the operation side, they may be focusing and concentrating to improve the quality or productivity, and they may not put much efforts or much concentration over the instruments or equipment installed across the plant. So which may at rare chances land into failures. Methods to overcome random sys failures. Design sys configuration as redundant wherever possible. Diversify type of instruments to improve the safety instrumented function, SIF performance. Feedback failure data to technology centers for analysis. There are multiple and repeated failures. The data has to be given back to the technology teams so that they can evaluate and come out with a better design. report the failure to instrument manufacturers about the failure type, incident time, and any issues with the field devices. So, what are the failures identified has to be reported back to the manufacturers so that during the production they can do the design improvement and bring out with a better quality and higher capability material. Utilize reliability models and tools where applicable. Adjust the proof test interval to many failure, human errors, and plan for instrument replacement after useful life period. See, some plants they do the maintenance at regular intervals and do the replacement as and when it is required. For example, if the O-rings has to be replaced after 7, 8 years or 10 years during a major turnaround, they will take it up and do the replacement. But some plants, due to the time limitation, economics limitation, they may skip out and then keep on running. So these are all giving a good chance for the particular equipment or particular actuator or valve getting into failure. Adjust the proof test interval to minimize any failure, human errors, and plot for instrument replacement after useful life period. Follow the recommendation from international safety certification agencies like TUB, EXID, etc. These are the certifying agencies who do the detailed analysis for each of the instrument being manufactured and supplied to different plants at different environmental conditions based on the geographical locations. So the instruments have been put into rigorous testing, and after that only they certify those instruments for putting into the service. So that has to be taken care, and all the end users like manufacturing companies need to go for a certified products. Communicate to all applicable disciplines about any change in the process, flow, pressure, and temperature variations, if any. So, as I told earlier, only the operations should not focus on the changing the quality or productivity for a particular plant. So, they have to analyze and then get in consultation with the design teams, maintenance teams who are responsible whenever they are going for a change in the process condition. This may also have some impact on the instrument install. Suddenly, if they increase the pressure, there could be a chance of the sensor getting failed due to higher pressure. These are for small examples. So those things has to be reviewed with the respective teams, maintenance teams and engineering teams to have a safe operation. Document and share learning experiences with maintenance and engineering teams. EPCs. EPCs stand for engineering procurement and construction companies. So that necessary improvements can be made over the type of construction, installation, maintenance and training. So wherever required, there has to be improvement. So to come out with a better improvement, any failures in the plant has to be communicated back to the manufacturers about the nature of failures so that the better design can be produced for the future products. So this is a combined responsibility. Plant operations and the plant production charges has to take care and communicate to the relevant teams. Thank you. Hello everyone, I am going to make a presentation on safety instrumented system reliability. The video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe. SIS reliability. It is very important to understand the SIS reliability so that the different types of failures on safety instrumented systems can be tackled. Like random failures and systematic failures can be tackled once we understand the types of failures. So the SIS reliability is a concern for the safety experts as well as the production and maintenance teams in a plant. Reliability. Reliability ensures that a SIS element is able to perform a required function over a stated period of time. It is defined on a yearly basis in percentage and is inversely related to fault strip probability. Fault strip probability is that has to be given after the rigorous testing by the manufacturers as per the IEC norms, International Electrotechnical Commission norms. So based on which the reliability can be improved. Why reliability is important? In the safety instrumented system, or the system responsible for the operating safety and ensuring the emergency stop within the limit considered as safe whenever the operation exceeds such limits. Time and again, we are talking about the safety instrumented system. What do? They do the protection. They to take care of the hazards from getting escalated. So the hazards is being contained and controlled to avoid any further damages to the plant, equipment, personnel, environment, etc. So for that, the safety instrumented system has to be in good working conditions and they have to act on demand. This is the main driver. The main objective is to avoid accidents inside and outside the plants, such as fires, explosions, equipment damages, protection of production and property, and more than that, avoiding life risk or personal health damages and catastrophic impacts to community. It should be clear that no system is completely immune to failures, and even in case of failure, it should provide a safe condition. So as we all know, any instrument or any equipment cannot be manufactured giving a guarantee that it can never fail. There 99.9% it cannot fail, but that 1.1% or 0.001% there is a possibility that it could fail. So it is a responsibility for the designers, operating plant personnel, plant in charge, as well as the maintenance teams to understand and overcome such kind of failures. This is why the reliability is important. SIS reliability will further understand about it. For many years, the process industry has addressed SIS integrity and reliability issues through the use of prospective design and maintenance practices, which are sufficiently conservative to assure that the risk reduction can be met in a wide variety of process applications. So this is not talk for the last 1 or 2 days or few months. It is being safety instrumented systems are installed across the plants across the globe, and they have been in service for many years. Some area it could be 30 years, some plants it could be 50 years, etc. So the importance is given for doing a better design. These internal practices are frequently criticized for what it is perceived as over-design because the practices seem to go beyond the minimum requirements of IEC 61511 or other good engineering practices. However, it should be recognized that any good engineering practice documents general practices that are acceptable to participating stakeholders. Meaning, every time whenever the design is done for a particular safety instrumented system components, the manufacturers take care about its quality and then they abide to the IEC 61511 norms. Sometimes there could be a possibility of doing over design which may have a cost impact as well as the time, so that has to be avoided, and the equipment as per the standards developed has to be manufactured. A specific application may necessitate to more rigor, including additional fault tolerance, diagnostics testing, etc. For more guidance related to IEC 61511, refer to these are the two different standards, which are two different standards applicable in different parts of the globe. So they are more or less similar, but it can be counter-checked from one end to the other end wherever necessary. So IEC 61511 and ISA, these are all applicable in two different parts of the globe. One is applicable in the Asia and European environment, another one is in the American continent. So wherever as and when required, they can be interrelated and checked. Reliability principle. The reliability of a measurement system is defined as the ability of a system executing its function within the operating limits and conditions during a defined period of time. So this is the principle. Reliability of measurement system is defined as the ability of a system executing its function within the operating limits and conditions during a defined period of time. Unfortunately, several factors such as manufacturer's tolerance according to operating conditions sometimes make difficult such determination, and in practice what we can get is statistically expressing the reliability by failure probabilities occurring within a time period. It is something like the two-wheeler manufacturer. For example, we are giving a product saying that this vehicle can run for 60 km per liter, but due to practical difficulties like according to the road conditions, it can give only 45 km per liter or 50 km per liter. Then the individual owner who has bought cannot go and make a complaint or argument with the vehicle producer. So this is depending on the practicality. Similarly, the safety instrument system manufacturers also claim about a higher tolerance, but in practical, based on the operating conditions, based on the environmental conditions, the said tolerance cannot be met. So, however, it is important for the safety instrument system experts to understand and apply practically possible installations to go ahead and do the operation of the plants as per the international standards such as IEC and ISA. Reliability approach. Reliability analysis is used to study about the frequency that it will falsely trip the plant. So there are different tools and that can be done. Like there are some tools, Markov modeling and fault tree analysis and reliability block diagram, like that. Some tools are there which are used to do the improvement on the safety instrumented system. And ways to improve the reliability. Evaluate and optimize the occurrence of fault strips. Add redundancy and diversity of instruments. Ensure instruments are protected against potential unrelated damage. Include diagnostics or automatic testing. Nowadays, many manufacturers are coming with products having a self-diagnostics or internal testing with smart meters for a flow measurement principle. And valves are concerned, they have come with the digital valve controllers, which has intelligent microprocessor based devices that can detect the failures in early stages. So such kind of installations has to be made in the plant. So any failures that can occur can be predicted upfront to avoid any consequences with respect to safety. So that's the different approaches by which this reliability can be improved. Reliability benefits. Reliability helps to verify and improve the reliability and availability of safety instrumented system. It helps to identify and systematically eliminate any bad actors, which calls for repeat maintenance. There could be some bad elements like some dirt coming into the sensor part, which can block the sensing tubes for the process to hit the sensor. So this could be due to the process conditions. There are some filters in the upfront of the process maybe not functioning properly, or it could be choked to stop the process, or it may not be cleaned at regular intervals, which can result in the dirt keep on coming and getting blocked into the sensor part. Just such kind of any bad elements which can affect the performance has to be eradicated, has to be removed. Reliability modeling helps to identify and reduce no problem phone maintenance requests. Reliability studies improve cost performance of engineering and maintenance. The modeling helps. Reliability modeling, there are different modeling based on the plant, whatever based on the, there may be installed different software, some ERP tools which can give a predictive and reliability analysis techniques. So the maintenance people who are go into the maintenance, they have to identify and note with any fault that can probably impair the performance of the instruments. If they simply say that there is no problem, no fault is identified, then it is difficult for the future maintenance teams to address it. So this requires a detailed study and understanding about the process and instruments, so which can improve the performance of the engineering and thereby doing a better maintenance. These are all the benefits of the reliability studies. Thank you.